Okay. Since you know who I am and you know how I operate, I'm all about protocols, not putting the proverbial cart before the horse. That being said, tonight, one night and one night only, we're going to put the cart before the horse. The way that I want you to approach ELEC 110, and this is a recipe for success, because like I said, I've been doing this for a couple of years. I know what works and I know what doesn't. And I guarantee you, if you follow the syllabus, if you do all the assignments that you're given, if you follow that recipe for success, you will be successful. You'll pass this class. Guarantee it. I don't know if any of you also know, Lake Washington Technical College has a guarantee that if you graduate our program, go into industry, and your local, whoever you go to work for says you don't know what you're talking about, we will re-educate you for free to get you to the standard that industry says. You know, how many students have been sent back to the electronics program? Zero. So I know it's working. So keep in mind the way that this is supposed to work. I think this really is the best recipe for success. Is I like to read through the chapter very quickly. And what that does is like formats your hard drive for what you're about to receive. That, of course, is a given that you've already reviewed the syllabus. In reviewing the syllabus, that shows you specifically, like on page 1 they start, the course outcomes and objectives. And then you look at how those course outcomes and objectives of the syllabus, which is really the training contract between you and I, how closely the book and the chapter works meet those objectives. So read through the objectives in the syllabus first, then read through chapter 1 or chapter 17, whatever chapter you're on, just like a book. But this isn't a book, it's a textbook. So when you get to the end, it's not going to be like, oh, I never knew it was going to turn out like that, okay? I mean, it's a textbook. It's a text/reference book. After you've read through the chapter, then go through it with a fine-tooth comb. Whenever you come to an example or a problem, take out your calculator and do the math. And follow along and do every practice problem. Keep note of that because that's going to be part of your written assignment. Then when you're all done with the chapter, then I'd read through it again very, very quickly, just to make sure you retained all that information. Some of the stuff that we're going to talk about tonight in chapter 1, like atoms, molecules, you probably have heard before, right? The periodic table, a lot of you have heard that already before. So keep that in mind that if you're going through the book and the book is talking about stuff that you already know, you don't need to beat that to death. And that's actually good because it's going to draw you to focus your attention on those areas that you don't understand. And you're going to be able to dump all of your energy into the stuff you don't understand. Does that make sense? I mean, it sounds really basic when you think about it like that, but that's really what's going to be the most effective means of traversing this. Normally, I will not lecture on a chapter until you've read the chapter, done your homework, and gotten together in your teams and completed a peer review, right, of your homework. Once your homework has gone through that process, and then you've got completed homework, then come into lecture, because you know what I want to spend my time in lecturing on? What you didn't get out of the book, what you didn't get out of the assignments. That's how I want to spend the majority of my time in lecture. Fair enough? Okay. Let's get started. These slides here actually follow the book. And these slides, by the way, are available online on the Google site. The TAs helped you out on how to get that site. The links are right there in your syllabus. So what you could do is you could download these from the site to your computer and then put them on your laptop or home computer and have the same slides that I'm showing you tonight. Also, there are audio files of this lecture in MP3 format that you could download. Joe Gryniuk on MP3. Right? And listen to me when you're working out at the gym or running from the police or whatever it is you do when you listen to MP3s. And then also we're going to be adding to this now videotape of the lecture that we've got our TAs back there working on right now. So ultimately we'll be able to upload that. And the reason that I go out of my way with recordings, with the slides, I've got nothing to hide. I've got nothing to hide. As a matter of fact, I want to give you as much information as I possibly can so that you could benefit from that information. And you know what? How many of you here own any DVDs? Your favorite movies? Why would you own a copy of a movie? Why would you do that? Isn't seeing it once good enough? Why would you go out and buy DVDs of a movie? Because they're cheap. Unless they're giving it away, it still costs money. Why do you? What's that?
Because you couldn't BitTorrent that specific one?
Yeah.
You can watch it anytime you want.
You can watch it anytime you want, but why specifically would you purchase a particular movie?
Because it encompasses your interest.
Exactly. It encompasses your interest. And for those of you that have movies, how many of you have watched the movie the second time and picked up stuff out of it the second time around? That there's some movies I've seen in the theater that I'm like, I got to go out and get that DVD because I want to see this again. I know how it ends up, but I want to see it because I missed something in the beginning and I want to look for that thing that I missed in the beginning or whatever. So it's perfectly natural for you to want to hear this lecture over and over again. I mean, for some of you, once might be good enough, okay? I go to church on Sunday. My pastor, normally, he gets up there and he preaches. I get it right the first time. I don't need to hear it again, okay? For some other people, though, and actually at my church, they do audio recordings, and then people can listen to that content. They want to hear it again. Normally, I get it the first time. That's the kind of guy that I am. That's the type of learner that I am. But look at that. That's the other thing, too, with taking notes. Some of you, it's been a while since you've been in school. Try to hone your note-taking skills. When I emphasize something, I'm usually emphasizing it for a reason, and that reason is you may see it again in the future on a quiz, on an exam, but most importantly, you may see it in industry. Because one of the things I don't want to do is teach you the exam, teach you the quiz. That's not what it's all about. One of the things that I want to share with you is I'm not really concerned. I mean, I want all of you to pass my quizzes. I want you to all pass my exam. I want you to all pass this class. But to be totally honest with you, do you know how I measure your success? I measure your success as to where are you going to be 5 years from now. And did I give you anything out of this course that helps you in that position you're in 5 years, in 10 years? The payoff for me is when you call me and say, Joe, I'm in town or I'm passing through. I'd like to buy you lunch. I like lunch, okay? Swing by, buy me lunch. Tell me what's going on. Tell me what you're doing now and how I had an impact on that. I actually, I went on a cruise over spring break, Caribbean. I was just getting ready to get on the ship, and I get all my emails forwarded to my phone, and I got an email from a student that I had in 1993. And he introduced himself, and he says, I don't know if you remember me. You know, my response back to him, of course I remember you, you know, because again, we established a relationship, a professional relationship. But he graduated, he went down to California, kind of dropped off the radar. He was going to be in the area and was wondering if I'd be available next Friday to get together and we could visit. And I said, yeah, geez, unfortunately I'm out of town. And, you know, but you know, that is how I measured the success. Number one, that he remembered me. Number two, what he learned here is part of his present reality. So that's what I want all of you to think about. Yeah, you want to pass the quiz, you want to pass the exam, you want to pass the class, but where are you really going to use this stuff? Anyway, kicking things off here, this is section 1 of the book. Section 1 of the book, area of the text that deals with what are called DC circuits. DC stands for direct current, and we're going to talk about the difference between direct current and alternating current throughout this. Chapter 1 deals with the fundamentals of electricity. And I got to tell you that these first few chapters are like sacred chapters. You know, we should like ring bells and like hit gongs and chimes or whatever when we speak of some of this stuff. Because if you want to be successful in electricity and electronics, these things that we're going to speak of are critical attributes of what makes stuff work. As far as I'm concerned, I'm going to let the cat out of the bag from the get-go. Okay? The big four things that we're looking at that drive this entire industry are four properties. The properties are voltage, current, resistance, and power. Voltage, current, resistance, and power. Voltage, current, resistance, and power. My cell phone works because of voltage, current, resistance, and power. My car computer works because of voltage, current, resistance, and power. Satellite TV works because of voltage, current, resistance, and power. Anything electrical or electronic works because of those four. So what we really need to ensure is that these four properties that we're going to discuss, we fully understand up one side and down the other. As I said earlier, I've been doing this like since puberty. So you would think that I know everything there is to know about voltage, current, resistance, power. No, I do not. Occasionally I get questions from students that are associated with those properties that I can't quite answer, even though I've been doing this for so long. So I'm on a continual journey to learn as much as I can about those four properties. So we're going to kick things off with Chapter 1 here, dealing with the fundamentals of electricity, but pay special attention to those four properties: voltage, current, resistance, and power. The big four. I like to call them the big four, because they are the big four. It's what everything is based on. If you know what's going on with voltage, current, resistance, and power, you know what's going on inside the circuit. We're going to talk about that. So kicking things off, fundamentals of electricity. One of the things that I do at the start of every lecture is I review the objectives. The objectives that I review are the same objectives that are on the syllabus. That's a pretty good reason why I selected this textbook to use. Although there's errors in this textbook, although it's not the best textbook on the face of the planet, the objectives in the textbook reflect the objectives in the syllabus. One of the other things I want you to fully understand is I don't teach the textbook. I teach the curriculum. The curriculum is contained in the syllabus. The curriculum is derived through input from our local industry advisory committee. This is a group of volunteers that get together on a regular basis, sit down, and tell us what we need to be doing for this program to stay competitive. So this book works really good because you're going to do all the chapters in it. But occasionally, in the future, you may get some textbooks that the instructor is going to say, you don't need to do this chapter. Why? It's not part of the curriculum. Local industry really doesn't think it's important that you learn that aspect of it. So does that make sense? Okay. One of the reasons that I review the objectives as well is to prepare you for what you're about to receive. It's like formatting your hard drive, so that when I start talking about this stuff, you're kind of like ready to store that information away on your hard drive, your mental hard drive, your brain. So let's take a look at this here. Objectives: after completing this chapter, the student will be able to define matter, element, and molecule. There's 3 questions right off the quiz. Define matter, define element, define molecule. It's an objective. I hope at the end of this chapter you could define those. List the parts of an atom, define the valence shell of an atom, and identify the unit for measuring current. Draw the symbol used to represent current flow in a circuit. Describe the difference between conductors and insulators and semiconductors. Define difference of potential, electromotive force, and voltage. Voltage, wasn't that one of the big 4? So again, if this was like church, you'd be ringing bells or gong, you know. We'll talk about projects later. Some of you may want to build sound effects so that we could, you know, whenever do that stuff. Or dim the lights. Voltage. Draw the symbol used to represent voltage. Identify the unit used to measure voltage. Define resistance. Gong. One of the big 4. Identify characteristics of resistance. Gong. in a circuit. Identify the unit for measuring resistance and draw the symbol used to represent resistance in a circuit. A circuit. Everything you are about to learn as it pertains to electricity and electronics is traceable back to matter. Do any of you here know anything about matter? Do you know what matters? Matter is anything that occupies space and has weight. Does anybody know where we could find the absence of matter? Does anybody know, can we create this condition here on planet Earth? Vacuum. And I'm not talking about the Auric 5-pound upright. I don't think that's what you're talking about, right? What kind of vacuum are you talking about? It's called industrial vacuum. And in essence, what we're talking about is pumping all of the matter out of a vessel so that all that's left inside is space, empty space. It's used a lot. A lot of you that go into high-tech careers, you're going to see this process used in the manufacturing process because it allows us to only put into the chamber what we want to be into the chamber. Where can we find a large abundance of an absence of matter? Space. And you know the odd thing about it is that's why it's called space. Because there's no matter. There's no matter. Now, if you're in a spaceship traveling through space and you roll the window down and you stick your butterfly net out and you pick up some cosmic debris in your butterfly net, pretty odd thing to do. Don a spacesuit if you're going to roll the window down to the spaceship, do that. But if you find any cosmic debris in your net, that means that you have found matter. Because if it's something and it occupies space and it has weight, therefore it's matter. Have any of you heard of antimatter? We will not be talking about that here in this program. Okay? I used to think it was science fiction until I was talking about it in a lecture like this, and I had a student raise their hand, and we're not going to talk about it because I don't know anything, the absence of matter, antimatter, the opposite of matter. And he brought in an article the next week about a NASA project. And these NASA teams are all about funding. So all these PhDs and all these scientists, it's all about getting money for them to continue their research. Well, NASA was running out of money, and there was a particular group that was doing research. And they were going to get their operation shut down. So as soon as they all were basically put on notice, you all are no longer going to have a job at NASA. They're like, oh, jeez, that's too bad, that's really bad. Well, why is it so bad? Well, we just discovered a cloud of antimatter, and we think it's headed this way. So right away, NASA gives them more money to continue the research. And somewhere in my archives, I've actually got a picture of this antimatter cloud that, who knows if it even exists. But obviously, if antimatter collides with matter, they cancel each other out. So if there was antimatter cloud that inundated our solar system, we'd be gone. I don't know where we'd go, but this is what they say. Enough said, we won't be talking about antimatter in this class. We're more concerned about matter. Now, the basic building block of all matter that we're aware of, and this is really interesting, is what's known as an element. An element can be found on the periodic table. I must not be a real professor. If I was a real professor, I'd have one of those pull-down charts that's got the periodic table and all the squares, That's the sign of a true professor. I don't have one of those. I could probably call it up on my computer screen, but it wouldn't be the same of having one of those pull-down charts where you could, with the pointer, right? And you've all seen that. You all know what I'm talking about, right? Probably saw it back in elementary school. Elements of the basic building block of nature cannot be reduced to a simpler substance by chemical means. And believe it or not, there are only about 100 known elements in existence, period. Over 100 known elements, period. That means me, you, that desktop, the chair, a cow, a monkey, a sports car, an airplane, we're all made up of 100 of the same ingredients, period. Isn't that amazing? That was one of the things they really didn't know about going to the moon. Were they going to go to the moon and find some new element? They went to the moon and they found the same stuff we got here on Earth. So basically the assumption is in the scientific community that really the entire universe is made up of about 100 of the same ingredients. I mean, I got more crap in my pantry at home. Spices, seasonings, I got all kinds of stuff all over the place. But the fundamental essence of it all, 100 plus elements, period. Everything's made up of those same 100 plus ingredients. Now, we're really focused on the parts of an atom. So when we have an element, the smallest particle that we could break that element down into and have it retain its identity is an atom. So I know you think I'm going all wacky like chemistry on you and everything, okay? Bear with me. We have to understand the essence of matter so that we can get electricity out of matter. That's where we're going with this. The first part of the atom you need to understand is called the nucleus. And the nucleus is not even really a part. I misspoke that. It's not a part, it's a place. And that place is simply the center of the atom. The first true subatomic particle that we're going to talk about is the proton. Proton is a positively charged particle that's located in the nucleus. Okay? And I just said something that's very, very significant. I just said the word positively charged. For the first time in this program, we just spoke of something that has an electrical characteristic, a positive charge. So a proton has a positive charge. The other subatomic particle that's located in the nucleus of an atom is called the neutron. And neutrons are uncharged particles, meaning no charge. One of the ways that I remember it always is proton, proton, positively charged. Both start with the letter P. Neutron, neutrally charged. Okay? They're not positive or negative. They're uncharged. They're neutrally charged. That's why they're called neutrons. Electrons, well, that's the other subatomic particle. And if one's charged positive and one is neutral, then therefore the electron must be negatively charged particles. The electron actually orbits the nucleus, where the protons and the neutrons are located. This is a very, very significant slide. Remember earlier I shared with you a little bit about my background. I wasn't the sharpest tool in the shed. And as a matter of fact, when I was in the Navy on active duty, my uniform, the Navy, even if you sail on a cruise ship, you have a symbol that identifies what division you're part of. And for me, I had on my arm my chevrons, that signified, my rank. But then I had a helium atom on my arm. And that helium atom was to signify matter. And the helium atom with the electron orbiting around the outside was to signify electrons orbiting the nucleus. Why? Because I was an electronic technician. And I basically went for like 3 years of my career before I realized, why is there like an atom on my arm? Okay, What does that mean? What it means is the electrons orbiting the nucleus, because I was a subject matter expert, a technician on the behavior of electrons. That's what you're all here to learn. If you're here to learn about electronics, you're here to study the behavior of the electron. And that's what we're really going to talk about. Make sense? One of the things I do not want you to study while you're here in this program, and I'm pretty open-minded. If you want to go off and do some projects and stuff like that, I'm all about it. One of the things I really don't want you doing is anything with the nucleus of the atom. Okay? And if you plan on doing anything with the nucleus of the atom, give me fair warning. And I think I'll stay in Federal Way that day. Okay? And then you could have at it and try to split the atom or do whatever it is you're going to do. But when you start playing around with the nucleus of the atom, bad things happen. As electronics professionals, we're only going to play around with electrons. As a matter of fact, we're only going to play around with certain electrons. And I'm going to share those electrons, what those electrons are with you in a moment. This is kind of sort of what it looks like, maybe. This is an artist's depiction, and the scale is really, really off. The proton is a very big particle. The neutron is a very big particle. So the nucleus, this is kind of working. Okay, this is kind of working for me. The electron, though, is not the same physical size as the proton. The electron would be like the spot of my laser pointer. But in actuality, if this truly was the neutron and the proton, I don't think this spot of my laser pointer would even be in the room anymore. That's how far the orbit is around the nucleus. I heard it once explained as like a cathedral. If you had the size of a grapefruit in the center of the cathedral, the electrons orbiting would actually be like on the outer walls. It'd be really, really far out there. So the scales here are off, but this gives you an idea what's going on. One thing I want you to understand also is that all matter, when in its neutral, natural state, has an equal number of protons and electrons. Protons are positively charged, electrons are negatively charged. They're equal number, so they cancel each other out. That means that matter is in a neutral, natural state. Did that answer your question? You got a balanced. Right. So there's an equal number of electrons and protons in atoms until we do something to it. We're going to talk about that in a minute too, because we're not just going to let everything stay in a neutral, natural state. If we did, we'd be out of jobs. We wouldn't have current flow. It'd be a drag. A couple of the numbers that you need to familiarize yourself with. And one of the things that I want to stress to you is that all of you are here taking electronics courses. You're here to learn the language of electricity and electronics. That's really what it is. This is like taking a second language. I've actually had a lot of students that speak different languages, and English is a second language, and they wonder if they could come in and do it. It's like, yeah, you could come in and do it. Because you know what? What I'm talking about here is another language. So one of the technical terms that we may use in the future is a number called atomic number. An atomic number simply is the number of protons in the nucleus of the atom. And every one of those 100+ elements that I talked to you about earlier has a unique number of protons. You don't have two different elements that have the same number of protons. So the scientific community embraced this, and they said, you know what? Why don't we just use the number of protons, and that's going to give it its position on the periodic table. Make sense? Okay. The next number I want you to familiarize yourself with is the atomic weight. And the atomic weight deals with the mass of the atom, its weight, its physical weight. And remember when I said that protons and neutrons were big and they were contained in the nucleus? And the electron was just like a little tiny subatomic particle orbiting way outside? Basically, to end up with atomic weight, all you do is count up the total number of protons and neutrons in the nucleus. Count that up, that gives you the atomic weight. Every weight of every element on the periodic table is unique. And basically, the mass of the electron is so insignificant, we don't even take that into account in determining the atomic weight. Make sense? Now this is where things get interesting. First term, shell. This isn't the kind of shell you find by the seashore. What we're talking about here for shells is simply an orbital path around the nucleus. This is where the electrons orbit. They form concentric circles around the nucleus, and they're filled in sequence. Have any of you here been to a parking garage, like down at SeaTac Airport or Bellevue Square, or, you know, and I don't know about you, and I'm, again, not the smartest guy, but normally I want to park at like the first level like I find a space at. So what I'll do is I'll go to the first level and I'll drive around, and if I can't find a parking space, where do I go? Up to the next level, okay? And then I drive around, and if I can't find a space there, where do I go? The next level, and I keep doing that. This is how shells are filled in atomic structure. When the first shell gets filled, then electrons start going out to the second shell, and then the next shell, and then the next shell. So our most complex atoms in existence have electrons in shells that are way out there because they have the highest number of electrons. And the higher the number of electrons, the higher the number of protons, because remember, they have to be equal. Make sense? Now, the shell that should most concern you is this valence shell. This is the outermost shell. If it's a complex atom, it may be way out there. If it's a simple atom, it's going to be real close to the nucleus. And I'll talk to you in a minute why it's important for two different reasons. The number of electrons contained in the valence shell also refers to the term valence. Now, this is the scheme that they came up with in naming the shells. If we have a simple atom, let's say we've got an atom that contains one electron. That one electron is going to be parked in the lowest level. And we're not going to call it the lowest level. No, that'd be too easy. We're not going to park it in what's called the first shell because that would be too easy. You're here to attend college, okay, to get educated. So we've got to not call this the first shell or the A shell. We're going to call this innermost shell the K shell. Why? I don't know. It helps us educated people justify our existence. After the K shell comes this is the part that actually makes sense to me. After K comes L, M, N, O, P, Q. So I did okay with the alphabet. So it kind of makes sense. So what this means is the Q shell, the most complex element that we have found in the universe, contains electrons in the Q shell. Does that make sense? If it's a simpler element, an element with a lower atomic number, that means it's going to have electrons maybe only in some of these shells. But we have to fill a sequence first, fill this K shell, before we bump an electron up into the L shell, when L gets filled. And some of you that have maybe taken chemistry and some physics classes know there's a certain number. I don't want you to memorize that. That's not going to help you become an electronics professional. But just remember there is a limit of how many electrons you could park in a shell before the electrons have to go into the outer shell. Now, why am I talking to you about all of this stuff? Again, this was a question that plagued me for about 3 years since I was educated. Like, why were they teaching me about all the subatomic stuff? I'm not going to be some mad scientist, you know. Why do I need to know about the periodic table? Why do I need to know about subatomic structure? You know, I want to learn how to use a multimeter to take voltage readings. I want to know how to use an oscilloscope to take readings. Why do I have to understand subatomic structure? 2 reasons you need to understand subatomic structure. Number one is so you could identify the properties of materials that we use in electronics. That's first and foremost. Secondly, you need to understand where voltage comes from. And we're going to talk about that in a minute. First, let's talk about some of these materials and their properties. Conductors. How many of you are familiar with conductors? Conductors. That's the guy that runs the train, right? Is that the conductor? I actually saw that the other night. What's that movie? Unstoppable? How many of you have seen the movie Unstoppable? Train. It was actually a pretty good movie. You haven't seen that one? Yeah, it was good, wasn't it? Train, running out of control. Based on true stories. It was based on a true story, you know. Let's set the throttle and jump off the train and switch the track and jump back on it. You know, it just didn't work out very well. Anyway, well, that's not even what we're talking about. Conductors, and we're not talking about train conductors. We're talking about conductors, electrical conductors. Materials that readily accept the flow of electrons, or electricity, if you will. Categorically, the textbook says they're materials that contain a large number of free electrons. However, I want you to think of it in a different way. When I speak of conductors, I am speaking of materials that have 3 or fewer electrons in the valence shell. And by the way, in this class, in this program, the only shell that you will ever work with, for safety reasons, is the valence shell. If you plan to experiment beyond the valence shell, again, let me know, and I'll probably stay home that day. Okay? So it's only the valence shell. So if you've got an element that has 3 or fewer electrons in the valence shell, it's going to potentially be a good conductor. Now, in order of precedence, the material that has the best conductivity or conductance is that of silver. Silver, believe it or not, that's the best found in nature. Out of all the elements, silver is the best. Followed by copper, gold, aluminum, tungsten, iron, nichrome. Okay? Silver is the best. If silver is the best, why when you buy a stereo, why when you buy audio-video equipment, do they try to sell you gold-plated patch cords? Okay, we've got one response there, money, yeah. They can get more money out of you.
It's corrosion. Silver has a higher corrosive potential than gold.
Absolutely. Absolutely.
And copper is a little bit more corrosive than gold, but not as much as silver.
So basically, gold is the least likely to oxidize and corrode. So when we get copper wire and plate it with gold, we get a good conductor, because gold is still a good conductor, but it won't oxidize. If you're scuba diving in the Caribbean and you find a treasure chest full of gold that's been sunken hundreds of years underwater, and you dig it out of the sand and you open it up, underwater, salt water, hundreds of years, you open it up, you would know that you found gold, because it would look as good as the day that that treasure chest fell off the pirate ship. If you found a treasure chest under the ocean in the Caribbean, and it was filled with silver, and you pried it open, you'd be like, oh, what happened in there? Because it's all oxidized. Of course, there's still good silver in there, but the exterior would be oxidized. So that is why we use gold-plated connectors. Don't oxidize. We live in an oxygen-rich environment. So if I could have gold-plated connector to connector and I could mate the two, I'm going to get the best possible electrical connection that I can. Now, do you really need to go out and buy those gold-plated audio-video connectors? It's actually kind of funny because I've seen a lot of people go out and spend good money on those, and then they plug it into the back of a dusty amplifier. You know, it would have been better for you to go out and get some technical grade alcohol, clean the male-female connectors, you know, connect them, and you'd get a better electrical connection. Now, in a perfect world, a totally clean gold to totally clean gold, clean, nice, no dust, is going to give you a superior connection. We actually learned a lot of this was developed in the space program. Because think about it, to basically send people to the moon and have them get back and have those electronic circuits work, needed to be highly reliable. So this is where NASA started playing around with everything is interconnected. You can't permanently wire everything up. You have to have boards and sockets, and everything is interconnected like that. So NASA did a lot of research, and they said, hey, we plate the stuff with gold. We'll be golden, you know. Literally, that started that whole trend in electronics. A lot of the circuit boards and stuff that you buy, your computer motherboard, you know, your video card have gold plating on it, so they make that connection, and it's a highly reliable connection. Big thing I want you to remember though, 3 or fewer electrons in a valence shell. Insulators are materials that prevent the flow of electricity. The textbook says they're stabilized by absorbing valence electrons. The material found on planet Earth that has the highest insulative quality in nature is mica. Any of you know what mica is? It's found in rock formations. It's very fragile. It's a good thermal insulator, and it's a good electrical insulator. A lot of times it's found in quartz formations. And it's almost like paper, like you can kind of peel. There's one layer and another layer and another layer, but it's highly fragile. That, for thickness, is the best insulator that we have found in nature. That's why it's at the top of the list. That's what we compare everything to. Glass is high, but not as high as mica, followed by Teflon, paper, wax paper, which is used in the manufacturing of some electronic components. Rubber, Bakelite. You know what Bakelite is? Bakelite is like the handle on your toaster oven, and like when you drop it, it chips it and you can't glue it back together. It's not only a good electrical insulator, it's a good thermal insulator. It's that black stuff that, again, you chip on your pots and pans and you can't fix.
Isn't that the original form of plastic? They started now.
Yes. Yeah, it is one of the original forms of plastic, if you will, that they used as a composite, if you will. Oils, a lot of oils are used. They used to use a lot of oils that had a lot of poison in them for like electrical transformers, but we kind of got out of that because oil is an insulator. And it's nice because oil will draw heat away from circuits. So if you had a circuit submerged in oil, if any what do you call them, computer heads here, PC files, you know, one of the big problems we know with PCs are heat, the generation of heat in the processing. So one of the big things is if you could super cool a computer, you get more performance out of that computer. So if we got the computer, don't try it again with my computers, but if we got it and submerged it into a vat of oil and then we cooled the oil and recirculated it, we could draw more heat away from the circuit, and then we could start bumping up the speed of the computer and in the industry overdrive the chip. Ask more of the chip than what it's rated for. Yep. Porcelain. And of course air. Air is an insulator, isn't it? If you've driven under power lines, what's between the power lines? Air. I don't know if you've ever driven under or walked. You do some walking, hiking under the BPA power lines down south. And on a day that's damp, you could actually hear the bzzz. It's like, wow. Air is the insulator, and I guess it ain't working too good right now. Hope it doesn't arc to me. There's also a category of materials that are called semiconductors. Semiconductors are materials that can be altered to function as either a conductor or an insulator. Let me go back. I left out one thing here. Insulators are materials that have 5 or more electrons in the valence shell. 5 or more electrons in the valence shell. So conductors were 3 or fewer. Insulators, 5 or more. Anybody want to take a wild guess what a semiconductor might be? One that could be altered the function as either a conductor or an insulator. Do you want to take a wild guess? 4. You all could have been scientists back in the 1940s. Because that's basically what they came to the conclusion. We know the properties of conductors. We know the properties of insulators. What happens if we start playing around with something that has 4 electrons in the valence shell? We could get it maybe to swing both ways, depending on how we want it to behave at that moment in time. And as you know, semiconductors are the fundamental building block of diodes and transistors. Transistors are the fundamental building block of computer microprocessors. That's all a microprocessor is. Now, in essence, billions of transistors on something the size of a postage stamp. Made of materials that have 4 electrons in the valence shell. Those materials that you're going to study later on in the program, not real important now for you to know, but I think you'll recognize one of the names. Germanium. That's not geraniums, that's what grows in the gardens. Germanium, it's an element. Carbon, that's an element. And the most prevalent, silicon. Silicon Valley. You've all heard of Silicon Valley? Have any of you know where Silicon Valley is? Have you ever been there? Vast mountains of silicon everywhere. No, it's fabrication facilities, labs. Okay? You're talking about in the Bay Area. Make sense? And what they did is they harnessed the power of semiconductors and made transformers, or transistors, excuse me, not transformers. It's another line. Trust me, we'll enjoy that lecture when we get to it. The other big thing I want to address with you is negative ion, positive ion. Because in essence, this is where voltage comes from. This is where voltage comes from. If I get this calculator here on the desktop, it's just been sitting on the desktop all day. It's just your average everyday calculator. I assume that since it was sitting on the desktop, minding its own business, it's electrically in a neutral, natural state. Because this calculator is made up of matter, which is made up of elements. Sitting here, neutral, natural state. So if I get this now, and I start rubbing it, what effect do you think that's going to have on the calculator? I'm cleaning it. No, it's a different class. That program's down the hall. Go out the double doors.
Creates friction.
Static electricity causes friction. The friction does what?
Creates charge.
How? And why?
Through the resistance of the fabric going across the plastic.
Close.
Somehow.
Close, kind of.
The difference of electrical potential in that you're rubbing that cloth on the plastic calculator, which creates charge on there,
Mm-hmm.
and then when you touch it, you have less charge and no shock.
Yep, that's pretty good. It's pretty good. In essence, by me rubbing this and applying friction, which is a form of energy, when I apply energy to matter and I rub this, there's a pretty good chance that I am going to knock some subatomic particles. Which ones? Electrons off of what shell? Valence shell. If I rub this so hard that smoke starts coming out of it and it bursts into flames, chances are I've gone in too far. But if I just rub the valence shells and I knock some of those electrons from this onto this, now we've got a disparity. Now no longer, if I've removed electrons from something that was neutral natural and I've taken electrons from it, what is the predominant positive? Why?
Because electrons are negatively charged, taking them away leaves you with a positive charge.
Exactly. Now I'm left with more protons on this than I have electrons. It wasn't a neutral natural state, so I started rubbing it. Okay? So that's exactly what I've done. So I just made this a positive ion. I just made this a positive ion by removing electrons from it. If this was also in a neutral natural state till I started monkeying with it, now I rubbed electrons from the calculator onto the cloth. What does this mean for the cloth? It's now negatively charged. Why is that? Because it contains more electrons than it had when it was in its neutral natural state. Now you know what? When I do this, both of these items, I don't want to make it sound like they have consciousness or whatever, but their whole freaking goal in life now is to get back into a neutral natural state. They cannot wait until I put them together and the electrons could jump off the cloth back onto the calculator and they could be at rest in a neutral natural state in a perfect world. Does that make sense? What I just shared with you is how we generate electricity. That's how we generate electricity. In order for us to generate electricity, we must apply energy to matter. When we apply enough energy to matter, we could knock electrons off the valence shell, gather them, and then say, hey, what? You want to get back to the you want to get back to the positive? Have I got a deal for you? Come, travel through my circuit, make this light bulb illuminate, and I'll give you a complete path back to your neutral natural state. That's what we end up doing as a career, making sure electrons that were harnessed are ready, able, and willing to do work for us, and then we make sure that they follow the correct path and do something for us. We just don't let them complete the path. If you're just letting them complete the path, that's called a short circuit. Okay? That's not a good thing. We'll talk more about that in future chapters. We just want to make sure that the electrons follow the path and complete that path. Make sense? Very critical. Talked about two big things already. The properties of materials we use in electronics, and also the property of how we create voltage or electricity. There's one other thing here the book does not go into. We have conductors, we have insulators, we have semiconductors. There's a fourth property that's floating around out there in science right now. Does anybody know what property I'm talking about? Superconductor. Superconductor, very good. Very good. A superconductor, all of these materials, whether you're a conductor, whether you're an insulator, whether you're a semiconductor, you have one property associated with you. Everything has that property associated with it. It's a property of resistance. We're going to talk about it in a bit. There is a material that exists. It's called a superconductor. It has no resistance. The problem is, does anybody know where it exists? It is at low temperatures. So therefore, where it's going to exist is in a laboratory. They don't have it operating at room temperature. I can't bring you next door and give you a tour of my superconductor that I have set up over on a bench over here. Okay? I could if I had a cryogenics plant and I was, research facility and playing around with it. But when they harness superconductivity, it's really going to rewrite the textbooks on how we manage electricity and electronics. Okay? You think Bill Gates got a lot of money? The dude that captures and harnesses superconductivity at room temperature is going to be very, very wealthy. Very, very wealthy. Make sense? By the way, does anybody know what material they're having the best luck with as it pertains to superconductivity?
Graphene.
What's that?
Graphene.
Graphene, they're doing some stuff with that. But that's not the best results yet. Believe it or not, it is ceramic. Ceramic at room temperature is an insulator. It's a great insulator. We use it as an electrical insulator. But when they bring these ceramics to really, really cold extreme temperatures, they take on conductive properties and they conduct with no resistance. Pretty cool. Ionization, that's the process I just described. It's the process of gaining and losing electrons, and it's significant in current flow. Okay, without ionization, you wouldn't have voltage. Without voltage, you would not have current flow. Current, again, we should ring bells. Current is the movement of electrons from negatively charged atoms to positively charged atoms. The letter that we use to abbreviate current with is the capital letter I. Capital letter I. One of the terms we need to familiarize ourselves with when dealing with these electrical properties is the term coulomb. We'll talk more about the coulomb next chapter, but what a coulomb is 6.24 times 10 to the 18th electrons. This is a big, huge number. This is basically 6.24 and 16 zeros after that 4. It's too big to fit in your calculator. That's why we refer to it in this as an engineering notation. We'll talk more about engineering notation again in future chapters because we got to get you used to dealing with these extreme numbers. In electronics, we deal with a lot of extreme numbers. And we represent it with the capital letter C. Now, an ampere, named after André Marie Ampere, French physicist, 1 coulomb, that big number of electrons, 6.24 with 16 zeros after it, that number of electrons moving past a single point in 1 second is called the ampere. Have you all familiar with the term ampere before? If you've ever burnt out a fuse, you make sure you get the fuse that's the proper ampere rating. If you pop your circuit breaker, you need to make sure when you're resetting it that you're not overloading the circuit and exceeding the amperage rating of the circuit. And what that is physically a given number of electrons that you're forcing through a conductor in 1 second's time. 1 coulomb per second is 1 ampere. 15 coulombs per second is 15 amperes. We'll talk again more next chapter on that. Current's measured in amperes and it's represented by the capital letter A. So if you go out to your fuse box in your car, pull a fuse out, it says 15A next to it. That stands for 15 amps. Universally accepted. Universally accepted. Potential, the ability of a source to perform electrical work. What we're talking about here with potential is voltage. Difference in potential causes electrons to move or flow in a circuit. This is referred to as EMF or electromotive force or voltage. EMF, electromotive force, voltage, difference in potential, they're all synonymous. Voltage, ring bells, chimes, hit the gong, is the force that moves electrons in the circuit. It's the pressure or pump that moves electrons, represented by the capital letter E or the capital letter V. Whether you use E or V, here the textbook uses E, you could use V if you want, as long as you know what we're talking about. It's universally accepted. The unit of measure is called the volt. Resistance, the opposition to the flow of electrons. The degree of resistance depends on size, shape, and temperature, and it's measured in ohms. Named after George Simon Ohm, represented by the Greek letter omega. One of the things I want you to familiarize yourself with is, you know what has resistance? Everything. Everything except superconductors. And superconductors only exist in a laboratory right now. Hopefully when you buy an extension cord, that extension cord has a low amount of resistance. Okay? Hopefully when you buy new spark plug wires for your car and they're insulated, hopefully the outside of the spark plug wires has a high amount of resistance. Make sense? Conductors have low resistance to current flow. That's why they're called conductors. They have many free electrons to transfer the energy. Insulators have high resistance to current flow, very few electrons. In summary, tonight we talked about matter, we talked about elements, the fundamental building block in nature, we talked about atomic structure, specifically subatomic particles and a place. Right? Nucleus is not a particle, it's a place. Which that place contains the protons, the neutrons, and the electrons. Protons are positively charged, neutrons are neutrally charged, and electrons, well, those are the other ones, they're negatively charged. We talked about atomic number of protons in an atom, atomic weight, number of protons, and number of neutrons in an atom. We talked about shell. These are the orbital arrangements of the electrons, starting with the K shell, going all the way up to the Q shell. We talked about ionization, the process of taking things out of a neutral natural state. We talked about current. Current is the flow of electrons from negative to positive. Why? Because it wants to get back into a neutral natural state. We talked about the Coulomb, 6.24 times 10 to the 18th electrons. It's a number of electrons, like a dozen eggs, a bushel of apples, a gallon of gasoline. We talked about the ampere. The ampere is 1 coulomb per second. We talked about electric current that is measured in the ampere. And then finally we talked about potential or electromotive force. What we're talking about there is difference in potential or voltage. Does anybody have any questions on anything that I covered in lecture for chapter 1? Going once. Going twice.
This will be on the website there, right?
What's that?
This will be on the website, right?
Yes, these slides are on the website. The audio recording is on the website, and eventually we're going to get the video uploaded as well. But the content will remain the same.
Yes. It'll be the new Google site.
New Google site. Any other questions? Going once, going twice, going. The new Google site, the last one that's listed there, the HTTPS, sites google.com, site LWTC Electronics. I've got that turned on to anybody with the address should be able to get in there. We haven't uploaded this material to it yet, but should be there.
Take the S off for it to work, don't you?
Really?
Yeah, because I think the S means that there's somebody with administrator access logged in on a secure connection.
So like messed up? Is that what you're saying?
Yeah.
All right, I messed up.
I think so.
Cool.
I don't have scientific evidence.
Cool. That's why you got the job as TA. You're here to keep me honest. Any other questions? Once, twice?
I should know where lead falls in that conductivity.
I honestly don't know. I mean, it's pretty far down. It is a conductor, of course.
I think it's amazingly good.
It's real close on a periodic table. It's amazingly close to silver.
Yeah.
It is good, but it
Oh, yeah.
And that's why actually in solder, we used to contain lead, but because lead is lead and it's bad, they realized it was really, really bad, so we pulled it out of solder, but it was used to join in complete electrical circuits, so it's pretty high. I don't know its actual conductivity value, but it's pretty high. Going once, going twice, going, gone. We're black. The next questions that I have for ELEC 110, Chapter 1, you'll be answering for me on a quiz. But don't worry, well, you'll have another week or so before we take the quiz. I'll coordinate with the class lead on that. Any other questions about protocol, anything else we're doing here? All right, I'm going to go ahead and cut you loose. Okay, last week, wrapping up lecture, we're talking about electrical insulators. We're talking about conductors, things of this nature, right? I dug out of my archives here. Remember I talked to you about mica? Mica? I found my stash, my private stash of mica. Please be very careful passing this around. It actually kind of flakes off, so you can just handle it, look at it. This is found in nature, it's found in rock formations, and this is the best insulator found in nature. This is a washer, an insulator washer that's been made out of mica. Okay, so we'll pass these things around so you can see, but these are very fragile. Don't try to bend it, you'll break it. It's almost like a real thin piece of glass, if you will. So this is mica in the raw, and this is a processed piece that could be used as an electrical insulator. So cool stuff. So anybody have any questions on anything else before we get started here? Chapter chapter number 2. Okay, just to get us kind of ramped up from where we left off last week, we really started our discussions last week talking about the fundamental properties of electricity. And that discussion really started off with a discussion about matter. Matter is everything. If there is no matter, the absence of matter is called space. We could recreate the absence of matter here on planet Earth by using an industrial vacuum chamber. That's where we pump all the gases out of the chamber and we're left with nothing inside. Industrial vacuum is used a lot in industry, in the manufacturing process, so that they can remove everything from it and only introduce those materials that they want to be inside the chamber. Remember that discussion? Okay. The next thing we talked about, which is very, very critical, are the properties, the fundamental physics properties, if you will, of materials that are used in electrical and electronics applications. The most popular that we talked about is the conductor. The conductor is a material that has 3 or fewer valence electrons in the valence shell. Okay? That means there's basically, we talked about it like a parking garage. There's room for electrons to park in this valence shell. Therefore, it's going to make it a good conductor. Materials that have 5 or more electrons in the valence shell are good insulators, like that piece of mica that we're passing around right now. If you looked at that, you'd see, again, more than 5 electrons in the valence shell. That means if you're a free electron, you're not going to have any place to park on that piece of mica. We also talked about semiconductor materials. Those are materials that have 4 electrons in the valence shell. And for those of you that continue on in this program, ELEC 120, that's right where we're going to pick up the discussion, back to fundamental properties of physics as it pertains to materials. If any of you were in the classroom the other night, last week, I gave that lecture to ELEC 120, and we were talking about these fundamental properties, subatomic structure, because that discussion was all about solid state materials, silicon, germanium, that we use in the manufacturing of transistors and integrated circuits. The other big thing we talked about is, in essence, the beginning, the creation of electricity. When we have matter and we impart energy on matter, we could knock an electron off that valence shell. When we knock an electron off that valence shell, we end up with what's known as a positive ion. A positive ion. Because remember, in nature, matter is typically in a neutral state. That means it has an equal number of protons and an equal number of electrons. Remember that? That's how we end up with the atomic weight. Atomic weight or atomic number?
Number.
Which one is it? A is weight, B is number on the quiz. C is both. D is none of the above. Which one's it going to be? The number of protons is number. Okay? So that number, whatever number of protons we have, we also have the same number of electrons. That's what puts it in a neutral natural state. So when I impart energy on matter and I knock an electron off, now I have more protons that have a positive charge than I have electrons in the atom. That makes it a positive ion. In essence, what I just did is created electricity. That's what electricity is. Electricity is us applying energy to matter, knocking an electron off, gathering those electrons, and then saying, hey, electrons, have I got a deal for you? You want to get back to your parent atom and get it into a neutral natural state? Come this way. Go through this circuit. Do a little bit of work for me, and then I'll give you a path back to neutrality. And the electrons, they do this. So part of your careers in the electronics industry is going to be simply managing the behavior of electrons, making sure the electrons do what they're supposed to do. I guess that's why they call this electronics, right? Electronics, the study of the behavior of the electron. That's what this is all about. The other thing we talked about last week briefly was the coulomb, a unit of measure, right? A coulomb is like a gallon of gas, a dozen eggs, a bushel of apples. A coulomb is 6.24 times 10 to the 18th electrons. It's a big, huge Herkin number, right, of electrons. There was a guy by the name of Charles de Coulomb. He was counting electrons for a living, and then he died, you know? And then they said, hey, anybody here want to continue on Chuck's work? Anyone? Anyone? All right, we'll just call it even. We'll call, you know, the number that he came up with, 6.24 times 10 to the 18th, we'll call that a coulomb. 1 coulomb per second is the ampere. That was put together by a guy by the name of Charles Ampere? No, Andre Ampere, another Frenchman, or Beret. Andre Marie Ampere. And you know what? Universally, that's accepted. See, the amazing thing, I enjoy travel all around the world. People speak different languages. We use different coins, different monetary values. When it comes to current, worldwide, the ampere is the accepted value that we use, no matter where you go. So, those of you that are learning, if you have English as a second language and you struggle with this, we're all learning a new language. It's the language of electronics. And the word we're going to study tonight is current. Current. And you already know kind of a little bit about current based on our lecture last week. Well, we're going to pull back the curtains and study a little bit more tonight. After completing this chapter, you're going to be able to state 2 laws of electrostatic charges. I'm going to give you a heads up. Anytime you see the word law, you should like sit up straight and like take note. Because if it's a law, the type of laws we're talking about here are not laws that we could go to Olympia and have repealed. Okay? They're not talking about laws that we could go to the Supreme Court and have overturned. That actually would be kind of fun, wouldn't it? Go to Washington, D.C. Students from Lake Washington Technical College in Kirkland, Washington protested today outside the Capitol to have the laws of physics repealed. We can't. These are laws of physics, okay? So these electrostatic charge laws are kind of critical. We're going to be able to define coulomb, identify the unit used to measure current flow, define the relationship of amps, coulombs, and time through formula. Describe how current flows in a circuit. Describe how electrons travel in a conductor. Define and use scientific notation. And identify commonly used prefixes for powers of 10. Some of you may be familiar with this law. You've probably heard it before. The first law of electrostatic charges are like charges repel each other. Have all of you heard that one before? Okay. The other thing that you're probably familiar with is like opposites attract. Right? Opposites attract, and that's not only in relationships, that's actually the laws of electrostatic charges. Opposites attract is actually the second law of electrostatic charges. So if I got a negative and a negative, they're going to oppose each other. If I have a positive and a positive, they're going to oppose each other. If I got a negative and a positive, pow, they're going to be attracted to each other.
Same concept with magnets.
Yep, very similar. That's not electrostatic, that's magnetism. It's a different property, but the same thing. North is going to be attracted to south. You got 2 north poles, they're not going to be attracted. They're actually going to push back on each other. 2 south poles, the same thing. So we're actually going to study that in future chapters. But this is the law of electrostatic, not electromagnetic. So just keep those 2 separate. Coulomb. Coulomb is the unit adopted for measuring charges. In last week in lecture, I gave you the number 6.24 times 10 to the 18th. I figure I'd wait a week before I actually showed you what that number looks like. I mean, it's one thing for me to say up on the board it's 6.24 and then 16 zeros after, but this is really what the number looks like. Okay? It's really what the number looks like. One of the reasons that we need to use this form of notation is that this number right here will not fit in your calculator. It won't fit in your calculator unless you enter it in this form. And I'll show you. By the end of the lecture, I'll show you to make sure you know how to enter it in that form. It's kind of funny because if you had your neighbor down the street or whatever, and you found out that they were going to college in an accounting program, right? If they're going to go to school to become an accountant, you'd probably say, wow, that person must be really good with numbers, okay? Tell you what, if you're Bill Gates' accountant, you're not dealing with a number like this, okay? But yet, regularly, on a daily basis in the study of electronics, we're going to be dealing with numbers like this. So, if you're struggling with this form of notation, we'll work with you. But don't be like me. When I was in school initially like this, I looked at this number and I looked at this stuff and, man, I don't know, that's too complex. It's like, 6.24 times 10 to the 18th. That's a number like Mr. Spock would use or something on a Starship Enterprise. And I'm a more down-to-earth guy, so I'm going to keep it basic, And in very short order, I realized you can't keep it basic in electronics because we're going to be dealing with these extreme numbers. So we have to use this form of notation. So you see how we came up with this 6.24 times 10 to the 18th? The decimal point here means there's 18 places past it. So if we went ahead and actually counted here, right, that's like us moving the decimal place from here all the way up to here. So if we went ahead and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 6.24 times 10 to the 18th. That means there's 18 places past the decimal point. In this particular case, since I have 0.24, that means there's going to be 16 zeros after it, right? 16, 17, 18. 16 zeros after that. Does that make sense? Everybody see how I did that? All right. There's our first law of electrostatic charges, negative and a negative, positive and a positive, negative and a positive, Because remember, in the beginning, everything was in a neutral natural state anyway, right? So originally, everything was like harmonious, balanced. When we apply energy to matter, we knock an electron off that valence shell. And all is that valence shell, that electron that we knocked off has in mind is getting back and putting that atom in a neutral natural state. So if you put an electron in the same room with a positive ion, they're going to seek each other out. They want to achieve balance and harmony. Make sense? Current. And every time I use this word here, we should like ring bells, chimes, hit a gong, something like that, because this is like a holy word in electronics. There's 4 properties that you really need to be infatuated with. And when I say infatuated with, I'm not talking about just as a student. I'm talking about later on when you continue on with your career. The worst day you have in this industry as a paid electronics professional, the problem will be solved by understanding and knowing the behavior of voltage, current, resistance, and power, period. Do I sound like I'm oversimplifying it? I'm not. It gets that basic. If they've got an electrical problem with the space shuttle and they can't hit the button and have it blast off, it's because voltage, current, resistance, or power isn't doing what it's supposed to be doing. So if you know everything about those 4 parameters on the space shuttle, you could get in and look at those 4 parameters and quickly find where the problem is. So today we're talking about current. We should ring bells, hit chimes, hit a gong or something, because current is one of the big 4 properties. Now the textbook talks about current as being the drift of electrons from an area of negative charge to an area of positive charge. I don't like this definition, the drift of electrons. Makes it look like I'm an electron and I'm drifting, I'm floating, okay? An electron is more like if I'm negative charge and there's like positive ions out in the freaking hall, I'm going to be like. I'm going to be trying to get over there. Why? Because I want to fill those holes. I want to fill the void that was created when energy was imparted on matter. Does that make sense? So that's really the behavior of current. As a matter of fact, that was kind of a mad dash. I bet you didn't think I had it in me, huh? It gets better than that. You know how quickly electrons are going to go over there if you could complete the path? At the speed of light. At the speed of light. If we allow electrons to complete the path, it's going to travel at the speed of light. So I don't call that the drift of electrons, negative to positive. Now, Andre Marie Ampere came up with this term that he called the ampere, named it after himself. These dudes didn't have egos. You kidding? They didn't have egos. Andre Marie Ampere invented a unit of measure called the Smith. No, the ampere. The ampere is the amount of current in a conductor when 1 coulomb of charge moves past a point in 1 second. This is kind of emotional. This is your first real formula. It's your first real formula. The relationship between amperes and coulombs per second can be expressed as I, which is current, is equal to Q, charge measured in coulombs, divided by T, time measured in seconds. So what we're saying here is 1 amp or ampere is equal to 1 coulomb per second. Now be careful with this, because I could ask you a question about number of electrons. Is number of electrons coulombs? Number of electrons is number of electrons. Coulomb is 6.24 times 10 to the 18th electrons. So this formula only works if you're using coulombs. What happens if I have half a coulomb per second? It's not a trick question. If I have half a coulomb per second, what's my current going to be? Half an amp. If I have quarter a coulomb per second, what's it going to be? Quarter of an amp. If I have 2 coulombs per second, this is a trick question. No, just kidding. 2 coulombs per second. That means I'm going to have 2 amps. So typically for household current in your home, we talked about this last week. What was that number? What's your typical utility connection from the power company to your home? That's the voltage. What's a typical box?
Oh, 200 to 250.
Typically about 200 amps is a typical residential connection. You know, you buy a home, you're going to see that it's typically 200 amp connection from the power pole, or if you have underground service, to your box, that big gray box that's in your house, 200 amps. Okay? From that box, the circuits in your home get distributed to circuits that are typically either 15 amps or in some cases 20 amps. And for some of your appliances, you know, they'll be a little bit higher in some cases if you have an electric hot water heater or things like that. I've got a hot tub. Okay, it requires more than 15 amps, more than 20 amps. So I've got a high current connection going to that. So if you've got 15 amp outlet in your home, that means that outlet is capable of handling how many coulombs per second? 15. 15. I could also ask you how many electrons per second can that handle? Then you'd have to get 6.24 times 10 to the 18th times 15, and that's how many electrons it would be physically that's capable of supporting. That's why it's so critical that all of these components, when they're manufactured and they're given their specifications, that you don't exceed those specifications. Because if you try fitting more electrons through than it's physically capable of handling, you're going to start an electrical fire. Okay, so everything has ratings associated with it, current ratings, and this is why. Physically, it can't handle any more electrons. If you try pumping, you know, if you got a garden hose and connected it to a fire engine, okay, and turn the pumps on high, what do you think is going to happen to that garden hose? It's probably going to blow up. It's probably going to explode, right? It can't handle that volume. That's why firemen have like big hoses, okay? Because they have a higher volume of water that they try to put, you know, from the truck onto the fire. That's why they're firefighters, fire people. Make sense? The other thing I want to share with you about formulas, okay? If there's shortcuts that I could teach you and you could remember, I'm all about that. This is college, so whenever I give you a formula, I'm just going to give you this formula and assume that all of you are like college students that have paid your dues and are here for the right reasons. So I'm not going to show you every possible variation of the formula. I'm going to expect you to know how to do it on your own. But I don't expect you to know how to do it on your own because all of you don't have a comprehensive algebra background yet. So I'm going to show you a couple shortcuts here, a way to cheat. What I want you to do is start off with drawing a triangle. I want you to draw a simple triangle. Then inside the triangle, I want you to draw a T. The one formula that you know, I want you to plug into this triangle. So I, in this particular case, I is equal to Q over T. Does everybody see how I did that? I is equal to Q divided by T. So that's the first formula that I gave you. I is equal to Q over T. Now on a quiz or an exam, or simply when you're hanging out together working with each other in the lab, what happens if I gave you coulombs and I gave you current? Then what we could do is simply cover up the letter T and say T is equal to Q over I. So I did that. So T is equal to Q over I. That's the other algebraic manipulation of this. If I asked you on a quiz, if I gave you current and I gave you time, and I wanted you to figure out how many coulombs, what the value of coulombs would be, then we simply cover up the Q, and then it's going to be I times T. See, the I is next to the T, so it's going to be I times T. So that's going to be our other variation. Q is equal to I times T. So with that one formula that I gave you, there's three basic algebraic manipulations that we could have, and this is all of them. So do you have to memorize these? No. Remember, do the triangle, put the T in the center, and then lay that one formula out. And then now you have all the algebraic variations of that formula. And you know what? You need to know how to do this, because I could ask you, I'll be honest with you, everything right now is fair game. I could ask you to solve for current. You should be able to do it. I could ask you to solve for time. You should be able to do it. I should ask you to be able to solve for coulombs, and you should be able to do it. I should be able to give you a number of electrons, right? You have 30 gazillion electrons. How many coulombs is that? That gives you this value. Then you could figure out the rest. Does that make sense? So it's a stepping stone. But don't get hung up on what you don't know. Focus always on what you do know. And the one thing to remember is 1 amp is 1 coulomb per second. I is equal to Q over T. And then if lay that out, gives you all the other variations. Make sense? Is that right? Hole. An all-female progressive rock band from Seattle, Washington. Hole. That was a joke. Is Hole even still around? No? No? No. They're not. When did they disband? Where did they go? No. She's doing her own thing. Yeah, that's what I understand. She's doing her own thing. So reference, what Beavis and Butthead Do America, right? There's a reference to Hole. Not this hole, but the other hole. Remember they were, no seriously, they were going, remember Beavis and Butthead Do America? They're looking for their TV, or the TV broke and they stole one and whatever they're doing, but they were going to go to Washington, like DC, but when they heard about Washington, they were like, Washington, that's cool, that's like where Seattle is. We could go see Hole, you know? So, anyway. That's required viewing for all of you. Beavis and Butthead Do America. It's going to help you understand. Anyway, no, I'm talking about a different type of hole. Hole that I'm talking about here is the absence of an electron. If I have an atom and I apply energy to matter and I knock that electron loose, what do I leave behind? A hole. So a hole is nothing more than the absence of an electron. The reason I want to point this out to you is that here at Lake Washington Technical College, every other technical and community college in Washington State, in the country, the U.S. military, all branches of the U.S. military, technical schools, a lot of universities all embrace what we embrace, and that is electron flow. We call 1 amp 6.24 times 10 to the 18th electrons traveling per second. That's what we call 1 amp, right? Engineers, scientists embrace what's called hole flow. They think that the holes are flowing to get filled by the electrons. I don't want any of you to lose sleep over this. Whether 6.24 times 10 to the 18th electrons travel in that direction per second, that's an amp, or it's 6.24 times 10 to the 18th holes that travel in that direction per second, that's going to be an amp. But hole is the absence of the electron. And the reason I'm pointing this out to you is I know all of you this weekend, as soon as you get a little bit of time off, you're probably going to go to the library and pick up some electronic books, start reading. I don't want you to call me a liar. I don't want you to open up that book and say, hold on. This book shows that current flows positive to negative. That Joe Gryniuk over there at that Lake Washington, he doesn't know what he's talking about. He said that current flows negative to positive. Current does flow negative to positive. Electron flow. Current also flows positive to negative. Hole flow. Are any of you going to go home and lose sleep over this? Be honest with me. Okay, let me know, because I did. I honestly, when I was in school, I got the same lecture I'm giving you right now, and I'm like, oh no, I didn't raise my hand. But then I went home and I'm like scratching head. What the heck was he talking about? You know, and I like for months I freaking tried to analyze. It's not that difficult of a concept. You just got to hit the I believe button. Joe says 6.24 times 10 to the 18th electrons per second equals 1 amp. So be it. We do want to talk about hole briefly so you can differentiate between electron flow and hole flow, and also to prepare you for what you are about to receive in the future. Because again, if you sat in on my lecture last week on ELEC 120, guess what? We started talking about hole flow again, because hole flow is significant in the study of semiconductor devices, solid state devices. If you want to understand how a transistor really works, you have to embrace hole flow. So we are going to talk about it more here at Lake Washington, but you don't need to beat yourself to death on it. Question?
Do holes have matter in them?
Well, you got to realize that the hole itself, no, is the absence. But if you're talking about matter that exists and it's the absence of the electron, then we're really talking about a positive ion. And a positive ion does have mass because you got all your protons, you got all your neutrons, and of course that's how we determine atomic weight. Very good. Answer A. Fill in the A. Atomic weight, number of protons and neutrons. So hole is the movement of an electron from one atom to the next, creating the appearance of a positive charge moving in the opposite direction. So that's what we call hole flow. If you had a piece of copper, which we know copper is a good, abundant conductor, this is kind of how the electron path, how it would work. Negative to positive, kind of copper atom, it would jump over here to copper atom, jump over here to copper atom. Make sense?
Drifting along.
Drifting along at the speed of light. This here we see, again, a conductor. We've got electron flow left to right, current flow left to right, hole flow right to left. Make sense? Okay. I want to show you something how this really works, because the way they're making this look, and I think you guys are all buying this, right? Because again, you kind of got to believe me, right? But this is kind of like the free electron is kind of like hopping from copper atom to copper atom because there's 3 or fewer electrons in a valence shell, right? It's kind of hopping along hopping along, there's another copper atom. You know, you ever jump across a stream, right? It's kind of what they make it look like here, right? Okay. Everybody at this table here, can you just back up here? Nobody has a coffee or anything on here, okay? Can you put your hand on the end of the table just like this, okay? Okay, let me know how quickly you feel this. That is how current flows through a conductor. That's how current flows through a conductor. The speed of light, instantaneous. Instantaneous. If I've got a negative here and I've got a positive there, pow, instantly that is going to be felt on the other side. That's how current flows through a conductor. So it's not this. Got to have your tongue out when you're doing it too, right? Doesn't work like that. It's instantaneous. The speed of light, which is important. 186,000 miles per second. The speed of light is 186,000 miles per second. Or for those of you in the metric system, 300 million meters per second. 300 million meters per second. Or for those of you that keep track of all things nautical, 161,000 nautical miles per second. And I got a couple chuckles out there. It's kind of like, well, Joe's ex-Navy, he would probably know that. No. I'll tell you what, if you know those three numbers, 186,000 miles per second, 300 million meters per second, 161,000 nautical miles per second, if you know those three numbers, you could probably get about 8 or 9 questions right on your FCC license exam. Because it's how RF energy transmits as well. If you're working on a radar, you want to get your radar endorsement to be able to work on a radar. The only radar in the world that I am familiar with that operates in statute miles is the radar that's operated by the police. If you're on a Washington State ferry and they're looking at a radar, that radar is calibrated for nautical miles. So all the math that takes place internal is 161,000 nautical miles per second. If you go to work for the Federal Aviation Administration and you work at Seattle TRACON that keeps track of all the aircraft arriving to Seattle and departing Seattle, the radar that they're looking at is calibrated in nautical miles. And the aircraft also travel speed-wise in knots. In knots, which is nautical miles calibration standard. Okay? So that's why those numbers are very important. That's how fast current travels. That's how fast radio frequency energy travels at the speed of light, or close to the speed of light. There's actually some atmospheric anomalies that kind of slow it up a little bit, but generally speaking, it's the speed of light, which is also important to realize. That's why it's so great you got me as an instructor, because you could learn from all of my goofy mistakes. Back when I was in the Navy, the only way that I could get a raise, the only way that I could increase rank, was obviously not getting in trouble for a period of time, which is actually another funny story. I'll share that one with you in a second. I forgot all about it. But anyway, the other thing is by taking professional examinations twice a year. And I remember one of the exams, you would have thought I would have been ramped up with this stuff. I got to this whole section of the exam once when I was trying to, go up in rank. And they started talking about the behavior of antennas in outer space. And I was like, I'm a submarine guy. I have no freaking clue how this antenna is going to behave in outer space. What the heck are they talking about? The Navy's got like people in outer space, and I just got myself into a tailspin, and I couldn't even answer anything instead of looking at the obvious. How do antennas behave in outer space? Perfectly. Theoretically, perfectly. That's what they were looking at. So I got all those questions wrong because I could they're talking about going to freaking outer space. I'm not going to outer space. I want to live beneath the sea. So, more on that, on keeping out of trouble. Can't make this stuff up. I was looking at a copy of my medical record. I have a copy of my military medical record at home, and I was looking through it. And I came upon a page. I got into a slight altercation. And actually, the medical record reveals 25-year-old Caucasian reported to sick call, reports being worked over by 2 bouncers. And then it goes into how I slept well and I woke up somewhat sore. And Basically, I reported the sick call, and it was I had my cheekbone got broken. And one eye was pointing one way and the other eye was pointing the other way. And finally they said, you got to go get that looked at. But right in there in print, reports being worked over by 2 bouncers. Called my son over. I said, check this out. It's kind of cool. I should have that framed, put that in my office, my medical record, But anyway, I was a good sailor. Voltage source. And again, we should almost ring bells, chimes, hit gongs when we're talking about voltage source. And I hope you don't think that I'm over-exaggerating this. These first few chapters of what we're talking about are the fundamentals. You have to understand this stuff 100%. Now, you need at least a 70% to pass this class. If I were truly the Pope of electronics, I'd say no. You don't move on to the next module, the next chapter, until you prove 100%, because this is how critical this information is. Voltage source, what we're talking about here is a power supply. It supplies electrons from one end of the conductor, and it removes electrons from the other end of the conductor. It can be thought of, for those of you that like using analogies, fluid systems, it could be like a pump. What does a pump do? It sucks from one end and pushes out from the other end, right? This is what a voltage source does. It basically supplies electrons from one end and then sucks them back from the other end. That has to be taking place or it's not a valid voltage source. So a battery is a voltage source. We're going to talk more about batteries in future chapters, right? It provides electrons on the negative end of the battery, and it collects those electrons on the positive end of the battery. That's what makes it a battery. That's what makes it a voltage source. And we need a viable voltage source in order for us to have a viable circuit. Now finally, we're going to talk about scientific notation, but we're not. Actually, what I want to talk to all of you about tonight is what's known as engineering notation. Anybody here really comfortable using scientific notation? If you're really comfortable using scientific notation, I guess you could keep using it, but I would encourage you instead to use engineering notation. The difference is scientific notation can be times 10 to the first power, second, third, fourth, fifth, sixth, seventh, it could be anything. You follow what I'm saying? Can you dig it? Engineering notation is always going to be in groups of 3. It's always going to be in groups of 3, which lends itself very well to what we're doing here in electronics. Let me show you. Let's start off with a decimal point. Oops, there it is. There's the decimal point. Okay? So if I put something to the left of the decimal point, this is going to be my base 10. This is going to be my ones column. So this number here could be anywhere from 0 to 9. If I get 9 and I add 1 to it, 9 plus 1 equals 10. So I've got to go to my tens column. So this is my tens column, this is my ones column. Can you dig it? This is the part that I did well in school too, the number line. Okay. If I get up to the number 99 and I add 1 to 99, now I increment to the hundreds column. Okay? So we're familiar, ones, tens, hundreds. Cool? Okay. So those are going to be my basic units of measure. This could be pounds, ounces, volts, amps, miles, whatever. Now, if I go here to my thousands column, 1,000 column, basically what I'm doing now is this is times 10 to the third. Times 10 to the third. Everything in here will be times 10 to the third. This could be 1 times 10 to the third, 22 times 10 to the third, 943 times 10 to the third. Make sense? The reason that I'm so infatuated with having you put it in engineering notation is by 10 to the third, we're going to call this value here in the metric system what? What's thousands in metric? Kilo. Very good. Kilo. So what we're going to do is we're going to call this, small letter k, kilo. So instead of saying 1,000, I'll say 1k. Instead of saying 943,000, I'll say 943 kilo. Kilo pounds, kilo ounces, kilo miles, kilo volts, kilo ohms. Make sense? Kilo miles. There's a new one for you.
So resistors expressed in K, meg, kilo, or that's all basically, it's scientific, or it's engineering notation.
Well, metrics, it's in metrics, but if you put it into engineering groups of three, then it's going to fit directly into those prefixes, those metric prefixes. So, 3 more places past the decimal point. 1, 2, 3. This is times 10 to the 6th. We're going to call this mega. Mega. And in actuality, it's like millions, right? 1 million, 10 millions, 100 millions. Mega. Ten to the 9th. What's that? Giga. Very good. Capital letter G. Giga. When I first got into this industry, I'm dating myself. I don't know why I say that. I make myself feel old. This is as far like as we had gone in the electronics industry. General Electronics. Giga. Wow. And I'll be honest with you. Where I used to work in electronic intelligence, the only people that could afford to play up here in giga values were superpowers. It was either us or the Soviets. And we knew what we had, so if I detected something that was in gigahertz, it had to be the Soviets. Okay? Now, giga, commonplace. After school today, you could probably stop at Fred Meyer, pick up a laptop computer that's got a, 80 gigabyte drive in it for $49. That's actually too much money. $49 you could get a times 10 to the 12th, tera. Tara also happens to be a barista down in Federal Way that's kind of got it going on, if you know what I mean. I don't even know what I mean. I don't even know what that is. Tara. When I first started teaching here 20 years ago at Lake Washington Technical College, boy, I can't even remember. I think I might have had like an 80 meg hard drive or something. I remember getting super jazzed by getting the Sunday Seattle Times, and I saw an ad in the paper that I could get like a 250 megabyte hard drive for less than $1 per megabyte. And I'm like, you gotta be kidding me. I could get less than $1 per megabyte of storage. I'm gonna go out and get one of those. So I went out and paid my $250 or whatever. Now you're getting a terabyte hard drive for $49. Now they have 2 terabyte hard drives they could get for $99. So this is, have I made my point about the numbers we're going to work with in high-tech industry? I mean, the numbers are extreme. They're extreme. So again, if you use engineering notation and put it into groups of 3, and most of you on your calculators have a mode that you could put it into engineering notation. So ultimately, the answer is going to be given to you in either times 10 to the 3rd, 10 to the 6th, 10 to the 9th, 10 to the 12th. If you don't know how to do that, you might want to look at your owner's manual. If you're already threw your owner's manual away, do a Google search on your model, and it'll come up with a PDF of it. Okay? You want to make sure you know how to access those modes in your calculator. Because, again, we're going to be using some extreme numbers. But you know what? I'm not done. I've yet to begin. We're about halfway done. We're also going to be dealing with numbers that are smaller than 1. So when I go back 1, 2, 3 places, anybody know what we call these? Times 10 to the negative third, 3 places to the right of the decimal place? Milli. And actually, if any of you come from a machining background or whatever, like thousandths of an inch, this would be a tenth of an inch, right? This would be hundredths of an inch. This would be thousandths of an inch. And you use the term mil, right? How thick is that plastic? 3 mil. 3 milli. Okay? So we're going to call this small letter m for milli. M-I-L-L-I, milli. 3 more places past the decimal point gives me times 10 to the negative 6th. Anybody know what we call this? Micro. Very good, micro. Micro is kind of weird too. It's a Greek symbol. Kind of looks like this. It's kind of like a backwards U. It's actually the Greek symbol called mu. Mu.
Dirty jobs too.
Dirty jobs?
Micro.
Really?
Micro.
He does that? Micro. For our friends at home, yeah, micro. He actually participated in a fundraiser here in the fall with Lake Washington Technical College via satellite. Actually, the producer from that show, Dirty Jobs, was here, and as a fundraiser for our college foundation. But Mike Rowe was live via satellite, speaking directly with all those that went to breakfast here at Lake Washington Technical College. I slept in that morning. I was hoping they were going to TiVo the event so I could watch it at my leisure, but nobody TiVo'd it. 3 more places past the decimal point times 10 to the negative 9th.
Nano.
Yep, nano, very good. Small letter n. Small letter n, nano. Any of you have heard about nanotechnology? This is kind of like where nanotechnology is playing around with now. 3 more places past the decimal point times 10 to the negative 12th.
Pico.
Pico, small letter p, pico. Suffice to say, I could go further. There's a couple places past this, but it's beyond the scope of what we're talking about right now. But as students at Lake Washington Technical College, you on a regular basis are going to be dealing with numbers times 10 to the negative 12th to times 10 to the positive 12th, sometimes in the same problem. So like I said earlier, even if you're Bill Gates' accountant, even if you're the IRS itself, anybody here not filed their taxes yet? 2 of us? 3? Be honest. 4? It's actually funny. I was with friends on Saturday. We stopped at Starbucks for a cup of coffee, and my friend saw this woman that she thought she recognized, that she knew, and you can't make this stuff up. It's like, she's like, you look like a good friend of mine, blah blah blah. And do you work for Quest? No, I don't work for Quest. Well, I work for the IRS. Really? Excuse me, ma'am, but you look lovely today. Can I buy you a pastry to go take a cup of coffee? Hey, you don't want to tick those people off. That's who finally brought down Al Capone, wasn't it? Right? The IRS. Anyway, we're going to be dealing with numbers like this, so we have to make sure we get it right. So in most of your calculators, you'll have a key EE, and you could enter that. Whatever you do, do not enter it as it appears here on the, don't go 3, hit the times key, 10 to the 3rd power. You're actually going to end up a decimal place off with that. You have to enter it, the EE key, exponential notation. Any questions on that? All right. There's no harm in using your imagination when you're dealing with an electrical system in equating it to a fluid system. Because let's be brutally honest, you can't see electricity coursing through wires. You can't see it. Our five senses are very, very limited. So sometimes analogies really, really help us out. So for those of you that understand fluid systems, it all rolls downhill and, pressure and pumps and that kind of stuff, you could use the same analogies to figure out what's taking place inside an electrical circuit. One of the things that I do, because I just love Seattle, is I'll use the Seattle freeway system to sometimes explain the behavior of current in a circuit. I-5, 405, 520, and we'll use those as analogies of how current behaves, how traffic behaves on a Friday before a 3-day holiday weekend, and it's sunny out and raining in the convergence zone. And we'll use those analogies to kind of figure out what's taking place in a circuit. So this analogy shows us the pump. This would act like our voltage source, right? It's sucking and then discharging, right? So this is our source of electrons, and this is where it's drawing the electrons through the pump. The current flows through the plumbing. The electrons flow through the circuit. The only thing that I would have done differently if I drew this illustration, I can't take credit for this, I simply pulled it out of the text, is the load. This would have been nice if they had like a water wheel right here. So as the water runs by, it turns the wheel, because that's what a load does. A load converts one form of energy to another form of energy. An electrical load converts electric energy into light energy, or electric energy into motion, or some other form. Does that make sense? So you can use this if you care to. Since this chapter is talking about current, typically in the study of electronics, not electrical, but electronics, we're typically only going to be using values associated with milli, times 10 to the negative third, milliamps, which, don't be fooled, milliamps could kill you. There's enough, even though it's thousandths of an amp, it's still enough to kill you. More than enough to kill you. And also we're going to be dealing with microamps. Typically, as a student here in the electronics program, Lake Washington Technical College. For those of you that go into the electrical trades at all, you're going to be dealing with amps. And lots of them. We had a student that just got hired by Bonneville Power Administration, BPA. He's going to be working substations. I don't even know how many amps you're dealing with at a substation. What makes a substation a substation? Lots of amps, I would imagine. Okay? I never had an interest in working with that many amps. Since milliamps could kill you, why would I want to work with more than enough to kill me? In summary, we talked about the laws of electrostatic charges. The first law is that like charges oppose each other. The second law is unlike charges attract each other. A coulomb is 6.24 times 10 to the 18th electrons. Electric current is the flow, not the drift, the flow of electrons in a specified direction. Measured in amps, conceived by the dude by the name of Andre Marie Ampere. And Andre Marie Ampere stated that 1 amp is equal to 1 coulomb per second. That's the relationship between current, electrical charge, and time formula. We talked about holes moving. Holes move in the opposite direction of electrons. Electrons travel negative to positive, holes travel positive to negative. We talked about scientific notation. Negative exponents, specifically milli, micro, nano, and pico. And we talked about positive exponents, specifically kilo, mega, giga, and tera. And tera also happens to be a in. That's kind of got it. Outstanding. If you know what I mean. I don't even know what I mean. We're going to talk about milli prefix. Typically, these are the values of current that we'll see in an electronic circuit. And also micro, times 10 to the negative 6. These are also values of current we'll typically see inside an electronic circuit. Make sense? Anybody have any questions on anything that we covered in Chapter 2? Chapter 2. All right, let's go ahead and take about a 15-minute break, and at 6:45, we'll go ahead and kick things off again. Okay, Chapter 3, Voltage. Chapter 3, Voltage. After completing this chapter, you're going to be able to identify the 6 most common voltage sources, describe 6 different methods of producing electricity, define cell and a battery, describe the difference between primary and secondary cells, describe how cells and batteries are rated, identify ways to connect cells or batteries to increase current or voltage output or both, define voltage rise and voltage drop, and identify the 2 types of grounds associated with electrical circuits. This kind of makes me laugh. You know, the big buzzword now is alternative energy, right? Alternative energy. And really, worldwide, we consume electricity. That's the form that we've pretty much chosen. Electronics, electricity. You know, I don't think there's any places that are installing oil lamps. You know, new hotel in the Caribbean. We light our place with oil lamps. No, we use electricity. And there are 6 methods of producing electricity, period. So when I hear about alternative energy, I kind of sit up. I'm like, wow, have they come up with a 7th method? No. As long as I have been in this industry, there have been 6 methods. There are only 6 methods. If you come up with a 7th, now maybe you're onto something. Those 6 methods are friction, magnetism, chemicals, light, heat, and pressure, period. The first one we're going to talk about is friction. Probably the most familiar is the Van de Graaff generator. How many of you are here familiar with the Van de Graaff generator? Let me try that again. How many of you here are familiar with lightning storms? That's probably the best example of friction producing electricity. Guy by the name of Ben Franklin figured that out by flying a kite in an electrical storm. One of our brilliant forefathers. It's amazing he didn't get electrocuted in the process. So lightning is a form of friction, caused by atmospheric friction, if you will, and that produces lightning. Another example is electrostatic discharge. When you walk across a carpet or you move, if you're wearing clothes, just that movement, you could generate static electricity. Tens of thousands of volts could be generated by you simply wearing clothes. Okay, the alternative is not wearing clothes. You wouldn't generate static electricity by doing so, but of course the world would be a different place. The Van de Graaff generator, some of you have maybe seen in a museum before. I've got one in the back room. It's out of commission right now, but there's a big sphere on the top of it. And then what it is a belt. Pulls electrons off the bottom, brings it up to the top, so the sphere becomes charged. And what we could do with that is if you were insulated and you put yourself at that electrical potential, you've maybe seen the pictures where people's hair is standing straight out on end. That effect could be created with a Van de Graaff generator. Friction, not really the best method of producing electricity. You know, I'm not going to hire tens of thousands of people to walk around on carpets and then, you know, touch a you know, a conductor and power cities that way. It just doesn't make sense. On the other hand, if there was a method of somehow harnessing lightning, now that would be something. That would be something. I don't know. How many of you are from the Seattle area, Northwest, originally your whole life? I don't know if you've ever had the opportunity to travel like to the East Coast, the Midwest. Monster storms, the tropics, monster storms. Storms that even jet airliners can't get above. You know, 60,000 foot thunderstorms. Just amazing. I remember a few years ago I was flying commercially down to the Caribbean. And on the way back, this monster storm outside, and even the pilot was talking about it, and he's like, you know, in my 30 years of flying, I have never seen a storm this big. And you just looked out, and the whole thing was just glowing, constantly glowing. It wasn't like lightning flash. Lightning flash was just constantly sitting there, just like throbbing, glowing. It was like, ugh, pretty frightening. So if you could somehow harness that lightning, that would almost constitute a form of alternative energy. Magnetism is the most common method of producing electrical energy. This is how we produce electricity using something called a generator. That generator could be powered by steam. That steam could be generated from nuclear power, coal, water, wind, gas, diesel. It doesn't matter how you rotate the shaft. The goal is you got to rotate the shaft. It's actually very devastating, the news from Japan. I was watching the news this morning, and I guess they upgraded it to a level 7 accident now, which is on par with Chernobyl. Actually, the amount of radioactivity that puts out could exceed Chernobyl if they don't get it figured out. It's really too bad. I'm not necessarily, I don't know if you want to call me a proponent of nuclear. I mean, I worked on nuclear submarines for, 8.5 years of my life. And it's pretty cool. I mean, it's hot because it generates steam, but you know what I'm saying. It's pretty innovative technology. Because you know how often I commute. And I gotta go to the back gas pumps about twice a week with my car. And my car burns premium. High compression engine. I got to burn premium in it. You're talking about $50 a pop just to fill up my car for me to commute. You know how many times I saw my nuclear submarine refueled? 0. Just kept going and going and going and going and going. So you get a lot of use out of nuclear power. Commercial nuclear power plant, basically what they do is they refuel the reactor, start it up, run it at full throttle for 18 months. 100% flat out for 18 months. Then they shut it down, refuel it. Most nuclear power plants have multiple reactors, so when they're refueling one, they got another one that's up and running. And then just back and forth. There's in some cases 3 reactors. So it was actually getting quite a bit of momentum in the green movement. A lot of the folks in the green movement were like, no nukes, and they realized that it's pretty clean energy. Yeah, you got to worry about the nuclear waste afterwards, but it's really a devastating, not only for the folks in Japan, but also really for, energy efficiency and non-dependency on fossil fuel burning. So hopefully they could get a handle on it. I mean, nuclear power, all forms of energy are inherently dangerous. My fuel tank splits open on my car on the drive home and I burst into flames. That'll kill me just as dead as radiation, you know what I'm saying? So it's a matter of mitigating those risks. But I want you to keep that in mind. This is why, again, alternative energy. I've been to Holland before. They got freaking windmills over there. Windmills. They were harnessing wind energy. Now wind turbines, All you're doing is rotating the shaft and you're turning a generator as opposed to grinding your grain with power from the wind. So is it really alternative energy? Nah, there's just a different spin on it. Which is interesting, because I've known this stuff since, puberty. And I always, in the back of my mind, was thinking about, energy in different forms. Because I was always getting yelled at by my parents, shut the door, shut off the lights. What do you think, you live in a barn? This type of stuff. So I was, at a very young age, I was thinking, wow, one of my duties as a child was cutting the grass. And it used to amaze me the small amount of gas I could put. I was always hoping I'd run out of gas, so I couldn't finish the lawn. Why? I ran out of gas. The thing would never run out of gas. It was this little tiny tank, and that motor would just keep, the engine would keep going and going and going and going and going. If there's a way of harnessing that motor to a generator, and that could, I could leave the lights on, I could leave the doors open, I'd get my parents off my back. At a young age, I was thinking about alternative energy. And obviously, I didn't understand all the formulas associated with it. So, no, you can't necessarily power a home with a small 3.5 horsepower Briggs & Stratton engine. But with a 10 horsepower, you could do it. And if you've got a backup generator, that's a good enough size generator to power a home. Anyway, that's how we harness magnetism. The generator could be configured to produce either direct current. Direct current is the flow of electrons in only one direction, negative to positive, period. Negative to positive. Or alternating current. Alternating current is actually current that goes back and forth, back and forth. What comes out of the outlets here in the school and at your home is alternating current. The electrons never really go anywhere, but they're getting shaken back and forth, back and forth, back and forth. That's the harness, that's the energy that we harness. So we could have a generator connected to a shaft that produces either DC or AC. DC generators are not that prevalent. They're not that prevalent. Really, AC is used predominantly throughout the industry because of it's a higher level of efficiency in transmitting the power. This is the schematic symbol for an AC generator. So if you saw this on a schematic, you would say, ah, this means an AC power source, AC generator. Chemical. Chemical. The most common is a cell. Chemical means is the second most popular method of producing electrical energy. A chemical cell. What we're talking about here is batteries. The original chemical cell consisted of two metals, copper and zinc. These were the old school batteries. Remember the kind that if you left them in your device too long, they'd start to like ooze and ruin your portable electronic device? Those were just standard carbon or zinc cells, copper zinc cells. Typically, many cells can be connected to form a battery. When we use the term battery, we're actually talking about something that's made of multiple cells. And part of why I'm telling you this is that you're all here to learn a second language, and that second language is electronics. So if you were going to go to Fred Meyer, where are you going? I'm going to Fred Meyer to get me some batteries. If you said that to me, I'm going to assume that you're going to get batteries, and batteries are multiple cells that are put together. Where are you going? I'm going to Fred Meyer to get me some batteries. What do you need batteries for? For this here flashlight. That battery doesn't, that flashlight doesn't take batteries. That flashlight takes cells. And cells are the typical size batteries that we've come to know and love. AAA, AA, C, and my personal favorite, the D size cell. D size means it's bigger. Since it's bigger, it means it's got more chemical in it. More chemical means it's gonna last longer. If you had a D-size battery and you connected it to your remote control, it'd look stupid, but it would last forever. Okay? I put AAA batteries in my remote and they last for longer than my TV lasts. You know? I just had some cells go out in a remote. And I looked, they were the original cells on the remote. I'm like, man, I've had this thing for freaking 14 years. It's got the original goofy brand batteries that came with it, you know? So typically, many cells can be connected to create what's known as a battery. Now, in schematic diagrams, when you see this symbol right here, you can assume that this is a cell. The short line is the negative lead. The long line is the positive lead. On a schematic diagram, if you put a short one, a long one, a short one, and a long one together, we could make the assumption that this is a battery. The other assumption that you could make on a schematic diagram is when you see this, assume 1.5 volts. Because most cells, AAA, AA, C, and D, all produce 1.5 volts DC. So if we saw this, what can we assume? 1.5 plus 1.5 is 3. So normally on a schematic diagram, sometimes they'll draw 2 of these side by side, sometimes they'll draw 3, but they won't draw any more than 3. So anytime you see 2 or more, assume that it's either the value here, or right next to this I could write 12V. And if I write 12V, well, it's a 12-volt battery pack. And if you split that battery pack open, you would find that it's actually made up of multiple cells that are wired together internal to that battery pack. Make sense? Light. Light. Photovoltaic cell harnesses light. A single cell can produce a very small voltage. So therefore, many cells must be linked together to produce a usable voltage and current. These are primarily used in satellites, because satellites would look stupid if they had like an extension cord connected to them. You know, you'd be like, what the heck is that going up into the sky, you know? Well, it's an extension cord for, you know, communication satellite. So we can't do that. Cost is high, but it's declining. What I suspect is going to happen with this, photovoltaic, basically to make a solar panel, it uses the same technology that is used to make microchips. So it's a pretty costly process. What I suspect to see, and you're not going to find this in any textbook, what I suspect you're going to see is a marriage between photovoltaic and nanotechnology. And when those two merge together, you're going to be able to go to Sherwin-Williams and get paint for your house, and they're going to say, sir, would you like the photovoltaic additive today for $19.95? Sure, go ahead. And they'll add a photovoltaic additive, and the fact that your paint on your house is outside and it's in daylight part of the time, it's going to be producing voltage. Now, we're not quite there yet, but I suspect that that's where we're going to be. They do have the technology now that there are companies that basically could spit out photovoltaic film almost like Reynolds wrap. So you could, you know, go out and buy a roll of photovoltaic and roll it out and connect your connections, and you're producing electricity. So the cost is coming down on this stuff. And think about it, free voltage from the sun. I mean, how cool is that? I mean, it really is. Here in Western Washington, well, you know, you probably have to pressure wash it twice a year to keep the moss from growing on your panels. I got moss growing on my car. I'm getting it the other day, and I'm like, what the heck is it, moss growing on it? But other areas of the country, they're doing this. They're doing this. I was in Arizona, Flagstaff, several years ago. And I checked into the hotel late at night and got up in the morning and opened my curtain of the hotel room. I was on an upper floor, and I was shocked. Number one, it had snowed out the night before, and there was like 6 inches of snow out there. I'm like, holy crap, this is Arizona. What's their snow doing out there? It's Flagstaff. You know, you're in the mountains. The other thing that shocked me is, wow, look at this. Across the street was a solar farm, and it was all photovoltaic panels connected directly to the power grid. And these panels would all track the sun and you know, basically supplying energy to the power grid. So in some areas of the country, they're already doing this. Would I rent out tonight and buy solar panels for your home? Probably not. But again, it's free energy, free voltage. So keep your eye on this technology, because I'd love to be an investor in the company that gets that photovoltaic nanotechnology harnessed. You know, just add a little pinch of it to your paint or whatever, and paint whatever, you just turned it into a solar panel. Science fiction? No. Guarantee you within the next few years we're going to be seeing that technology. This is what those solar panels look like. And the problem is this is on a metal backing, but basically it's glass. It's glass, so it's pretty fragile. You know, you want to have it permanently mounted. Still, for out of space, satellite, it's the best option. Point it towards the sun. The sun comes out every day. Actually, if you're in outer space, it never goes out, because you're not rotating if you're a stationary satellite just looking at it. Unlimited electrical resources. It was actually interesting. I was at a conference. I spoke at a conference a month ago. That was like a month ago today in Milwaukee, Wisconsin. It was at the Green Energy Summit. I was an invited guest speaker. And one of the other speakers was it was very interesting. He had one of our first satellites, a mock-up of it. And when they were developing the satellite, this was in response to the Russians launching Sputnik. And it was the whole thing with the space race. And basically, he who gets the satellite in space first and goes to space first is going to dominate the Earth, So this is all stuff that was going down in the 1950s. They, in a push to get our satellite up there in response to the Russian satellite, basically what they had was a battery-operated satellite. Launch it, goes up, beep, 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 and that's literally all this thing did. It was a beacon, just beeping in space. And then as an afterthought, though, the engineers were like, let's put this on it. This here is a photovoltaic cell. Let's put this on it so that when the battery dies, it'll continue to beep. And they're like, what are you doing? This is stupid. This is stupid. This is not viable technology. Solar panel, photovoltaic cell. This doesn't make any sense. Well, they finally convinced them to put it on. Well, guess what happened after the battery died? Photovoltaic kicked on. And then it kept going and going and going and going. And I think finally it was like interfering with some other communication technology that developed. They finally had to shut the thing off. So that was proof of concept that photovoltaics really work. And of course, it's become mainstream ever since. This is a cool way. No, it's a hot way, actually, of producing voltage. We could use heat to produce voltage with what's called a thermocouple. These are two dissimilar wires twisted together. When I say dissimilar, I don't mean one blue wire and one red wire. I'm talking about two dissimilar metals. And they're not actually twisted together, they're actually welded together. So you get the two dissimilar metals, and then you weld them together. Where they're welded together, when you heat that joint, because they're dissimilar metals, it's going to produce a voltage. Voltage produced is directly proportional to the amount of heat applied. These are going to be used in thermometers. If you've seen a digital thermometer, typically that's going to be a thermocouple. Because what it does is you apply heat to it, it produces a voltage. The voltage gets converted to an equivalency of either Fahrenheit or centigrade. And then you read it out. Real simple way of doing it. Also called a pyrometer. Pyrometer. Had a student in this class several years ago whose father owned a company locally. I forgot the name of the company, but they basically produced thermocouple sensors. And one of the big products that they were developing was specifically for the racing industry. And what it was is about the size of my laser pointer. It was nice stainless steel, and it had a little probe on the end, and that was the thermocouple. And what was so popular in the race industry, I don't know how many of you are into racing or whatever, you take like NASCAR, for example, and ideally what you want to do with one of those race cars is set it up so that you distribute the weight evenly on every tire equally across the tire. And if you could do that, obviously you've got the most contact with the road. It's going to give you the most handling on the track. It's going to give you the best performance. Generally speaking, there are some exceptions to that on a road course versus whatever. But basically you want full contact with all your tires on the track. Make sense? Also understanding with NASCAR, rear wheel drive, right? You're going to have a lot more friction on your rear wheels. So what happens is when that race car pulls in and they pull the tires off, then they could sit there after they get the car out of the pits with their thermocouple probe and then measure across the tire, outside, inside, or outside, middle, inside, for my left rear. My right rear, take the same readings. My front tire, take the same readings. My other front tire, same readings. So you should see consistency between the two fronts across temperature-wise too. That means you got the car set up so that the tires are in full contact with the road. So it's really a poor man's alignment tool. So he gave me one of these. And it's kind of cool because it's the OEM. It's just stainless. It doesn't have any decal or sticker on it. I mean, they're the factory that built it and then sold it to some racing company so they can put their name on it, and or Snap-on and charge an arm and a leg for the thing. So he gave me one of these things. So I actually did some experimentation. Since I am a commuter, I did that a couple times on my drive home. I was wondering what the alignment on my car was. So sure enough, I drive home, I pull off the exit hot, Federal Way, pull over the side of the road, get out my fluke meter with this thing plugged in, take temperature readings, look for consistency. I've basically been tweaking alignment in my vehicles using nothing more than that temperature gauge. Pretty cool. Pretty cool. Thermocouple. Simply applying heat to the device produces voltage. That simple. Apply heat, it'll produce voltage. This is what the schematic symbol for one looks like. Again, understanding that these are going to be dissimilar metals, two dissimilar metals, and then you weld this together, the bead.
So are they not actually twisted together like it shows in the picture?
Actually, because they're in contact with each other, it will produce.
Where would you take the reading at the very end of it?
On the tips.
Okay.
Yeah. So simply by putting the wires together, they are going to be in contact with each other, so you are going to get some reaction, but these thermocouple probes are actually welded. The tips are welded. Believe it or not, another method of producing voltage is simply by the use of pressure. This is called the piezoelectric effect. Piezoelectric effect. Voltage is going to be very small, so it must be amplified in order for it to be useful. But just a pressure change on a crystal will produce a voltage. This is used for crystal microphones, phonograph pickups, right? And precision oscillators, as well as some sensors, pressure sensors. You could get some really inexpensive pressure sensors now that are calibrated for barometric pressure, standard barometric pressure. So as the Earth's pressure, the atmospheric pressure changes on it, the voltage will change. You couple that with a weather station, or couple that with, actually you could use it for altimeter. If you're sending a rocket up and you want to know how high your rocket goes, you know what your base pressure is. As you go up in altitude, the pressure decreases. So you can have an inexpensive little sensor that keeps track of your pressure. Also, these are used in a lot of engine sensors now, right? You could monitor all types of different pressures, your oil pressure, your cooling system on board an aircraft, your hydraulic pressures, all of them. Little sensor. That voltage gets amplified, sent into a computer, and then you can look at all this virtual instrumentation. Simply doing it by applying pressure to a crystal. This is what the schematic symbol looks like for a piezoelectric crystal. Now, we're going to talk about some different types of batteries. Battery, of course, is a combination of two or more cells. Now, we have two different choices of cells. One is called a primary cell, the other is called a secondary cell. Let's first talk about primary cells. Primary cells are cells that cannot be recharged. One-time use. These are like most of the cells that you and I buy, right? When you're done using them, you recycle them. Don't throw them in the landfill, right? You recycle them. Bring them to the hazmat place, and then they'll turn it in and get money and make your community more profitable based on you turning in your dead batteries. Some of the stuff you don't want going in the landfill. Although they've gotten better with the choice of chemicals that they're using. But primary cells, once you use them, you throw them away. This is designed after what's known as the Leclanche cell or dry cell, also referred to as the carbon zinc battery. Carbon zinc battery. This is the old school battery that we were talking about earlier. I got a couple old timers in here. Remember, that's all we had. These are the only types of batteries that used to exist. And then I believe it was in the 1970s they came out with alkaline cells. That's when alkaline became somewhat mainstream. Started to become mainstream. These alkaline cells were still pretty expensive as compared to the carbon zinc batteries. I remember Radio Shack, because again, I was a big electronics guy, so I was like hanging out at Radio Shack, like looking at all the parts and stuff. And Radio Shack used to have a Battery of the Month club. And you got a little card, and you'd go in with the card, and you'd pick out the battery that you wanted, and then they'd punch your card, and you got a free battery. It was a carbon zinc battery, but it got you in the store. It's kind of a cool thing. Alkaline cells, really, really good. Alkaline cells would work a lot better with a lot of electronic equipment when it came into being. The latest cell, and my personal favorite, is the lithium cell. These are the high-end lithium batteries that Energizer produces. They cost like $16 for 8 batteries. They're very, very pricey. But these lithium batteries will produce a voltage longer than any of these other types of primary cells. They also have a longer shelf life. I'll bring in a package, we can look at it. I bought some last week, and I think it's the expiration date on them is like 2022. Some crazy time in the future. We won't even need batteries like that. We'll be flying to work in jetpacks and stuff. We won't even need lithium batteries. And the other thing that these are real great at is working at a variety of different temperatures, from extreme cold, which really kills batteries big time, slows down that chemical reaction, to extreme heat. They've kind of known about lithium batteries for a while, lithium cells for a while. On my airplane, there's something that's called an ELT, Emergency Locate Transmitter. In the event of crashing, there's a G switch that triggers a transmitter to start transmitting out a beacon that gives your position away. So search aircraft, actually they used to have satellites that looked for that signal, but now long story, they've switched those satellites off. They've gone to some different frequencies now, but it would transmit. So when this thing worked, it had to work. It's a safety device. Even like on a ship that goes down, they have these EPIRB systems that transmit to the satellite. You want that thing, when it has to work, you need the thing to work. So this has always been the choice for those types of applications, the lithium cell. I was really, really jazzed and excited when I saw these come on the market for a consumer-based product, because the lithium batteries before were unique, you know. To the manufacturer would put it together, and you'd have to buy the replacement from them. Because like the FAA requires every 24 months, you've got to replace that cell whether you've used it or not. So for them to come out, the sizes that I'm aware of, they have AAA and they have AA size. Have any of you here used any of those? Have you used them? Highly recommend it. If you're going on your dream vacation, if you're doing photography and you want something for your flash and you want that flash to keep going off and you don't have to worry about it. If you have if you're going hiking, I use it in my GPS. I have a backup GPS, that I use whenever I'm going off the grid or anything. I've got a pack. That I bought. Energizer will sell you a pack that you could use to recharge your cell phone. Have you seen those things? It's like a little pack, and it comes with those lithium batteries, and it's got a little cord. So like if you're off the grid and you got to recharge your battery, it comes with that style, your micro USB or mini USB plug or your Nokia. Everything now is micro USB. That's kind of the standard for newer cell phones. But you put those lithium batteries in it, you plug it in, and it'll give you another charge. So if any of you do any backcountry stuff or anything like that, I highly recommend you look into them. It's a wise investment, a very wise investment. It's the best primary cell that money will buy. This is kind of, you got the diagrams in your book, kind of a cutaway view of a standard carbon zinc cell. Another cutaway view there. Cutaway view of a 9-volt battery. Is this really a 9-volt battery? Is it really a battery? Yes, it is. It's made up of multiple cells that have been put together. Each cell is capable of 1.5 volt. So they put multiple cells together to give them 9 volts. Why 9 volts? Actually, this 9-volt battery is also synonymous with what was called a transistor battery back in the day. There's no transistors in it. Why was it called a transistor battery? Because this is the type of battery that your transistor radio would take. Growing up in Connecticut, I used to have a little small 8-transistor radio. Used to go to the beach, and I used to tune in my little radio, play music, listen to New York radio stations, playing all the top 40 hits and everything. 8-transistor radio. Took a 9-volt battery or transistor battery. This was typically the battery that I would get as a free battery at the Battery of the Month Club from Radio Shack. Why? My assumption was it's got 9 volts. The other ones have 1.5 volts, so I'm getting more for my punch, my free battery, than a 1.5 volt battery. So this was typically the bad boy that I always used to get for the purpose of experimenting. Secondary cells are cells that cannot be recharged. You're all familiar with this type of cell, the lead acid battery or wet cell, which is in your car right now. These batteries are not just used for automotive applications. These wet cells, these lead acid cells, are also used for backup power supplies by the phone company. For your landline, they're also used at cellular sites for backup power. In the event that power is interrupted to the cell sites, automatically they'll switch over to battery backup. They're typically lead acid cells.
That's what they use for like solar systems too, right?
Absolutely. And they use those for solar systems now because they're the cheapest secondary cell that's really on the market. There's other technology that's more efficient, that's more better, okay, but it costs more. So if you just want to, let's say you live out in the desert and you want to run lights by day and harness the energy by day, and you need a lot of solar panels and you're going to need a lot of secondary cells. The cheapest secondary cells that you could buy are lead acid cells. My submarine had a whole bank of lead acid cells located in the center of the submarine down in the keel, the very lowest portion of the boat. And it was called, ironically, the battery well. And in the battery well were batteries that were basically 6 feet tall, and they were about this big around, and they were individual cells. And it took a crane to be able to lower these things in and move them all in. And then they had wooden shims. Wax-impregnated maple shims were all put in between these, and it was all one giant bank, and they were all wired up. Lead acid. On a daily basis, an electrician would strip all the metal off of their uniform if they had a belt on or anything metal. And typically what they had is a special jumpsuit that they put on that had all acid burns in it. And what they would do is they'd have to climb down in the battery well, and they'd have to check the gravity, the specific gravity. This is the electrolyte fluid inside. And basically, when we charge a battery, what are we putting into a battery? Who said electrons? Electrons. That's really what we're doing when we charge a battery. We're putting free electrons, we're storing it in an electrolyte solution. Are electrons matter? Absolutely. They're not very dense, but they still are matter. When you charge a battery, what you do is you increase the specific gravity of that fluid, that electrolyte fluid. So what the electricians would do on a daily basis is they had a clipboard and they had a grid that showed all the locations of the battery. They would go down in and they would check the specific gravity. You know what I'm talking about with specific gravity? Specific gravity is a comparison of the density of pure water, H2O at room temperature, standard temperature. The specific gravity of H2O, pure water, at room temperature, standard temperature, is 1. 1.000000. It's 1. It's what we compare everything else to. Now, if I have pure water and I start to get some salt and I dissolve salt into the water, what am I going to do to the specific gravity? I'm going to raise it. I'm going to increase the density of the fluid, and by taking a specific gravity reading, I'm going to show that it's more dense. That shows me that I've done what? I've put matter into the solution. If I dissolve sugar into it, same thing. If I pump electrons into it, what am I going to do? Same thing. I'm going to increase the density of it. I use specific gravity. I brew my own beer. And I use specific gravity to tell me what the alcohol content is. In the brewing process, I basically impart a lot of sugars into the beer. And I take that reading. The more sugars I put into the beer, the specific gravity increases. The density increases. Make sense? Then what I do is I get yeast. I put the yeast into that solution, and the yeast consumes the sugar, converting it into CO2 and alcohol. So after the yeast has done its job, I expect to see that specific gravity decrease because alcohol is less dense than water. And then I take my first reading, compare it to my last reading. That gives me my alcohol content of what's inside the beer. For a battery, your battery in your car has 6 cells. If you buy a hydrometer and you test those cells, you should get consistency across all of those cells. If you don't, if this cell's good, this cell's good, this cell's a little bit lower, this good, 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 this cell being a little bit lower, you're probably developing an internal short in that cell. You need to replace your battery. You can't just replace the individual cells, you have to replace the whole entire battery. So back on the submarine, they were really concerned about that on a daily basis. They sent somebody down in the battery well to take those readings, because if they saw a cell that started to develop an internal short or a problem, conceivably it could take all of that energy and dissipate that energy through that one bad cell. That's bad news. Because, oh, by the way, you know why we had a battery bank? If our nuclear reactor shut down or we had a problem, we could get to the surface. When we get to the surface, we could start up a diesel generator. So from that transit from the deep up to the surface, we needed to be on battery power. If you can't get the diesel started while you're on the surface, or actually at periscope depth, because we had a snorkel they could just stick up where it's you're in induction system for the diesel engine. Run the diesel, we had a generator connected where we could keep not as much power as we'd have to nuclear power, but to keep all vital systems up and operational. Actually, I had a real scare once. We were someplace we weren't supposed to be, like someplace we were not supposed to be, typically where we always went with my submarine. And it was a national holiday for this country. So all of their, they'd take their submarines and drive them through Red Square and their tanks and their missile launchers and everything. And, we had nothing better to do. So instead of like, hey, we're watching the Soviets, they're having a holiday, let's us have a holiday. Because on the 4th of July, we're going to be watching the Soviets and they're not going to take into account our holiday. The captain didn't think it was a very good idea that I had. Now, as a matter of fact, Mr. Gryniuk, I think what we're going to do is we're going to do some drilling today. And it's firefighting or whatever. Well, we did a drill, an exercise that involved scramming the reactor. Sounds ominous, doesn't it? Scram the reactor. Oh no, don't scram the reactor. Scramming the reactor is actually a good thing. Scramming the reactor is when you shut the reactor down. You have control rods, you move the control rods in, you neutralize the reaction, the nuclear reaction. This is actually what they did too in Japan. After the earthquake, as soon as there was seismic activity, pow, they shut those reactors down, scrammed the reactors. The problem that they had afterwards was with the tsunami damaging, I suspect it was their intake, their seawater intake used for coolant, and they couldn't dissipate all that heat that had already been generated, and then it became an avalanche, so to speak, of circumstances. Anyway, we're somewhere we're not supposed to be, and it was quiet. So the captain figures we're going to do some nuclear drill, scram the reactor, pow, scram the reactor. Normal procedure is we start to come up to periscope depth, make sure that we're not going to hit anybody up on the surface, come up, raise the snorkel mast, start the diesel generator. Well, they try starting the diesel generator, which was commonplace, wouldn't start. And what had happened is there was this multi-pin connector that for whatever reason disintegrated in the back of the diesel control panel. So it's kind of like, well, that's going to take 2 days to put back together, you know? So we're on battery power. To be honest with you, we knew it was a drill and we were all real sloppy, rigging for reduced electrical. That's where we shut down all non-vital systems. And we knew it was a drill, so we were very slow in doing it. We expended over half of our battery energy in that period of time. So now all of a sudden, the reactor shut down. We can't start the diesel generator, and we've just consumed 50% of our battery power because we were screwing around, kind of dragging our feet with this exercise. So we realized what was happening, and basically the decision was made, restart the reactor. Well, they try restarting the reactor, and the reactor won't start. And we've consumed all of our battery power. So now we went to this like super rig for reduced electrical, where there's like, you know, emergency lighting and all the environmental systems are down. So the air all of a sudden is almost unbreathable, and it's in excess of 120 degrees, and it's humid, and it's just miserable. Can't get the reactor started. And in my job, surveillance, I was down to one receiver. I shut all my sophisticated stuff down, and I'm down to one receiver. You can't make the story up. It's like, holy crap, here comes the fleet. It's like, what are you talking about? Here comes the freaking Soviet fleet. They're headed right towards us. I'm like, you gotta be kidding. So it got really hairy, because this is the type of thing that like World War III could start over. What's a submarine doing in our harbor? You know, violating our sovereign territory and all of this stuff. You know, we couldn't get caught. So. Truth be told, they were able to get the reactor started. They had to kind of amend their procedures, and come to find out it was actually a reactor control switch had failed. It was a series of circumstances. We called that day, anybody that served on the boat in that era, affectionately known as Black Tuesday, because things were really bad. And I had it good. I mean, my space normally where I worked, I had to wear like foul weather jacket to stay warm because of all the air conditioning. Of course, all the air conditioning was down, but I tell you what, the guys in the engineering spaces, I mean, they were stripped down to their underwear and no shirts, and they're just sweat pouring. I mean, it's temperature skyrocketed, you know, 150, 160 degrees back there in the engineering spaces, and you're trying to troubleshoot something. But anyway, it all worked out good in the end. But that's the necessity of backup battery. Now, a lot of you may be saying, well, I'm never going to go to work on a nuclear submarine or a ship or whatever. No, you might go to work as a biomedical electronics tech at a hospital. Guess what hospitals have? Backup battery banks. You might go to work for the Federal Aviation Administration. Federal Aviation Administration down in Auburn, Washington, at the Mountain Region Air Route Traffic Control Center. I don't know if any of you are aware of that facility. If you go to the Muckleshoot Casino down there, it's like right across the street. It's a big building, fences around it, armed guards, all kinds of stuff like that. That's where they control all the air traffic in the northwestern United States. From western Montana to the Pacific Ocean, from the Canadian border all the way to northern California. If you're an airplane in flight, you're talking to somebody in Auburn, Washington. They lose the power at that facility, guess what? The whole northwestern United States aircraft are flying blind. So they were kind of smart about this. They put in a battery backup system. So as soon as the power AC crashes, these batteries have power inverters, and that brings it back up online so they don't miss a beat. Once the batteries are up online, then they have diesel generators in another building on the property that will go ahead and kick in, and they have huge fuel tanks so that they can power that for a very long period of time. If any of you have ever heard of the news of the past, a lot of times if they have a glitch like in the air traffic control system and switching over to backup power, that's actually what the problem is going from AC to that battery backup. If it doesn't happen seamlessly, all of those systems go down. You all know with computers, you got to reboot computers, so you have aircraft flying blind without air traffic control for a period of time. So it could be somewhat of a inconvenience, safety concern. So a lot of you are going to see this. Actually, one of the most reliable systems, and this is I don't know how many of you still just have an old-fashioned telephone line to your home. POTS is called. And basically what that is an old school, just 2 wires coming to your house. Most of us now are on broadband and voice over IP and all this kind of crap. The old school telephones were the most reliable. You could have a power outage, you could have earthquake, whatever, and you pick that phone up and you're still going to get a dial tone, because that dial tone is being generated by backup battery banks at the central office, and that's powering the phone system. So, you know, I've experienced a lot of blackouts in my life where the power would go out, and I never lost that dial tone on the phone. Now, you know, how many of you are like with Comcast? You know, I mean, what was I thinking when I went to actually, believe it or not, I'm not just talking the talk, I'm walking the walk. Before I came to work today, I actually called Quest. I want to get an old school line back into my house, because I'm looking at my phone bill. My freaking phone bill, I don't know, I'm paying like $70 a month for, you know, caller ID and call waiting, and the only people that call me are people that I don't want calling me, okay? So why am I paying $70 a month to have something that I don't want, and I don't want to shut the line off because I have some other uses for that line. So I called Quest, and I'm like, it's kind of an unusual request. Do you have any of the old school lines that, you know, I could still have, you know, yeah. And how much? $13.50 a month plus tax. I'm like, that's what I want. Can you port my existing number back to it? Yeah, no problem. So I'm going to get that scheduled. $13.50 a month. Now, you can no long distance or anything, but I don't want it for that. I want it for that 911. I want it. I don't know why I'm going to disconnect the ringer, because again, the only people that want to call me, they call my cell number, you know. But I still need that. If you have an alarm system at your home, you need it. If you've got a satellite TV box for updates and pay-per-view, you need it, so it could call into the mothership on a daily basis. So battery backups are still out there. So don't think you're not going to go to work in the industry and never see a battery backup. Now, you're all familiar with lead acid, nickel cadmium, NiCad. How many of you are familiar with NiCad batteries? NiCad have been out for a long period of time. NiCad's had a nasty habit of generating what was called a memory. And what that memory was, in essence, is if any of you have ever had your arm or leg in a cast and you don't use it, basically the muscles forget how to fully exercise your range of motion. You got to go through some therapy to get your arm working again, right? It's kind of the same thing with a NiCad. A NiCad, if you didn't fully discharge it and then fully charge it, it would only think that its range was in this narrow margin of performance. So the problem with NiCads with like camcorders and cell phones, where as soon as that voltage started to drop a little bit, you start to get the low battery indicator. And to preserve the electronic integrity of what you were doing, it would shut off. Then you'd get it, stick it in your charger, charge it back up, and what would happen? It would only get used to operating in this little realm right here. Some of the manufacturers got smart and they put a little button on there and they could connect it to a load and drag it down all the way and then recharge it all the way. Because I understand this stuff, I've gotten exceptional use out of NiCad batteries. When my kids were growing up, my first video camera back in the 1980s, I had one of those big VHS units. Don't laugh. It was VHS. At least it wasn't beta. Should have been beta. Beta was better, but that's another story for another day. But it was one of these big Kirkland VHS, you know. And it took this big 12-volt battery pack. And I went to replace it, and I was looking at some different vendors, and they were looking at me, and they couldn't believe that it was the original battery pack. It's like, we don't even carry replacements for those anymore. You know, how long have you had this? Since the beginning. Well, you know, how could this be? It's because I understood how to take care of NiCads. What I did is I made myself a dummy load, and when the battery got low, you know, I mean, obviously if it was a birthday party or something that I wanted a video, I could recharge the battery. But at least on a regular basis, I would discharge it all the way and then charge it all the way. And by the way, with nickel cadmium cells, when I say charge it all the way, that doesn't mean slap it in your quick charger. Like I've got a cordless drill at home, a Makita. I got a quick charger for it. Worst thing you could do. Mine still works. But you know how those quick chargers work? They actually have a temperature sensor in the battery pack. When the battery starts to get hot, it must be full. So it cuts the battery off. It's not a full charge. The only true method of charging a NiCad properly is a timed charge. A trickle charge where you're trickling in a known amount of current and then you bring it gradually up to that 100%. Not slam it and then the thing gets hot and then shuts off. Some of the early ones, once it would stop charging, it would cut it off, right? And then what would happen when the battery cooled down? It'd start charging again. And then it would get hot and shut down. So you ended up with this cycle in it. So these were the real cheap chargers, and those would just eat these NiCads. So if you know about NiCads weren't that bad. They really weren't. The next thing was nickel metal hydride. Nickel metal hydride. That was the next evolutionary process, rechargeable battery, secondary cells. A lot of us had them years ago in our cell phones. Worked very, very well, less prone to that memory condition. With all these secondary batteries, though, is it an unlimited number of charges and discharges and recharges? No. Every rechargeable battery, when it's brand new, you only get so many cycles out of it. They're not going to last forever, even if you take good care of them. And then now lithium ion. Lithium ion, if you've got a newer cell phone, probably came with a lithium ion. That's really the best that's out there now.
Is your Makita battery still a nickel cadmium? Do they
Yep.
still make cordless drills out of that?
I don't know. I don't know. I was thinking about that the other day because I've actually got a new battery put aside that I've never charged yet. It's still in the package. So I don't know. I've been keeping my eyes open in a store for that style pack, and I'm sure it's available on the internet. But what am I going to have to pay for it? You know. The other thing, though, too, check this out, because you know I'm not the smartest guy, but I kind of understand some of this stuff. Some of those cases, you could actually cut them open and you could replace the cells yourself, you know, and then rebond the plastic back together. And I've done that on several things myself as I've reconditioned, put in new packs. I had some, I forgot what the heck it was. It took NiCad batteries. And then what I did is I cut it open, and it was just standard NiCad batteries. Usually it doesn't have the label on it, but the sizes were the same. And then what I did is I went to Harbor Freight Tools, and I bought nickel metal hydride rechargeable cells, and I put the pack back together, soldered it up, good to go. Good to go. So in some cases you could do that. A lot of high performance things too, even like jet aircraft. If you're down driving past Boeing Field and you see a Learjet sitting out there, believe it or not, what they're typically going to use is not the lead acid. They're actually going to have NiCad packs. So when they start the engines on the jet, they're starting it off a NiCad, and those are very, very expensive. So it's kind of amazing. You're a multimillionaire flying around in a Learjet. A lot of times, you know what those guys will ask for? They want a starter pack to be brought over with a little tug, and there's a cart with a bunch of batteries on it, lead acid batteries, and then you plug that into the aircraft, and then what they'll do is they'll use that so they don't have to put a charge-discharge cycle in their NiCads in their precious Learjet. It's like, man, if you can afford a freaking Learjet, you can afford a new freaking NiCad, you know. But I used to work it was the funnest job I ever had. I worked part-time at an airport in Connecticut. And those guys always used to amaze me. And a lot of them wouldn't. A lot of them would tip you. You know, you bring that pack over or whatever, and here you go. Go buy yourself a good lunch there, son. Oh, thank you, sir. You know, I didn't mind. Some of these dudes, oh man, I'm saving you money. You're not even tossing me a bone. Come on, man. The heck. Next time I'm gonna park you out there. This is the cutaway view of a lead acid cell. Now, connecting cells and batteries. Connecting cells and batteries. We have series aiding. This chart here is erroneous. Let me draw this on the board here, what we're talking about here. Series aiding means negative, positive. I can assume that this is what voltage? 1.5 volts. So if I connect it to another cell, I can assume that this is 1.5 volts. And if I go ahead and even connect a third cell down here, I can assume that this is 1.5 volts. What am I up to right here? What's my total voltage from this point to this point? Okay, very good. 4.5 volts. Does everybody see that? Everybody see that? So what I'm doing here is by series, in series aiding, I am increasing the electrical pressure that's available to me. The amount of current that's available here is going to stay the same because this is what we call a series configuration. And current will always stay the same in a series configuration. So by connecting up batteries or cells like this, I could get a higher voltage, but current will remain the same. Does that make sense? Now down below it talks about series opposing. Series opposing would be like, okay, I got a negative and a positive here. You all agree with that? Then I'm going to connect a positive and a negative here. So I've got 1.5 volts here. And how many volts do I have here? Minus 1.5 volts. So what's my voltage across? 0. So my slide, which is politically correct, says it has little practical value. It's actually stupid. This is like, you're putting a battery in backwards. Why come my flashlight no work? And you take them out and you realize you put in one of the cells backwards. Has little practical value. This one's adding 1.5 volts. This one's taking 1.5 volts away. You're putting a negative and a negative here. Current's not going to want to flow. Again, it has little practical value.
Is there any practical use for it whatsoever?
Yeah, challenging electronics students when they're going through a theory course like this. It really is. Because I could draw like 5 or 6 of these, and then you got to, let's see, plus 1.5, plus 1.5, minus 1.5, minus. So we are going to give you some problems like that have voltages. Because quite frankly, when you do get into sophisticated electronic equipment, you're going to see that there are some voltages that are being added to a circuit and some that are being taken away from a circuit. So from a math standpoint, a theory standpoint, it does have value in studying it. In parallel, and again, this is a typo here. These should not be equal signs. This should be total current is equal to I1 plus I2 plus I3. Let me show you this one. Actually, let me just go to the next slide and I'll show you on the slide. This is what we were talking about, or this is what I was talking about. I don't know if we're talking about it. That's what I'm talking about. This is 3 volts. 3 volts and 3 volts is equal to how much across this? 6 volts. Can you dig it? All right. So here we got 3 volts and 3 volts, which is equal to 6 volts, connected in parallel with 6 volts. Why come? Why come I do this? Why would I possibly, what is the advantage of this
To increase the voltage and the current?
over this? What's that?
To increase the voltage and the current?
Is the voltage increased? You said to increase the voltage and the current. Is the voltage increased?
Not over the previous.
No, I still get, how much electrical pressure am I getting out of the circuit? 6 volts. What's that?
Increase the capacity.
Increase the capacity. Tell me more about that. I like that.
Well, the milliamp hours of the battery.
Very good. Batteries are measured in amp hours. How much current over a period of time can they provide us with? So let's look at this scenario for a minute. Let's say that we all have a sailboat. Wouldn't it be nice if we all had a sailboat? We could sail off to the sunset. Let's sail up to the San Juan Islands and hang out up there. Okay? I've got a 6 volt, it's an unusual sailboat. I've got a 6 volt anchor light. So when I find a nice cove up in the San Juans and I drop my anchor, by Coast Guard regulations, I'm required at night to turn on a light that says I'm anchored. And it's a 6 volt light. The problem is this configuration here will only last for 6 hours. And then the light gets dimmer and dimmer and dimmer until it goes out. And shortly after it goes out, the fog rolls in. And here comes along a Washington State ferry. And it runs us down and it ruins all of our fun that we're having on our sailboat in San Juan Islands. So I'm a pretty smart guy. What I did is I went out and I got another battery pack and I put it in parallel with the original battery pack. The original battery pack lasted for how many hours? How many is this going to last for? For the same size load, it's going to last twice as long. How's about them apples? That's how it works. So basically, he or she who has the most batteries in parallel is going to last the longest. Plain and simple. It was actually kind of a funny story. Going to sea for extended periods of time under the water, there were very few things. I mean, even reading material, books. How many books can you bring with you? What can you do? So back in the day, the only form of media for me, basically, for music was cassette tapes. So I had my little, I didn't even have a Sony Walkman. I eventually upgraded to a Sony Walkman, but originally I had some, off-brand cassette player. And actually, that was a big advancement because prior to that, you needed the big cassette player. You put the cassette in, headphones, No 8-track. I'm talking strictly the cassettes. This was high-tech cassettes. So I bought something that looked like a Walkman, but of course, Walkman is a trademark of Sony Corporation, and this was some off-brand. So it was so funny, too, because everything that we did was super secret. You couldn't tell anybody. We couldn't even tell our spouses that we were going. So all of a sudden, you see a guy in uniform, at the exchange, buying 5 tubes of toothpaste and 7 bars of soap and 100 packs of batteries, and he's in uniform with his unit, on his ball cap, and it's kind of like, you're stocking up. You guys are going to sea, So you didn't have to be like an intelligence expert to figure out who's coming and going. So anyway, we're going to go to sea, and it was going to be like a 7-month operation. That doesn't mean that we'd be totally incommunicado or away from civilized, shopping or whatever, but for at least a minimum of 90 days, we're going to be underwater. So I go out, and my cassette player took AA batteries. So I bought a bunch of these AA batteries. Well, come to find out that this thing was such a piece of crap that I could listen to 1.5 sides of a cassette tape before the batteries would die. And I'm like, I'm not a math expert, but I'm like, I'm going to run out of batteries really quick. So after I used up all my AA batteries, and I still wanted to listen to music, because again, you're living with 120 other people in a steel tube, 285 feet long, 28 foot diameter. When you could put those headset on and you could kind of zone out, that was, a little piece of peace and tranquility you could have. So I'm like, well, I'm a smart guy. I got an electronics background. How tough can this be? So I cracked the thing up. I figured out what voltage I could wire in externally. So then what I did is every division on the submarine had different consumable products that they were responsible for stocking because you didn't have a store. So actually for my division, it was pens, pads, paper. So if you were a nuclear reactor guy, you'd come to me and say, hey, Joe, I need some pens? I'd be like, screw you, But no, I'd give you the pens or the paper or whatever you need. Well, ironically, the division that was responsible for providing batteries, ironically, were the electricians. So we went back and I said, I need some batteries. What do you guys got? Well, we got these sizes here. And they were the big D size, and they were military, olive drab, green, big batteries. And I'm like, yeah, give me 8 of them, So I got these 8 batteries and I wired them all up, combination series parallel. And then I got electrical tape and I this big freaking brick, And so I got this nice little portable cassette player that I paid, you know, an exorbitant amount of money for, and then I got this big brick that I like. So it was truly portable device, you know. So anyway, it worked, and it worked fine. And then I got so used to carrying this thing around that it was like months later, we're in port, and I'm still carrying this brick, and I even with a handle on it. And it kept working. And I'm like, why am I doing this? This thing is stupid. I actually cut it off, and I threw it over the side of the boat. It's probably sitting in the bottom of the Thames River in Connecticut still. But the moral of the story is that portable cassette recorder operated off of 1.5 volt cells, did it not? What was the difference when I added the brick to it? Those are 1.5 volt cells, right? Capacity. Physically more chemical, physically more capacity. Higher amp hour rating, and it kept going and going and going and going and going. So this is one of the principles for a lot of you that may pursue alternative energy. Whatever that means. Basically, it's the efficiency of your cells. How many cells do you have? How much energy can you store? I actually had a student that is a project. He owns some property in central Washington. And living off the grid. Had a backup generator, also put in some photovoltaic cells. And as a project, he basically did the math and figured out, like, on the shortest day of the year, how many appliances am I going to want to run in my little cabin? And will I have enough electrical energy to make it through the night? And that's basically what his target was. And he says, I need this much storage capacity. And that's what he used as a target. And actually increased that, I think, by about 20%. And then in the summer, how many hours could he use photovoltaic to charge that? And then what's the minimum amount of time that he needs to run his generator to get those batteries up to that full capacity charge? So if you understand the math behind this, let me tell you, you're a commodity out there, because a lot of people don't have a freaking clue. They don't. They don't. When I was on a cruise a couple weeks ago on vacation, I met I'm trying to get on better terms with this guy, and actually we've been corresponding via email. He owns a 52-foot yacht in Miami and an airplane, high-performance aircraft. And he likes taking his yacht down to the Bahamas and dropping anchor. And he doesn't like running the generator. So we had a whole discussion about energy management, photovoltaic. What's the minimum amount of time that you could run your generator? Can you add batteries to augment the system? And I mean, this guy is a couple master's degree, highly intelligent. And he didn't have a clue of what I was talking to him about. So if you understand this, let me tell you, you got it going on when it comes to this type of stuff. Make sense? Voltage rise is the energy we put into a circuit. Voltage drop is the energy that we take out of the circuit, if you will, is given up as the electrons encounter resistance in the circuit. So voltage rise would be like your batteries. Voltage drop is what you're powering. And you know what? They should always be equal to each other. If you've got a 5-volt battery pack and you're powering a radio, that radio should be consuming 5 volts. 5-volt voltage rise, 5-volt voltage drop. Make sense? You should never end up with energy left over. If you are, that's what we call a malfunction. You've got a malfunction. You've got voltage not going from the source to the load. The voltage rise that the power company provides my house with is 240 volts AC. My voltage drop for my home is 240 volts AC. If it was 239, that means a volt is being dropped somewhere underground or in the overhead. It's not supposed to be getting dropped there. Question?
So like if the power company provided you with, is it
Voltage rise.
voltage rise?
Mm-hmm.
So like if you use more energy, would you'd be pulling out more current, not more voltage?
Yeah, your question is more related to power. I'm talking simply voltage. I'm talking simply voltage. So that if I've got, and I'm keeping it real simplistic, and you need to understand it in a simplistic manner. If this calculator takes 3 volts DC, that 3 volts DC is going to be my voltage drop, right? If I want this thing to operate properly, I need to give it a voltage rise of 3 volts. So that's all I'm saying. Voltage rise is the voltage pressure you apply to it. The voltage drop is the pressure that gets consumed by the load. And they should always be equal. If they're not, wherever the missing voltage is, that's a problem.
So if you consume less voltage,
If you're consuming less than what the power company's providing you with, you've got a problem. Because that missing voltage has got to be somewhere. And where you find it, that's the problem. Make sense? Okay, we'll talk more about that concept, but right now I just want you to understand voltage rise equals voltage drop. Ground. Ground. This is an interesting concept. Any of you here ever driven over Snoqualmie Pass? How do you know you're going over Snoqualmie Pass? It's not a trick question. How do you know you're going over the pass? There's a sign on the side of the road that says Snoqualmie Pass. I try to keep it basic here. Now, that sign also says Snoqualmie Pass, and there's another bit of information there. Elevation. Elevation above what? North Bend? Seattle? Above where? Sea level. You guys are all smart. You guys are one of my smartest classes here in a while. High tide or low tide?
Average.
Average. And you know what we call that? MSL, mean sea level. Mean sea level. So one of the things that Al Gore is talking about, like sea level rising, that's what he's talking about. So his big concern is all the expense of changing all the signs. Elevation, no. Obviously it's going to cause a lot of problems if mean sea level, if the polar ice caps melt and sea level rises, it's going to be a lot of flooding and devastation. Okay, especially during hurricanes and high tide events and tsunamis and everything else. So we use the height of the ocean, mean sea level, as a reference for all of our height measurements. It's actually really important. When I fly my airplane, it's one of the first instruments I calibrate when I get in, is the altimeter. And that shows me how high I am above sea level. It's kind of important. I flew my airplane Friday night. I went across the top of SeaTac Airport. I had airplanes taking off and arriving, and I'm flying through there in my small plane. You kind of think it's important that I know what altitude I'm at? Yeah. And as a matter of fact, they check back with you. When you establish radio communications, they say, you know, hold, maintain 1,500. 46 kilo, what's your current altitude? 1,500. Roger, we got you at 1,500. You're cleared through our airspace. Because they want to make sure you're not off. It's important to me. So that's how we calibrate if you're into hiking, driving, even boating. Mean sea level is kind of critical, isn't it? High tide, low tide. If you're at low tide and you hit a freaking rock, it's kind of important you have the right charts and you understand low tide.
Are you saying mean or
Mean. Mean. No, mean. M-E-A-N, mean, which is average. So when we started playing around with electricity, we had to come up with a methodology, if you will, to what can we compare? What's a benchmark of something that's in a neutral, natural state? Earth. Why? Because this is where we be, okay? This is where we're standing. So literally what we got is a ground rod, an 8-foot ground rod, drive it into the earth and say, you know what, you connect to that, you're connected to ground. And you're connected to zero potential. It's not positive, it's not negative, it's neutral. Why? Because it's driven into the freaking ground. So what happens is, the idea kind of caught on. So the power company out at the power pole, or your transformer if you have underground, they got a rod and they drove it into the ground. They said, you know what? We're going to sell you 240 volts AC in reference to ground. At your home, at your load, you should get 240 volts in reference to ground. The electrical generating plant, where they generate the electricity, they drove a ground rod in, and they reference that voltage to ground. So we use it as a reference to all of our voltages, which are really quite critical. I'm kind of making fun of this in a goofy way, but in all honesty, it's actually really, really critical. Like right now at my home, I've got the electrical connection coming from the power company in reference to, hopefully, ground. I get my telephone line, soon to be replaced, kicking it old school, and that needs to be referenced to ground. I've got a satellite receiver that has the antenna up on the roof. That antenna needs to be referenced to ground. The satellite receiver also plugs into the electrical outlet that should be referenced at ground, and it also needs to be plugged into the telephone connection that should be referenced at ground. Actually, when I had Comcast installed in my home, it was over the summer, I had time off, I was watching these dudes install it. And because I teach electronics, I'd always like to say, hey dude, what's going on, man? How long have you been with Comcast? These people treat you okay? What's the deal? What's your educational background? What's going down? You know, how are you doing that? If I could learn something from you, somebody that does installs all day long, I'm going to pick your brain and see what I can learn. Anyway, I see this dude hooking his freaking contraption up to my faucet. I'm like, what are you doing? He said, I'm connecting this to ground. We got to reference it to ground. I'm like, hold on, cease and desist. What are you doing? Well, I got to connect this to ground. I said, that's my freaking water connection. Well, yeah, but this is, you know, water pipe is a good ground. No. You see that right there, driven into the ground? That's a ground rod, okay? That's the same ground rod that the power company's providing me with ground. It's the same ground that everything else in the house is connected to. So why are you going to connect it to this faucet coming out all? You don't know if it's PVC inside. He really got an attitude, and I'm like, no, boom, cease and desist. I got a supervisor out there, and I had to sign paperwork, modified install. Modified install? Customer request, I want ground, and I wrote that right in there. Me want ground to be connected to ground rod. You know, so they all really got an attitude and stuff, you know, but it's kind of like, no, I mean, it really needs to happen, because especially, too, this is back in the day when you had a computer modem. You could have that modem, you could have your computer power supply, you could have all these things, and if they're not all connected to ground, they could develop a difference in potential. And if they develop a difference in potential, you know how that's going to manifest itself with highly sophisticated electronic systems?
Sparks and fire.
Not necessarily sparks of fire, it could be gremlins. It could just be real wacky behavior. All of a sudden, your satellite receiver starts rebooting itself. All of a sudden, your computer reboots itself. All of a sudden, your modem kicks you out. So when they started doing all of this inter-building networking and everything, it became a real big issue to make sure that ground was really ground. Years ago, when they built this building, well, actually, they renovated this building. Behind here, they pulled up the concrete, and they drilled down into the earth. And they put in this huge ground for the school to make sure it wasn't just a standard ground rod. This was like drilled way down into the earth. You know, you can see like the core and stuff. No, I'm just kidding. But it was pretty far down in. This is actually one of the problems that they have like in Arizona because of the sand and the desert. And we have good ground here because it's like all wet. But in Arizona, they have some problems. So I think there's some code variants down there where they're like actually connecting it like rebar in the concrete, you know, foundation and such, and they do some different stuff down there. I'm not totally familiar with it, but some of those dry climates, they have to do it. John?
How big was that? Was it a pipe or a solid?
It was, and they were actually adding chemicals to almost create like a P and an N type material there, so current would only have one way to travel through that, like a giant diode buried in the ground behind here. So I wish I had taken pictures so I could, like, I know you're not believing me, but it was like a drilling rig out there. It's like black gold, Texas tea. We're going to Hollywood, you know. Anyway, the other type of electrical ground is electrical ground. And this provides a common reference point. We use this electrical ground because the 747 taking off would look stupid with a big reel, spool of wire trailing behind it. Okay? It just wouldn't look right. So for pure aesthetic purposes, We can't do this. So we use what's called electrical ground. Your car uses electrical ground. Airplanes use electrical ground. Ships use electrical ground. And what that in essence means is a chassis ground. Now most of our home appliances use both. We ground the chassis, the electrical ground, to earth ground. So that if you have a 3-prong plug, one of those plugs, that round plug, is ground. And that's connected to the chassis. So be aware of this. In the lab, you're going to have some problems with ground because you don't understand what I'm talking about. Some of the equipment that we have in the lab is isolated from ground. So when you connect the negative lead, like on a power supply, you think you're connecting ground as a you're not. That negative, if you have a DC power supply in the lab, you have a positive, you have a negative, they're isolated from ground. They have nothing to do with earth ground. So in some cases, you could create a ground loop in there and they get wacky results with your equipment. Most commercial, consumer, industrial products are for the purposes of electrical safety. That chassis will be a ground, and that's connected also to earth ground. Question?
So electrical ground can vary from whatever you want it to be. Electrical ground.
Absolutely.
Or not.
Absolutely, and that's one of the things that can be a real problem, is you might think you get into a piece of equipment and say, oh, wow, look at this big metal, look at this big, if this was inside, this is actually a DC power supply like we use in the lab, okay? This in the back here is a heat sink. If this was installed inside some big piece of equipment like a radar system, you see this metal, you assume that, oh, this metal here, that's ground. That must be ground because it's metal, right? And all of a sudden, you know, you put your hand on there, or you lean into it, and you get electrocuted. This, in some cases, could be electrically isolated from ground. This could be connected to some big high-power transmitter tube for the purpose of dissipating energy, and it could actually have, like that mica that I passed around earlier, it could have a big sheet of that mica there electrically insulating it from the rest of the chassis or frame of the piece of equipment. And that's taken out many a good technician. So never assume. Never assume. Generally, yes. Some of the worst shocking experiences I've ever had were working on a lot of tube circuits, because sometimes those tube circuits were notorious for 2-prong, old school tube amplifier. You plug it in 2-prong, and you didn't have that electrical ground in there. All of a sudden, you go up against the chassis, and you're getting zapped by 300 volts. Make sense? All right. We talked about current. Flow of electrons in a specified direction happens at the speed of light. Voltage. And there's only 6 different methods of producing voltage: friction, magnetism, chemicals, light, heat, and pressure. We talked about voltage rise. That's the energy that we put into a circuit. Voltage drop is the voltage we get out of the circuit. Voltage rise and voltage drop should equal each other. If they don't, you got a problem. Am I being silly? Am I keeping it basic? Yeah. But you know what? I have fixed in my career dozens of problems that was the symptom. And the symptom is the equipment doesn't work right. What's the first thing that I do? Check the voltage coming in. If the voltage coming in isn't good, it's not going to work right. Then you got to find out where the missing voltage is. Maybe it's a brownout. Maybe it's a brownout. Maybe the power company, they're having a problem with generating power and giving, you know, the feed. But those two always need to equal each other. We also talked about ground. Earth ground is a freaking rod driven into the earth. Why the earth? Well, it's where we stand. It's where we live. It is what it is, neutral natural state. And we talked about electrical ground, which is typically the chassis. Could be the airframe of an airplane, which is actually kind of odd. It's kind of odd when I talk about an airplane, because what's Boeing building now? 787. What's that thing made out of? Aluminum? Composite. Think about this one. By using the chassis of your automobile as ground, you know how much wiring it saves on your car? Go ahead, make a stab at it. You know how much wiring it saves on your car? It saves half the wiring. If your car was made out of composites, and it was not a conductive material, you would have double the amount of wires on your car. Because we use the chassis as an electrical connection. Make sense? Okay, I've got a question for you, and I'm going to ask you about this in our next lecture. And I want you to discuss this in teams and as a class. Since there are 6 different methods of producing voltage, I am going to design a deep space probe to boldly go where no man has gone before. So this deep space probe is going to probe deep space. That's why it's called deep space probe. What method should I use to power this thing in outer space so that it keeps going and going and going and sending data back to Earth through a high-powered transmitter so we could monitor its journey from afar? I want you to think about this. I want you to discuss it as teams. And next week when we lecture on ELEC 110, I'm going to expect an answer from you, and it better be the right answer, or all hell's going to break loose. Any questions? Question?
Kind of in reference to the question I always wondered why radioactive materials are radiating something, right?
Yep.
I'm assuming it's radiating electrons.
It's radiating something, absolutely.
I always found it strange, like, that we were never able to figure out a way to generate electricity out of the radiation itself instead of...
Sounds like you got some good ideas that are worth pursuing. Enough said.
Okay.
We got somebody in here that's thinking. That's cool. Question?
How do you measure ground?
How do you measure ground?
In ohms.
It is measured in ohms. What you do is you have to, it's a comparative process of what you assume is a good ground. And you're basically comparing your ground, unknown ground, to that good ground. But there's an assumption made that by getting an 8-foot long rod in driving it in, that is providing you with an adequate ground. You need something else to compare it to in order for your assessment to be accurate.
So when you take a multimeter to test ground and it measures the material, does that multimeter have a
What are you measuring it in reference to?
I don't know, an electrical outlet, let's say?
Okay. What you're doing from an electrical outlet, if I wanted to verify that this is a good ground, in actuality, what I need to do here is I could measure ground against my neutral. Those two should be connected back at that box. Okay? So between the hot lead and ground, and between the hot lead and neutral, I should end up with the same difference in potential. Then going with a multimeter to that box, I should get that same difference in potential across the two. And that basically is letting me know that the ground and the neutral for that particular circuit are valid. But for you to compare a good earth ground to a not so good earth ground, I don't know how you'd go about that, other than you've got to basically know that one of them is good. And that's actually one of the things about ground too, that I don't know if any of you are aware, a lot of AM radio stations are located in swamplands. It's the best place that you could put an AM radio station, because in a swampy area you get a really good ground. So you get a really good ground plane. And because of the frequencies that you radiate at, it's going to ensure much better transmission of that RF signal. A second choice is also a field, a pasture where cows graze and urinate and keep everything nice and moist, okay, and healthy. That's why even in New York City, growing up in Connecticut, all the New York City radio stations, WABC, WNBC, WCBS, all of their transmitters were located in New Jersey, the Meadowlands. Okay, if there's any Giants fans here, it's where all their transmitters were located. Why? Because it was a marshy location. FM transmitters, different. If you're in New York City, where do you want to put an FM transmitter? Top of the Empire State Building. Why? Because it's the highest. It doesn't have as much to do. You still need a good ground, but it's not as essential as that low frequency transmitters. So ground is important, folks. We're going to talk more about it. We could have a course in ground. We honestly could. 5-credit class and just talk about ground. Testing processes, you know, some of the different things that we've encountered with ground. 50 years ago, 30 years ago, 20 years ago, ground wasn't that big of a deal. Ground right now is very, very big because a difference equates to a difference in potential, and even a small difference in voltage could create a circuit and cause that circuit to go, here's your final technical term for the night, cattywampus. All right? All right, that's all I got, folks. Have a good Okay, let's get started. Chapter 4. Chapter 4. Just kind of as a review to get us up to speed with what we've talked about thus far. We talked about the fundamental physics of electricity. Where does electricity come from, and what subatomic properties mean to both materials, the type of materials that we use in harnessing electricity and electronics, and also how materials are affected when we apply energy to them. When we apply energy to matter, we could knock some electrons free from the valence shell. When we knock those electrons free from the valence shell, that represents potential energy, right? Because we could direct those free electrons through a circuit and make them do some work for us, right? So we call that flow of electrons current. Current, the flow of electrons in a specified direction, and that specified direction is negative to positive. And every 6.24 times 10 to the 18th electrons equals 1 coulomb. 1 coulomb per second equals 1 ampere. So we talked about current already. The next thing we're going to talk about tonight in chapter 4 is resistance, or as the French would say, resistance. Right? Maybe not. Resistance. And this is kind of easy to remember. One of the questions that I'm going to ask you in the future, in lecture, is going to be what has resistance? And the answer is easy. Everything has resistance. Everything. Some things have more resistance than others, but basically everything has resistance. There's only one thing that I'm aware of that doesn't have resistance, and it only exists in a laboratory. What am I talking about? Superconductor. Superconductor. Superconductivity is the utilization of materials that have no resistance, zero resistance. So once we get that stuff up and running, once science masters that, they're going to be dealing with materials that have no resistance. And that's going to revolutionize the industry, because right now it's something we just got to deal with, and there's a lot of losses associated with it. The power companies would love to get a hold of superconductivity at room temperature. They'd love to harness that. Question?
Do modern computers have superconductors?
No. No, it is not feasible right now for any everyday use. It only exists in a laboratory at extremely cold temperatures. The use of a cryogenics. And believe it or not, I shared with you, right, what material are they having the best luck with? Ceramics. Who would have thunk? Ceramics. Ceramic, a great insulator at room temperature, but at these extremely cold temperatures, some of these ceramics take on superconductive properties. Anyway, we're not going to talk any more about that. I'd love to, but we just don't have time. What we've got to do is embark on our journey here, Chapter 4, Resistance. After completing this chapter, you're going to be able to define resistance and explain its effect in a circuit. Determine the tolerance range of a resistor. Identify carbon composition, wire wound, and film resistors. Identify potentiometers and rheostats. Describe how a variable resistor operates. Decode a resistor's value using a color code or alphanumeric code. Identify the 3 types of resistor circuits and calculate out total resistance in series parallel and series parallel circuits. Resistance is the opposition to electron flow in a circuit. What has resistance? Everything. Except superconductors. Everything. Everything has resistance. If you went out and bought a new extension cord over the weekend, even though you paid a lot of money and it's a really good high quality extension cord, it still has resistance. If you went out and bought cable for your speakers, you're rewiring your house and you're putting in some new speakers and you went out and got some of that monster cable, cost you a fortune, still has resistance. Everything has resistance. It's expressed by the symbol R. It's measured in ohms. O-H-M-S, ohms. Discovered by a guy by the name of John Ohms. Abbreviated with the Greek symbol omega. The Greek symbol omega. And although everything has resistance, the amount of resistance varies from material to material. Silver is the best, meaning it has the least found in nature. So if you went out the periodic table, played around with it and tried to find what materials on the periodic table you could find and which one had the least resistance, it would be silver. Copper is the most common, meaning it's really the cheapest. Even though it's expensive, in the grand scheme of things, that's why you got these people like cannibalizing stuff, taking stuff apart to steal the freaking wire. What took the cake was, did you hear down in Tacoma a couple months ago? They've got the that drawbridge that goes down by downtown Tacoma, the big ships go underneath. They just got in there one night and they tore it all up. The control panel, it's gonna, I don't know, it's like millions of dollars to rebuild this thing. And they just stole all the wire out of it, gutted it, and I guess started turning it into a recycling place. Yeah, I got all this wire. Sure, you know, how much?
They passed a new law where you can only get $30 max for scrap wire now, unless you have a company associated with it.
You're kidding.
I'll tell you more about it later.
Huh. That's nuts. For legitimate people.
Yeah.
That's nuts. Now, Washington or Oregon? Washington? Washington?
I think so, yeah.
Huh. Gold doesn't tarnish. So although gold is not as good a conductor as silver, by plating it, by plating copper with gold, then you get the best of both worlds. You have something that doesn't tarnish. Because the problem with silver, if any of you have any silver jewelry or silverware, about the same time you're done polishing it, you need to polish it again. Because being exposed to oxygen oxidizes it. Gold, that doesn't happen. No oxidation means you get a superior connection when you use it as a termination on an electrical connector. Resistance is affected by temperature. It is affected by temperature. Typically, resistance has a positive temperature coefficient, we call it. Positive temperature coefficient, meaning as temperature increases, the amount of resistance in a conductor increases, which is a problem. If you have an extension cord and it starts to get hot, the extension cord is going to possess more resistance. If it possesses more resistance, that means less current makes it to your load, and the extension cord is going to get even hotter. If it gets even hotter, its resistance is going to increase more, limiting the amount of current even more that's going. So that's where you end up with a vicious cycle. You let that go on long enough, you end up with an electrical fire. So keep that in mind. If you've got an extension cord or a cable that's getting warm, getting hot, it's a problem. It's also affected by size. Size does matter when it comes to conductors. Basically, the individual that has the thickest conductor will have the least amount of resistance. So earlier in lecture, when I said about connecting up your speakers using that monster cable, if you really are using monster cable and that cable is really thick, the thicker it is, the least resistance it has. The more energy you transfer from the source to the load, from your amplifier to the speaker, and that's a good thing. So generally speaking, you want to use the thickest conductor that you can afford, or of course adhere to standard manufacturing processes. And there's tables that you could find that show specifically what is required. Electrical code dictates that. In your home, the majority of circuits in your home are 15 amp circuits. They can handle up to 15 amps. Standard electrical code dictates that you need to use at least 14 gauge wire for those circuits. For 20 amp circuits, you have some 20 amp circuits in your house, maybe in your kitchen or out in your garage, your workroom, your utility room. Electrical code dictates that you have 12 gauge wire minimum. That means that the wire is thick enough to support the flow of 20 amps of current. Resistivity is the resistance of a material to current flow. Resistivity is going to be different for different materials. Even good conductors have different levels of resistivity. Here is a table that shows us the resistivity, and what we use as a benchmark is the resistivity of silver. There's a lot of things in science that we do like this. One we were talking about last week. Remember I talked about specific gravity? Remember specific gravity? Specific gravity is a benchmark that we use with fluids. And we compare everything to the specific gravity of pure water, H2O, at room temperature, typically 65 degrees, standard temperature. And we say that it has a specific gravity of 1.000. In dealing with conductors, we use resistivity, which compares resistivity to the best known conductor that we have found in nature, which is silver. So we say that silver has a resistivity of 1.0000. Copper, 1.0625. Lead, 1.3750. Gold, 1.5. And you can see the rest of the table there. This compares all resistivity of all materials. So silver has the least resistance, it's the best, so therefore it has a resistivity we use as a benchmark of 1.000. So do you understand the difference between resistivity and resistance? Resistance is measured in ohms. Resistivity compares everything to silver. Conductance, the ability of a material to pass electrons. Conductance. It's expressed as the capital letter G, and believe it or not, I'm not making this up, the unit that we measure this in is called the mho, M-H-O. It's ohm spelt backwards. And that's not by mistake. Basically, the dude that came up with this said, I'm going to spell ohm backwards, take the reciprocal of resistance, and call it the mho, and see if that makes the textbooks. Well, it made the textbooks, but it's not the unit of measure that we've adopted for measuring resistance. It is the unit we measure conductance with. It's abbreviated with the Greek symbol. It should be an upside down omega. I don't know why it gives me like an Orthodox cross. But since that Orthodox cross appeared on my slide, I'm not inclined to remove it, if you know what I mean. It may be a sign. But all it should be is an upside down omega. A guy by the name of Siemens came up with this. Have any of you heard of Siemens before? Siemens Corporation? Well, this was like great-great-great-granddad Siemens. And he made the textbooks by playing around with electrical properties. And the rest of that company, of course, is history. And what Siemens said, I guess he was in a big argument with Ohm back in the day. Ohm said, we should measure the materials all for their resistance. Siemens said, no, we shouldn't. We should measure it all for their conductance. Resistance is measured in ohms. Siemens is like, conductance is measured in mhos. That's ohm spelt backwards. Well, how do you calculate it? Well, it's real simple. What you do here is you take the reciprocal of resistance. 1 over resistance equals conductance. I mean, I guess the guy said this to his face with a straight face. So what do you say the answer is, you know? I say the answer is 1,000 ohms. Well, 1 divided by 1,000, well, that's how many mhos I think it is. And actually, since it's thousands of ohms, taking the reciprocal of it means that most of our answers will actually be in millimhos. Millimhos. Or micromhos. You can't make this stuff up. It used to be that I put out in lecture, you will never see a conductivity meter. Anytime I put out any absolutes in lecture, somebody feels compelled to prove the prof wrong. So I stated, you will never see a conductivity meter, and then almost immediately I had a student in my class raise their hand. It said, I use one every day at work. Really? I've never seen one in my life. Where do you work? And the individual worked actually at a water treatment facility. A water treatment facility. And what they use the conductivity meter for, literally, is to see how much stuff is left over in the water after they treat the water. Because I don't know if any of you realize this. Is water a conductor or is it an insulator?
Pure water could be an insulator. Non-pure water would be somewhat of a conductor, depending on how many materials it's got in it.
Very good. Very good. Pure water, H2O, pure water, basically is an insulator. Current will not pass through pure water. So if I'm in my hot tub filled with pure water, and my neighbor's wife comes over and joins me, and my wife comes home and says, wow, you look comfortable in there. Would you like a piece of toast? And throws a toaster oven that's plugged in. Provided the tub was filled with pure water, H2O, it wouldn't be a shocking experience. But due to the fact that my water chemistry, actually if I get in the tub, there's going to be salts and oils from my body that are going to contaminate that and immediately take that pure water into the conductive realm. So again, the conductivity meter that my former student was using was to measure the conductivity of the water. The more stuff you have in the water, the more conductive it's going to be. I had a terrible bout of bronchitis several years ago, the flu with bronchitis. It was terrible. The verge of pneumonia. I was coughing, fever, felt miserable. Got up, went to the doctor. It's in the middle of winter, and you know how dry our air gets in our homes in the middle of winter? He recommended I go out and get one of those humidifiers. Fill it up with water, plug it in, makes humidity. Puts humidity in the air. So I stopped at Walgreens, picked one up, brought it home. It didn't even have an on-off switch. You know, it's just a tank of water. You put the thing on, you plug it in, and it puts humidity into the air. How tough can this be? So I mustered every ounce of courage that I had because I really felt like I was dying. Filled the thing up with water, climbed under my covers, and I'm looking at the thing sitting over on my nightstand. And it's just sitting there. So I look at the clock and I continue to watch it. Nothing's happening. I'm like, you've got to be kidding me. Okay? This thing's busted? Or worse yet, I got to read the owner's manual on something that doesn't even have an on-off switch? So I go ahead and I open the owner's manual and I'm reading it and stuff. And they say right in there, if you plug this in and it doesn't produce steam in a certain number of minutes, I think it was 5 minutes, your water may be too soft. And add no more than 1/8 of a teaspoon of salt to the 2.5 gallons in the tank. Any more than this could corrode the electrodes, blah, 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 blah. So I'm like, you know, I'll read the instructions. I'll follow the instructions. But I don't think 1/8 of a teaspoon of salt in 2.5 gallons is going to make much of a difference. So I got 1/8 of a teaspoon, which is a pinch. I mean, that's just a pinch of salt. Put it in there, plugged the thing in, got back under the covers. By the time I was tucked in under the covers, I look over, the thing steam's pouring out of it. That small amount of impurity was enough to make that water conductive, because those don't boil the water. What they physically do, they're electrodes, and they flash it to steam. So its operation is contingent on having water that has some impurities in it. That being said, what does it say about our water, tap water here in Western Washington? Really good water. What's that?
Depends on where you are.
Really? Where are you that you don't think the water's that good?
Well, Redmond.
All right.
There's,
They're getting it out of the slough out there, don't they?
it also depends on which side of Redmond you are. They get 2 different water supplies.
Generally speaking, though, here,
Some of it's not.
yeah, generally speaking, here in Western Washington, in the Northwest in general, we have pretty good water. If any of you have ever lived in Southern California, I mean, I was buying bottled water back there before bottled water was in vogue. You know, I was buying bottled water because it tasted like it didn't have a taste to it. That was
Hard water there.
super hard, yep. In the Midwest, I mean, you know, I stayed with a cousin of mine that lives in Missouri once, and, you know, get the water softener, you got like stalactites and stalagmites in the shower, you know, because all the minerals that are, you know, I mean, it's just crazy stuff. It's very hard on plumbing. I grew up on the East Coast, actually on artesian well water, until the city came in and finally, you know, but water was perfect. So there's some areas of the country that are really bad, but keep that in mind. Pure water, H2O, is an insulator. So we have to add some impurities to it to be able to convert it. Now, everything has resistance, but we in electricity and electronics have a component that is designed to have this property of resistance. And amazingly enough, you know what they call it? The resistor. So a resistor is a specific device designed to possess the property of resistance. It's designed to have resistance. It's designed to possess a specific value of resistance that's predictable. Comes in 2 different classifications. One is a fixed value, meaning what you see is what you get. And the other is a variable value. Variable, meaning we can adjust it. Variety of shapes and sizes to meet specific circuit, space, and operating requirements. So there are all kinds of resistors on the market. These components all have a tolerance associated with them. Tolerance is the amount that the resistor may vary and still be acceptable. The larger the tolerance, typically the cheaper it is to manufacture. Now, believe it or not, in electronic components, we could have values of tolerances that go anywhere from plus or minus 20%, 10%, 5 to 1%. But 20%, can you imagine that? Everybody get their taxes in on time? How do you think that would go over? Here, IRS, I did my taxes and I think they're accurate within 20%. Think that'd go over pretty big? What about if your employer said, here's your paycheck on Friday, but plus or minus 20%, we're not really sure if it's accurate, plus or minus 20. And if you're on the plus side, cool. But if you're on the negative 20, it's...
Isn't that technically 40%?
No, either plus 20 or minus 20. But it's a difference, yeah. Well, I don't even know if it's a difference of 40%.
Yeah.
Is it? I guess it would be.
Because you go 20 negative and you go 0, then 20.
Yeah, but yeah.
So the total-
But the way we say it, so we're allowed plus 20 or minus 20, but it's a difference, yeah. Of if you've got a 100 ohm resistor, keep the math simple, right? That means that resistor out of the package could be anywhere from 80 to 120 ohms, and it's still okay. You got what you paid for. So it's kind of wacky thing here because I make you follow all these procedures and policies here, dot your I's, cross your T's, make sure your paperwork is accurate. You're answering to your team lead, the class lead. We have all this protocol here and everything. I expect your answers to be very, very accurate. But when you get over here to the lab, when you get out into industry, you're going to find that you're working with components that have tolerances up to plus or minus 20%. Very, very frustrating. It's actually one of the challenges that I had in this industry. Because in here, everything we talk about is theoretical, perfect. In industry, it's at plus or minus 20%. And it's okay. It's okay. So keep that in mind when you're working with any of these components. Some of the different types of resistors, we have molded carbon resistors that are made out of carbon, that is, molded. It's the most commonly used. It's inexpensive, and it's manufactured in standard resistor values. By standard resistor values, what I'm talking about, like how tires come in different sizes? I'm sure you could, if you wanted to go take a machine class and then make your own wheels on a lathe or whatever, on a milling machine down here. You could make your own wheel. Whatever size you want, knock yourself out, you could make your own wheel. Can you find a tire that's going to fit your wheel? Probably the first thing that you would do is look and see what standard tire values are and then make a wheel, if you're going to make a custom wheel, that fits standard tire sizes. Because you're going to end up making a wheel that you can't even find a tire for. Make sense? So resistors are the same thing. When we say they come in standard sizes, they come in standard sizes. Don't expect to go out and find a 103.5 ohm resistor. Don't expect to find that on the market. You could go buy a package of resistors that are 100 ohm resistors that are plus or minus 10% and start going through and see if you could find one that's 103.5. But an engineer is never going to specify and say, I want a 103.5 ohm resistor in the circuit. They'll say, I want a 100 ohm resistor. Standard sizes. Another type of resistor manufacturing process comes up with what's called a wire wound resistor. These are used in high current circuits, and they are made out of wire that is wound. Because we know that wire has resistance, so If I get a certain amount of wire in one turn, then I can make another turn and get twice the amount. And it's literally how it works. The resistance of these varies from a fraction of an ohm to several thousand ohms. Question?
When you were talking about the tolerance, and you were saying if you bought a 100 ohm resistor and you found this 103 point something, will that tolerance change, or will that resistor constantly be 103?
It could change over time. It could. Typically, it's going to stay pretty close to what it was. But again, since these heat up, things could change in the composition of it and alter its characteristics. But that's not a big factor to worry about. There's a lot more components in electronics that are a lot more sensitive than resistors. Good question.
Does the tolerance add up? I mean, because if you have 3 resistors and you got 20% of both of them, all 3 of them, that's 60%.
Yeah. The question is, do tolerances add up? Is there a cumulative effect? Yes. I worked as a contract employee for a biomedical company before I came to teach here at Lake Washington, 20 plus years ago. And this unmentioned biomedical company, I was working on this product, and it was a pretty expensive motherboard. And every component, this board kicked my butt. I could fix these boards pretty much, a lot of them were common problems. I'd look at the symptoms, kind of hold it to my forehead. Let me guess, resistors, R22 needs to be replaced. I'd replace it, fire it up, the thing works okay. I had this one board that I couldn't fix. I just could not fix it. And when I looked and evaluated the integrity of every component was within tolerances. But when you put it all together, one tolerance was pulling it this way, another tolerance was pulling it that way. When you put it all together, the board would not work. It was an anomaly because everything individually functioned. And I kind of got in trouble over it. It was kind of like my ego, like, I'm not going to let no stinking board kick my butt. And believe it or not, this company had it figured out where every circuit board, a technician was allotted basically 0.65 hours to troubleshoot it. So what I would do, if I was given a big production run to do on racks, what I would go through is fix all the easy problems first, and then go to the next easiest problems and work my way so that when I was done, I had all the real difficult problems left. And then I'd look and see how much time I had left statistically. See, a lot of you, I don't even think realize that this is how you're measured when you get to industry. They know exactly how long it takes to fix this board. Okay? So if it's 0.65 hours and it takes you 3 hours, you're going to have a discussion with the boss. You're in the wrong profession. You're in the wrong. So anyway, I knocked out all my boards and I ended up with like 4 days left. So I could go take breaks for 4 days, goof off, and still end up statistically ahead of the game. But I wanted to fix this board. I ended up screwing around with this board for two and a half days. And then finally, my boss saw that, I don't have a lot of boards. What are you doing? I'm working on this board. This thing's kicking my butt. I've been working on it 2.5 days. 2.5 days! Got the thing, threw it across the freaking floor. We're not paying you to screw with that. And I never was able to fix it. But what it was, again, were tolerances pulling in different directions. So sometimes you could have something that individually everything is functional. You put it together, integrate it as a system, just doesn't work. Why? Because of what you said, tolerances pulling in different directions.
That's a pretty uncommon situation, though, huh?
It's probably more common than we think. But yeah, generally speaking, it's uncommon. And that's why I'm not mentioning the name of this company. One of the things that they did is the majority of boards that were rejected were because of this capacitor that they used 20% tolerance capacitors. And the circuit would not tolerate that. It had to be right in the zone. So what I would do is I would go to stores and I'd get a bin of capacitors. I'd sit there and then I would test every one and basically sort from 20% tolerance to like a 5% tolerance and keep those capacitors. So when I ran into that problem, I would just unsolder that cap, put the new cap in. Employees wrote a beneficial suggestion to the company saying, why don't we just buy 5% tolerance capacitors and all these things wouldn't have to be reworked. You don't know what you're talking about, just do your own job or whatever, instead of looking at the big picture. I think it was like, production manager, I think his brother-in-law sold cheap capacitors for a living or something, and he was buying them by the semi-load, or it just made no sense. They just made apps. This is a well-known biomedical company. It's kind of like, why are you doing this? Why not just use a tight tolerance component to begin with and avoid somebody having to solder and unsolder and repair these boards? It's costing them a ton of money. But what do I know? Film resistors are becoming increasingly popular. There's 3 different types: carbon film, metal film, and tin oxide film. And by film, what we mean is a manufacturing process that lays down a thin film of this material on a substrate, and then that becomes the resistive material. So it's some of the manufacturing processes actually are on par with manufacturing solid-state semiconductor devices. Surface mount resistors, ideal for small circuit applications, available in both thick and thin film. If you're working with surface mount resistors and you have a package open and you sneeze, they're gone. So don't sneeze near a package of open, because these are tiny. Some of these are almost the size of a head of a pin. Tiny, tiny components. That's what goes into making your cell phones and digital watches and TVs on your wrist that you could watch and all of that kind of stuff. We also have variable resistors. Variable resistors allow resistance to vary both linear and logarithmically. Linear and logarithmically. When I say linear, do you know what I'm talking about? Linear. Linear means a straight line. So if I have something on a linear scale, if I adjust it a little bit, I get a little bit of response. If I go to 100%, I get 100%. If I go to 50%, I get half. If I go to 25%, I get a quarter. Make sense? That's linear. It's a straight line. Logarithmically is on a curve. It's on a logarithmic curve. So if I turn a little bit, I'm not necessarily, the whole response is on a curve. Does anybody know why we would want to have a control that is not linear, that intentionally puts things on a curve for us?
Isn't it mainly with audio? One I know, isn't it? I believe in the second one.
Very good.
To do with audio.
Logarithmic is used for audio applications because audio is not linear. Audio is not linear. Audio, some of you may be aware, is measured in decibels, and that's on a logarithmic scale. So if you want to control something that is nonlinear, you need to use a control that's nonlinear, and audio is that example. So that's why we have this logarithmic control. One of the things, if you're shopping for these variable resistors, you may also see it say audio on the box because it's for use with audio. So volume control on a radio, on a stereo, would be a logarithmic control because it's controlling something that is nonlinear. And what we're trying to do is get somewhat of a linear response out of it, right? When you turn the volume all the way up to 100%, you expect to get 100%. When you turn to 50%, you expect to get 50%. But since audio is nonlinear, we need to use a logarithmic control to get a linear type response. Make sense? These variable resistors, when they're configured as a potentiometer or pot, also known as pot, a pot. When we configure it to control voltage, we call it a potentiometer. And I'll show you how we do that in a second. But I want you first to hit the I believe button. What type of a device do we use to control voltage? Variable resistor do we use to control voltage? The answer is potentiometer. When we use a variable resistor to control current, we call it a rheostat. We call it a rheostat. And basically the way that this thing works. What I just illustrated here on the board is a resistor, right? And what I've got here is I've got terminal A and I've got terminal B. When I put my meter across terminal A and B, what am I going to measure? The resistance. The resistance between A and B. The total resistance. You all agree with me with that? Okay. So, if I go ahead now and connect this up to a circuit, this is the negative terminal. This is the positive terminal. Okay? Current is going to want to flow in a counterclockwise direction here. And it's going to flow through this resistor. And when it encounters this resistance, it's going to limit how much current flows through this circuit. Do you agree with me with that? Okay? So, if I go ahead now, this is a fixed resistor. If I go ahead and turn this into a variable resistor, a variable resistor has a third lead on it. And I'll label this terminal C. So I have between A and B is my total resistance. And then I have C. And what this is a wiper arm. This is a wiper arm. And physically what it's going to do is move up and down and come in contact with either more resistive material or less resistive material. It all depends on your perspective. If I have this adjusted right now, smack dab in the middle, how much resistance do I have between A and C? Half. How much resistance do I have between C and B? Half. If I adjust it, just barely touch it, just a little bit. Now I'm 49% on one side, 51 on the other. Tweak it more, I'm 40-60, right? 80-20, 90-10, 99-1. So I'm moving this wiper arm coming in contact with a different amount of resistive material. You all agree with that? Does that make sense? Okay. Now, in this particular configuration, I could move this wiper arm up and down all day long. Am I going to have any effect on current flowing through the circuit? Why?
It's just one circuit.
It's just flowing between point A and point C. Excuse me, point A and point B. Point C is effectively not even part of the path. So I can move that wiper arm. Hey, look, Mom. Right? Nothing's going to change. Nothing's going to happen. Now, what if I break this connection here and come and move this and connect to point C directly? Now what's going to happen when I move that wiper arm? What's that? Total resistance is going to change in the circuit. Absolutely. If I adjust this thing all the way to the end right here, I may have what? 100%? Well, if I move it all the way here and it's not in contact with any resistance, 100% current flow, zero resistance, or as close to zero as I could get. When I move the wiper arm all the way to the bottom here, now I get 100% resistance, minimum current flow. So literally, when I'm adjusting this wiper arm here, I'm adjusting the amount of, you said it, current in the circuit. So I've got this configured right now as what? A rheostat. A rheostat. So when I'm using only 2 terminals of a 3-terminal device, I've got it configured as a rheostat. When I adjust my wiper arm, I'm literally adjusting the total amount of resistance, and that total amount of resistance is going to affect the total amount of current flowing in that circuit. Make sense? I'm going to disconnect this, reconnect this, and let's assume that I'm going to make another connection over here, and this is going to be a voltmeter. I'm going to connect a voltmeter between A and C, and I'm going to connect a voltmeter, another voltmeter, why? Because they're cheap, right? Between B and C. When I have this adjusted smack dab in the middle, what voltage am I going to get across this voltmeter? Half. I like you. You're keeping it basic. Half. That's the way I want you to keep it, you know. I ask that question, I see somebody going for their calculator, you know. It's like, I haven't given you any numbers. You can't calculate this one. If I've got it set smack dab in the middle, I'm going to get half my voltage here, which means I'm going to get my other half voltage down the bottom. Okay? So if this is 10 volts, I get 5 volts here and 5 volts here. As soon as I begin to move that wiper arm slightly, now I'm that 5149, 6040. But I'm not talking about resistance. Now I'm talking about what? Voltage. So when I connect all 3, I could use this as a voltage divider. 100% of the voltage that gets applied between A and B gets divided proportionally between the wiper arm and the outer terminals. When I have it configured like this and I'm dividing voltage or controlling voltage, we call that a potentiometer. This is how the volume control on your stereo is connected. This is basically what you're doing. And that voltage that you're controlling is going typically to a transistor. And it's telling that transistor, here's more voltage, I want you to amplify more and make the music louder, or turn it down and make the music softer. I'm going to give you less voltage to the amplifier, the transistor. And this is how it works. So keep that in mind. That's how we say we're either controlling current or voltage. Could I use a potentiometer as a rheostat? How would I do that? Only connect 2 of the terminals. So if you go to Radio Shack and say, do you have any rheostats here? That would be a fun question. I should give you that as an out-of-class assignment. Everybody go to Radio Shack and ask if you got any rheostats. And they'd probably scratch their head and bring in, oh, but we have some potentiometers. You could use a potentiometer as a rheostat. You only need to connect 2 of the terminals. If you went out and special ordered a rheostat, and it came in the box and it said rheostat, could you use a rheostat as a potentiometer if it only came with 2 terminals? No. You need that 3rd terminal to be able to divide the voltage. Make sense? Okay. Resistor identification. There's a couple different methods that we use to identify resistors. Does anybody know the easiest method of identifying resistors? I love it. Now, the easiest method is when they put the value right on the outside of it with numbers and letters. I always sucker people in with that one because everybody knows resistor color code. Now, the easiest method is really when they use numbers and letters and they just say if it's like a 1,000 ohm resistor, you know, 1 K ohm. It's right in there in black and white. You read it, you're good to go. Another method that they use is alphanumeric code. And for a lot of these resistors, you're going to have to, like a secret agent, use a decoder ring or a decoder chart to figure out exactly what the code means. The third easiest method is the color code. And of course, you can't have a successful career in electronics unless you understand the color code. First thing we're going to take a look at here is that alphanumeric code. If you looked at a small resistor and it had an RN60D5112F on it, and you came up to me and you said, "Hey Joe, what kind of a component is this?" I would probably hold my head and say, "I have no freaking idea." What you're going to have to do is you're going to have to call up this code and decipher it. If you work at a company, see, this is one of the things. This is a very difficult job. It's a tough job I got. I got to train all of you generically, but what happens is when you go to your specific industries, you're going to see some of the same components day in and day out, because you're going to get used to your company's product line. But here it's very difficult. I'm teaching you generic electronics, and there's a lot of different schemes that are, that they use. This is one of them. So the RN60 identifies the resistor style. What is it? Carbon comp, wire wound film. The D are its temperature characteristics. How does this behave? And they'll normally include some tables or charts in there to say, for every 5 degrees rise in Fahrenheit, this is how many ohms it's going to change. So it's going to be its temperature characteristics. Question?
Different manufacturers use different codes?
Yes, yeah.
So this right here is not
No, don't memorize this. The point of this is that you're dead in the water unless you get the code. The 5112, that shows the resistance value. The 511, the 2 represents the number of zeros at the end. So this would be 51100. Putting that in most common terms would be 51.1 K ohms. 51,100 ohms. And the tolerance would be F. I don't know if that's good, bad. You're going to have to look it up and see what it equates to. 5%, 2%, 10%, 20%. I don't know. But that's how you would decode that if you saw that on the side of the resistor. If you saw colors on the side of the resistor, well, there they are. You've got this in your book. The way the color code works, you have your first band, second band, third band, fourth band. If you have a resistor that's, well, first thing you want to do is hold it so that one of the bands is closest to the edge. You normally want to put that closest on the left and then read it like a book. If I had a resistor and I held it in my hand and it was orange, white, red, gold. Orange on the color code equals the number 3, white is the number 9, red is the number 2. So that means I'm going to add 2 zeros after the 39, 3900. And gold means it's a 5% tolerance. Putting that in most common terms means this would be a 3,900 ohm resistor or 3.9 K ohm resistor, 5%. Question?
We have to memorize this one.
I hate the word memorization. Question is, we have to memorize it. You got to know it. You've got to know it. And to be honest with you, a lot of job interviews, they're going to ask you to do that. The best thing, though, I'm not going to go out of my way. I'm going to be honest with you. I'm not going to go out of my way on a quiz to hammer you on it. You're not going to fail this quiz because you don't know the resistor color code. One of the big things with the resistor color code is simply your experience doing your labs. You're going to come to learn this. And the more you work with it, you're going to understand it and you're going to remember it. But I don't want to make flashcards. Other programs do that. We could give you flashcards and identify this resistor. I could keep you occupied and entertained but then when you're all said and done, you're ready to go get a job and identify resistors for a living. Not a lot of money in that. So this is just something that you need to learn, you need to know, you need to be able to decode it. Make sense?
There's also acronyms that'll help you memorize.
I'll let you study the acronyms at your own leisure in a group form. See, I'm ex-Navy, and we had some acronyms that basically if I repeated here, I would be handcuffed and dragged off. And
Start with bad boys.
that was one of them.
Yeah, that's one I learned.
It was a lot of, so I'll let you discuss some of these amongst yourselves. And they do work. It's actually funny because having interviewed potential faculty member, I'll of course always throw in there, identify this resistor, and you see some making charts, and I've never once given anybody a resistor, what size is this resistor? Oh, that's a 1.2K 5% resistor, Actually, if somebody identified it, I'd probably, you're a freak of nature, But it is something that, again, through experience, you're going to get used to, and when you're prototyping a circuit, you're going to say, I'm looking for a 1.5 K ohm resistor, and you find it, you plug it in your circuit, and you move on. So, resistors and circuits. Resistors are typically configured in a circuit in one of three different ways. Either series, parallel, or compound. And to be honest with you, I hate to let the cat out of the bag, put the cart before the horse. But you know what? In the entire world of electronics, in the entire universe of electronics, there's only three types of circuits. And here you are, week number 3, learning about them. It's that simple. The most complex circuit you ever work on in your life will be one of these three. It's either going to be a series circuit, a parallel circuit, or it's called a compound circuit.
Also known as a series parallel circuit, right?
Or a combination, yeah. The first circuit we're going to talk about is a series circuit. And the simple thing to remember with a series circuit is resistance is additive. Resistance is additive. So, the formula that we need to remember, and this is not accurate, this should have an equal sign right here. There's an error in this formula. It should be RT, total resistance, is equal to resistor 1 plus resistor 2 plus resistor 3 plus etc., etc., etc. If you got 5,000 resistors in a circuit, you're going to have 5,000 resistances to add up. It's cumulative. So in this particular circumstance, all we have to do is pick a point in the circuit and start to count. We'll start right here at the negative terminal. The first resistor I encounter has 30 ohms of resistance. 30 plus 20 is equal to 50, plus 10 is equal to 60. That completes the circuit. In this circuit, there are a total of 60 ohms of resistance. Does that make sense? Sounds real basic, doesn't it? It's all fun and games until you have a bad battery connection right here. There's some corrosion that adds some resistance. You got a bad solder joint right here. It adds a little bit more resistance. So in a theory class like this, how many ohms of resistance are there supposed to be in a circuit? 60. You get in there and measure it with your meter, and you get 67 ohms. Then you realize you have tolerance of these resistors. Did you take that into account? Yeah. But that only accounts for a small percentage based on that. Then all of a sudden you realize, well, I've got corrosion in the circuit. Or I've got a bad solder joint in the circuit. So that's where there's a disconnect sometimes between the world of theory that we live in here in a classroom, a lecture environment, and the world of reality in the lab. That's why I want to see all of you getting in the lab, doing your lab assignments. Because you're basically going to start scratching your head saying, hey, I kind of believed what Joe was saying in lecture, but it isn't quite working like that. It's going to work like I say, but there's going to be also a lot of variables that take place in the lab and in the real world. As I said before, that's the toughest thing that I had when I got out into industry. I went through a bunch of theory schools. When I started seeing things for real, I was like, whoa, this doesn't make sense. Is this good? can this possibly be good? This doesn't look like a good reading. I mean, it's not what the book says. How could this be, so that's the only way of getting that is experience. Any questions on series resistance? Parallel. This is my favorite slide of the entire quarter because, like, watch, I'm going to hit the key and the formula is going to fly in from the side. Ah. Ah. Isn't that cool? You ever see how people like abuse PowerPoint and use too much animation? This is just right. All right? And I'm going to do it one more time. It's the last time I'm going to do it. The entire quarter. The last slide that I have that's animated is this slide. Okay, you ready? Ah. Just kidding. One more time. Ah. Now, in order for us to calculate out the total resistance in parallel, this is kind of different. This is kind of odd, right? What we're going to do is this reciprocal formula. The reciprocal of resistor 1 plus the reciprocal of resistor 2 plus the reciprocal of resistor 3, on and on and on. That sounds awful familiar to me. What is the reciprocal of resistance? Conductivity. Remember that? 1 over R equals conductivity. Siemens, measured in mhos. So what we're saying here is by adding up all of the conductivities of all of these branches to a parallel network, then taking the reciprocal of that, we end up with total resistance. So this is kind of like a bar trick. How can you add resistors to a circuit and yet make the resistance of the circuit less? The answer is add them in parallel, because that's exactly what we're doing here. It's exactly what we're doing. Think of this as the Seattle traffic system. Seattle traffic system. Okay? This is it's a Friday afternoon before a 3-day weekend, and these are all the people that are in Seattle, and they want to get to Bellevue. And they've got multiple paths to take. How do you get from Seattle to Bellevue? 520. How else? I-90. How else? Up and around the north end of the lake, or down around the south end of the lake. So basically we got 4. Let's just talk about 3 for the case of our example here. If you're in Seattle, I'm a big commuter, so I like these analogies. They really work well for me. They work all too well for me. If I'm in Seattle and I want to get to Bellevue and it's a Friday 3-day weekend, what path is probably going to be the best for me to take and why? What's that? No. If I'm in Seattle and I want to go to Bellevue, 3-day weekend, which is the best path for me to take and why? Why?
Most lanes.
Most lanes. It's going to move the most traffic. It's got the least amount of resistance. After I-90, what would be my second choice? Before the toll. The toll will quickly make this number 3 choice. At least for me. I'm a tightwad. I'll take the ferry to Vancouver and drive down around before I get a boat. 520. 520 has fewer lanes. It's got more resistance. It doesn't move the same amount of traffic. And then finally, the other option is driving around the north end or the south end of the lake. Not an easy way of doing it. A lot more traffic, less flow. So comparing that now to this, we could say that I-90 is like the equivalent of 10 ohms of resistance. Because even though I-90, it's a super interstate highway and it's got multiple lanes, does it still have resistance? Oh yeah. Oh yeah. If it didn't have resistance, there would never be any brake lights on it. This would be like, 520 would be like twice the amount of resistance, meaning it moves half the amount of traffic. And then the north end of the lake, 3 times the amount of resistance, meaning even less traffic. Does that make sense? So every one of these is a viable current path. Every one of those routes is a viable traffic path. Let's say, for example, that Bill Gates, he really wanted to give back, and he loves the people of the Puget Sound region. And he wants to build another bridge across Lake Washington. And he is so into it, he's even going to let the bridge like come off of his property. Okay? And because he's building the bridge, it's going to be called the Bill Gates Memorial Bridge. When he builds that bridge across Lake Washington, what's it going to do to this flow here? What's it going to do? It's gonna make the overall circuit have less resistance because he built another viable path. Is the path he builds going to be perfect? Is it still going to have resistance? Yes. But is it going to have an overall effect on increasing the flow in the Seattle metropolitan area of traffic? Absolutely. So that's how we can add resistances on this circuit, yet lower the overall resistance of the total circuit. And that's why we have to use this formula. We're actually adding up the conductivity. We end up with the total conductivity for the circuit, take the reciprocal of that, that gives us the total resistance for the circuit. Make sense? Okay, now I'm going to give you some thumb rules. Thumb rules. The first thumb rule that I want to give you, it's very, very important. When you're analyzing a circuit like this, the total resistance of the circuit will always be less than the value of least resistance. If not, you made a mistake. Plain and simple.
So you can guarantee the total resistance will be less than 10 ohms?
Absolutely. And if you come up with something other than that, you're done screwed up. Plain and simple. So the total resistance of a parallel network will always be less than the value of least resistance. And your assumption is correct. In this circuit, it's got to be less than 10 ohms. The other thumb rule that I'm going to give you is if the values of resistance are all equal, you simply count up the number of resistors, take the resistance, and divide it by that number. As an example, if R3 is 30 ohms, R2 is 30 ohms, and R1 is 30 ohms, 30 divided by how many resistors? Equals 30 divided by 3 equals 10. The answer to this is going to be 10 ohms. That's a thumb rule. So if I've got 4 100 ohm resistors in parallel, 100 ohms divided by 4 equals 25. If I have 2 50 ohm resistors in parallel with each other, 2 50 ohm resistors, 25. 50 divided by 2, 25. So that's a thumb rule, only if the values are equal. So a lot of times in the lab, you may be looking for a certain value of resistance. I need 20 ohms of resistance. Or you could put 2 10s in series with each other. Or you could put 2 40s in parallel with each other. So there's a couple different ways of doing it. It's one of the reasons we're teaching about this stuff. Make sense?
Not yet. I'm just trying to synthesize it into a formula now.
Okay.
Add up all the resistors and then divide by,
The number of resistors. Only if they're equal. This only works if they're equal. It's a thumb rule. You don't need to use the thumb rule. It's just another tool in your toolbox to make it easier for you. If you doubt me, well, you could always use that formula. There is another formula I want to show you. It's not in the book, but I want you to know it, learn it. This is called the product over sum formula. Product over sum. This only works if we have two resistors in parallel with each other, period. Two resistors in parallel with each other, period. So this literally is the product over sum. The product is R1 multiplied by R2, R1 times R2, divided by R1 plus R2, the product over the sum. This works if you only have two resistors in parallel with each other. If you've got two or more resistors, you have to use this formula here. I just drew it a little bit differently, but that's basically the same formula. The reciprocal of R1, which is the conductance of R1, plus the conductance of R2, plus the sum of the conductances, total conductance, the reciprocal, 1 over the total conductance, equals the total resistance. So this formula works for two or more resistors in parallel. This one here works for two resistors in parallel, period. The reason I want you to start using this is because in the future we're going to take this formula and we're going to adapt this formula for some other use. So it's better that you just learn it now and it's another tool in your toolbox. Product over sum, easy enough to remember. Product over sum. When we execute the math on this formula here, the reciprocal of R1 plus R2 plus R3, we add those conductances up, take the reciprocal of it, we end up with 5.45 ohms. Does that answer sound right? Why does it sound right? It's less than 10. Works for me.
In that slide, could R3 be considered Rn as well?
No. Rn would be like R4, 5, R22, R447. R to the nth degree means to the nth degree. That this formula works to infinity. If we keep adding resistors in parallel, we just keep adding the reciprocal of that resistance on it. That's what we mean by that. So they drew it like this, plus 1 R to the nth. I did it, etc., etc., etc. This is a complex circuit. Now again, I know you want to do the math, you want to get it right, that's cool, okay? I want to keep things real, I want to keep things basic. The first thing that I notice in this circuit is that these two resistors are in parallel with each other. So this is an actual ideal situation for us to use this product over sum formula. 50 times 25 divided by 50 plus 25. Why don't we just do it right now? You got your calculators? Let's do it. Just do it. But I want to do it in stages here for those folks at home. This is how I'm going to start off with the formula. Now what I'm going to do is substitute in my numbers. What is that, 50 and 25? So it's going to be 50 times 25 divided by 50 plus 25. Okay? I know that this is going to, 50 plus 25, I could do that in my head, right? That's 75. Okay, but the 50 plus 25, times 25 equals 1250. So 1250 divided by 75 equals 16.67 ohms. So does everybody see how I did that? Isn't that a cool formula? It's cool. I like that formula. I don't know why. Because the answer's always like, come out? I don't know. I like that formula. You can do the same thing down here and you're going to get the same results. So I know that I've got, and the way I want you to look at these parallel circuits, the way that I want you to think of these parallel circuits is how much resistance is there between this point here, and that's actually called a node. A node are where two or more wires are joined together. How much resistance is there between node A and node B? So to lay this out mathematically, the way that I would actually calculate out this whole problem is RT for this circuit, total resistance, is going to be equal to the resistance of resistor 1 plus the resistance between node A and B plus the resistance of resistor 3. 4? 4, thank you. That's why this is a dry erase board. So R1 plus RAB plus R4. Now before I could solve for this, I'm going to have to calculate out what RAB is equal to. RAB is going to be equal to R2 times R3 divided by R2 plus R3. You agree with that? So then it's just a matter of me, we already did this, this is 16.67 ohms plus 30 ohms plus 20 ohms. Gives me my total amount of resistance in the circuit. So I highly recommend, until you really got a handle on this, you lay it all out like this. Oh, there's so many formulas, whatever. Don't look at them as formulas. These are tools. These are tools. Yeah, they're formulas, but they're tools to solve the problem, to unlock the key to the problem. Use the right tool, you get the right results. Use the wrong tool on your car, you strip the nut. Use the right tool, you get about the results that you desire. Make sense? When you first see a problem like this, though, one of the things that I'm going to stress in this program is that you keep it real. What was this total resistance going to be between this A and B? It's going to be less than 25. So I've got 30 ohms here and 20 ohms there. 30 plus 20 is 15 and less than 25. What do I know my answer is going to be? Less than what? Less than 75. If you could do that in your mind looking at this stuff, I want you on my team. I'll be honest with you. I want you on my team. Those are the people that I want. If I give you this problem and immediately you're with the calculator and I don't mind if you use the calculator, but if you're turning it upside down, you're sideways and no. What I want out of all of you is to look at this. I got 30 ohms here, I got 20, that's 50. 50 and 25, less than 25, my answer is going to be less than 75 ohms. Do not try to take my quizzes doing that. If you do, you'll probably be very successful with a lot of my quizzes. I could take most of my quizzes and not even use a calculator and get them all right. Well, that has something to do with the fact that I wrote my quizzes. But what I want you to do is that thumb rule as a litmus test at the end, or even before you calculate it. I should get less than 75 ohms as an answer. My answer should be less than 75 ohms. I came up with 66.7 ohms. Does that sound about right? If you come up with an answer of what's the total resistance in a circuit, 1,250. Well, that's not less than 75. Houston, we got a problem. There's probably a math error. If I were Pope of Electronics, I would require you to all get 100% on all of these quizzes. Because if you use the right tool, you get the right results. Make sense? In summary, we talked about resistance. What has resistance? Everything. Everything. We talked about specific devices that are designed to possess the property of resistance. It's known as a resistor. Can you imagine some dude wakes up every day and instead of it's off to make the donuts, it's off to design the resistors. There are engineers in the world that design resistors for a living, huh? Whew. Talk about a career path. Resistivity, that property that we compare the resistivity of everything to that of silver. Silver, the best conductor found in nature. Conductivity. Conductivity, the reciprocal of resistance, measured in mhos, or typically millimhos. Resistor identification for fixed value, variable values. We talked about fixed resistors, variable resistors that can be configured as potentiometers if they're used to control voltage. Rheostats if they're used to control current. If I'm using 3 leads, I'm using it to control voltage. If I'm using 2 leads, I'm using it to control current. And then finally we talked about circuit configurations. First was a series configuration. In a series configuration, how do I determine total resistance? Simply add it up. It's additive. In a parallel circuit, how do I determine total resistance? Add up the reciprocals. Sounds like I'm adding up the conductivity of the paths. In a compound circuit, what do I got to do? Both. Thumb rules for parallel circuits. Total resistance will always equal less than the value of least. And if I have like resistors, same size, then I could simply take that number, take the value, divide it by the number of resistors that I have, and that'll give me the total resistance. Any questions out of this chapter?
You add up the resistors or you just divide it by?
In parallel, you got to divide it out. So if I've got 4 100 ohm resistors, it's 100 ohms, 100 ohms, 100 ohms, 100 ohms, 100 divided by how many resistors? 4. 100 divided by 4 equals 25. I should have approximately 25 ohms across that circuit. All right, let's go ahead and take about a 12-minute break. And we'll start up at about 10 after. Chapter 5, Ohm's Law. Again, we should hit a gong, ring a bell, ring some chimes. Ohm's Law. Ohm's Law has more of an effect on being able to predict the behavior of electricity than really anything else. Does anybody know how predictable the behavior of electricity is, percentage-wise? We were talking about tolerances last chapter. Anybody know how accurate we could predict the behavior?
I'll say 100%.
100%. It's a bold statement. It's absolutely correct. 100%. You use Ohm's Law, you could predict with 100% accuracy what's going to take place inside a circuit. It's pretty powerful. It's a pretty powerful tool. especially when you're going to be paid to go out into industry and fix broken electronic equipment. You got this tool working for you, you got something. After completing this chapter, you're going to be able to identify the 3 basic parts of a circuit, identify 3 types of circuit configurations, describe how current flow can be varied in a circuit, state Ohm's law with reference to current, voltage, and resistance. Solve problems using Ohm's law for current, resistance, voltage, and series parallel circuits. Describe how the total flow differs between series and parallel circuits. Describe how the total voltage drops differs between series and parallel circuits. Describe how the total resistance differs between series and parallel circuits. State and apply Kirchhoff's current and voltage laws. And verify answers using Ohm's law with Kirchhoff's law. First of all, electric circuits, or the path that current follows, is called an electric circuit. All circuits consist of, and this is important, and it sounds really basic and it sounds very simplistic, but I'll tell you what, knowing this helped me on my worst day of my career as an electronics professional. Because it's so easy to get turned around and lose track of what the problem is. And if you could get back to basics, you're always going to do well. The basics are all electric circuits must consist of a voltage source, a load, and a conductor. The voltage source is the source of your electric energy. Could be any of those 6 different types that we talked about last week. The load is what converts one form of energy into another form of energy. An example of an electric load would be a light bulb, a motor, a heater. It converts electric energy into light, heat, motion. A conductor. A conductor, electrical conductor, transfers the energy, the electric energy, the current, from the source to the load. You have to have those 3 parts of a circuit, or it's not a circuit. I'm going to add 2 other optional parts that are not in the book. The other optional device, most circuits have them, not all do, is a controlling device. A simple example of a controlling device is a switch. A simple example of a complex controlling device is a microprocessor with 1.9 billion transistors on it. So you see, that's where we're going in this course, by the way. From one switch to 1.9 billion switches in a microprocessor. Controlling device is used to control the flow of current in the circuit. And the 5th optional device that you could have inside a circuit is a protective device. An easy example of this is a fuse, a circuit breaker, a fusible link, a thermal circuit breaker. These are all examples of protective devices. So, on my worst day of my career as an electronics professional, it involved a nuclear submarine someplace we weren't supposed to be, and it involved, unfortunately, my equipment that I was responsible for. There were 3 of us that were responsible for that system. Big system. $16 million system. And that was like in 1982 dollars. Expensive. This system was sold to the Navy, and it was designed with what was called graceful degradation. That means bits and pieces could fail, and the whole system would keep up and running. That's what the vendor told the Navy when the Navy bought the system. So here we are someplace we're not supposed to be, doing stuff we weren't supposed to be doing, and it was showtime for my equipment to do its thing. Didn't work right. Didn't work at all. As a matter of fact, it was totally down, 100%. And the captain, like, Mr. Gryniuk, how can this be? The system was designed with graceful degradation. It should never be 100% down. Well, Skipper, it's like this. It's totally busted. I don't care what you got to do. I want you to fix it. And we literally worked on that system nonstop, 3 days in a row. Stayed up. Popping no-dos, drinking coffee, just working on it. Two other guys, they finally gave up. They're like, we just cannot fix this. It's not fixable. It just cannot, we can't bring it back from the dead. I went back to these basics. It's an electronic system. It's made up of nothing but circuits. Circuits have a voltage source, they have a load, you have interconnected with conductors, have controlling devices, and have protective devices. Is something not doing what it's supposed to be doing? It's got to be. That's what's causing the problem. It's narrowing it down. And I stuck with the problem. I ended up fixing the problem. Saved the day. Whoop-de-doo. I basically did my job and fixed the equipment. But I had to take a couple steps back and say, here's a $16 million system. Fills half a room with equipment racks. None of it works. Can I verify the voltage sources for everything? Can I narrow it down and say this stuff's not working, but this stuff is working? Can I look at the loads? What's not working? What's not converting electric energy into the form of energy that we need to be getting out of it? So if you know all of these systems, then you're going to be an effective troubleshooter. But always go back to basics. Okay, God forbid you get out of class tonight, go out to your car out in the north parking lot, turn the key, and you've got an electrical problem. If you do have an electrical problem, approach it like this. Do I have a good source? Is my load functional? Is it the interconnects? Can I prove that the interconnects are viable? Is it a controlling device? And to be honest with you, in this day and age, most of the problems we encounter are controlling devices. Okay? It's not a simple switch, toggle switch. That was easy to troubleshoot. I do a lot of traveling. I forgot what brand car it was. I got the rental car. I flew in, it was the East Coast, and I'm there late at night, and I got in, and I'm like, I couldn't figure out where to put the key. Where do I put the key to start the car? There was no place to put the key. And I'm looking at it. You know, I got a little flashlight, and I'm looking, there's no place to put the key. I didn't need a place to put the key. The fact that the key was on my person was good enough for the car. I just hit the start button. Ooh, it started. All right. So the controlling device there was the fob, right? RFID talking to the computer saying this is a valid operator to be inside the car to operate it. Kind of a complex controlling device, but a controlling device nonetheless. And of course, protective devices. And sometimes wacky stuff is done with protective devices. I was working on my TiVo about a month ago. I had problems with my TiVo, and I've got an older TiVo. It's a direct TiVo. So it's got two dual receivers, so I could record 2 shows and watch another show. It's non-HD, because I don't have HD. I don't want to pay for HD. I'm a cheapskate. Okay? Feed my nice plasma screen. High-resolution plasma screen with my basic signal. It's great. It's great. It's all good. My TiVo crapped out. Okay? So all the TiVo is got a hard drive in there. So I got a new hard drive. I configured that and everything. And I was just through putting it together, and something happened, and I heard a pop, and all of a sudden TiVo wouldn't fire up anymore. And I'm like, oh man, if this thing is dead, I don't want to go out and buy a new DirecTV DVR. And I'm grandfathered into paying the older TiVo value. And plus, quite frankly, I don't know if any TiVo users here, TiVo's the bomb. It truly is, because it could do word searches and all kinds of additional stuff that a normal DVR will not necessarily do for you. So I wanted to bring this thing back from the dead, and I'm like, what the heck? I was pretty ticked off, because I already wasted a whole weekend screwing with this thing. So I'm looking through the circuit for something obvious, and I find this device, and basically it's got shrink wrap, black shrink wrap over it, and 2 leads coming out of it. And I measure across it, and I'm getting an open. I mean, I just got in there with the thing unplugged and I'm poking around. What the heck is this? So anyway, I unsolder it and I inspect it, and with an X-Acto knife, I cut the heat shrink up. You know what it is? It's a fuse. It's a fuse, and the manufacturer tried disguising it by putting a piece of heat shrink around it and sticking it on the circuit board, and that's what was burned out. I found a suitable replacement that I had at home in my tin can, soldered it back in place, fired it up, I was good to go. TiVo's been working nonstop ever since. Okay? But that's a hidden. A lot of companies do that type of stuff. So that if you don't know, if you're not the authorized service center, you don't know to get in there and even check that. I've seen some companies that will encapsulate a fuse inside silicon or epoxy. You don't even know what's in there. So keep your eye open for all these basic parts of a circuit. I know this sounds basic and I'm beating it to death, but I tell you, you will deceive me in the future when you get in the lab. And it's going to be, I can't fix this. The problem's too complex. It's never a complex problem. It's usually a real simple problem. Very rarely. All of you are here. You want to get into advanced electronics and work on sophisticated equipment. The problems with sophisticated equipment are always very, very simple. Okay? You gotta follow this protocol though. So use this as a checklist. This is a series circuit. We talked about series circuits already. The most important thing for you to remember about a series circuit is that current is constant in a series circuit. The most important thing to remember is that current is constant in a series circuit. Meaning, I've got a resistor here, a resistor here, a resistor here. These three resistors cumulatively add up to the total amount of resistance in the circuit. This electrical pressure here encounters this total resistance and allows this amount of current to flow. This current has to travel the entire path of the circuit. That is the most important thing about a series circuit, period. The second thing I want you to remember about a series circuit is also known as, like FBI lingo, AKA. A series circuit is also known as a voltage divider. A voltage divider. What voltage gets divided up? The total voltage. Remember this? We call this voltage rise. How many voltage drops do I have in this circuit? This circuit. 3. So voltage rise is going to get divided into 3 proportional values. The biggest resistance gets the biggest voltage drop. The smallest resistance gets the smallest voltage drop. And the resistance that's just right gets a voltage drop that's just right. Make sense? That's the series circuit. The parallel circuit, the most important thing I want you to remember about the parallel circuit is that voltage is constant across a parallel network. This is a parallel network. Here there are 3 resistors in parallel with each other. The voltage rise will be distributed equally across all 3 branches. So whatever this is, if this is 120 volts, this is going to have 120 volts across it, this is going to have 120 volts across it, this is going to have 120 volts. Kind of like how your house is wired. Your house is wired in parallel. Each of the outlets has the same voltage across them, or they should. If not, you got a problem. That's the most important thing about a parallel network. A series circuit was also known as a voltage divider. A parallel circuit is going to be known as a current divider. Because what happens to current in the circuit? This total current here gets divided here, at this node, and here. Then current gets divided here and here. The current flowing through R3 and the current flowing through R2 join up at this node and flow on to this node. This current plus this current equals total current. Series circuit, current's constant. Series circuit, also known as a voltage divider. Parallel circuit, voltage is constant, also known as a current divider. Complex circuit, well, that's got both going on. I've got current division going on here in my parallel network, and I've got voltage division going on here between this resistor and this resistance. This resistance. The best thing you could do in this circuit is label this A, node A, or in B, or X and Z, or whatever you want to label it. Give it some, I like using letters, because numbers typically equate to components. Letters I could use to, and there's no rule on this, but it works for me. So I'm going to label this node A and this node B. The resistance between node A and B is equal to the product over sum of R2 and 3. Remember that? Studied that last chapter. The total resistance of the circuit is going to be equal to R1 plus RAB. This voltage drop, RAB, plus the voltage drop across R1 equals RT. Voltage rise, and really, how many voltage drops do I have in the circuit? Really, how many voltage drops do I have in the circuit? 2. And what are they? R1 and RAB, or R2 and R3. If I say R2, it's really the same thing. R2 is the same as R3. You could argue and say, well, you really got 3 voltage drops here. You got a voltage drop here, you got a voltage drop here, and you got a voltage drop here. Well, this voltage drop and this voltage drop are the same voltage drop. It's the same difference in potential. So it really, I don't want to call it different. It's the same. Make sense? Some different circuit conditions that I want to talk about. And this is very important. I want you to use the proper terminology with me. It's part of why you're here at Lake Washington Technical College studying this stuff, is to learn to speak another language, the language of electronics. The circuit condition that I want to talk about is called a closed circuit. Is a closed circuit a good thing or is it a bad thing? Depends on what you want. Thank you. Depends on what you want. Right now, the circuit in this room for the interior lights is closed, meaning the circuit's energized and we have an appropriate amount of illumination in here. That's a good thing. If I go and operate the switch and try to open the switch and the lights won't go out, that could be a problem. That could be a problem. If you're operating an electric tool and you try to shut it off and you can't shut it off, that's a problem. Be a closed circuit is causing you a problem. I had this problem with a pressure washer. One of these $100 pressure washers, Costco special. Great pressure washer, okay, for what I do. Got a patio, I got a deck. I don't need a, 40 horsepower, fire-breathing, peel the paint off the Queen Mary pressure washer. But it's my pressure washer, and I like it. I got a lot of tools. Got a lot of neighbors that know I got a lot of tools. My neighbor Tom, he since moved. It's another story. I'll tell you about that some other time. Finally drove him out of the neighborhood. Tom's an engineer, an electrical engineer with Boeing. Hey Joe, I'm going to stain my deck. Can I borrow your pressure washer? I'm a nice guy, but I hate loaning out tools because nobody takes care of stuff like I want it taken care of. I mean, if I borrow somebody's tool, I take care of it 10 times better than my own. And if I break it, I buy it, I replace it. I said, Tom, that's fine. I'll loan you my pressure washer. But, only plug it in a dedicated outlet. And do not use any extension cords. Because it's right on the label. It's not that I'm that smart a guy, I just read the label, the tag that's on it. Because this motor requires a lot of current to be able to turn and be effective. You plug it in an extension cord, it doesn't get the right amount of current. Remember that whole thing, the cord gets hot, the hotter it gets, the more resistance, less current, the less current, the hotter it gets. It's a vicious cycle. So I loaned him my pressure washer. How did it work out? Oh, pretty good. Thanks, Joe. Fast forward a couple weeks later, I go out to wash my sidewalk. I plug the thing in, turn it on, and it's on. Continuously on. It won't shut off. Normally what happens, it's a real simple circuit. This switch right here on a pressure washer, one of those cheap Costco specials, what it does is there's a water pressure sensor. When the water pressure builds up, what it physically does is open the switch. So what you do in the handle, when you release the switch, you release the pressure. As soon as you release the pressure, you close the switch, you turn your motor on, the motor turns the pump on, and you're pressure washing. You release the trigger, you build the pressure up, you open the switch. Mine will never shut off unless I unplug it. If I unplugged it and it still kept operating, well, that'd be something. Keeps operating. I ripped the thing apart, and what had happened was, I guarantee you, I didn't see him do it, but because I had no problems with it, and I had it for years. He plugged it in a non-dedicated circuit, it built up a lot of heat, and physically the switch, the contacts got welded. I took the switch apart, the contacts were welded to each other. That's how hot it got. So I went to my file cabinet, opened the drawer, pulled out the manual, got the parts list, contacted the company. The new switch would be $65 plus shipping. A new pressure washer at Costco, $109. I could have it right now. The old one's in a landfill somewhere, after I cannibalized some parts off of it.
You talk to your neighbor Tom?
No, I ran him out of the neighborhood. I finally ran him out of the neighborhood. There was a chainsaw involved. Trees falling. Long story. Long story. No, actually what pushed Tom over the edge was he had problems in his basement, flooding, split level house, and water would get in. So what he did is he dug a trench around the entire foundation of his house. And then what he's going to do, he's going to put a treatment on the outside concrete. And then he was also going to backfill it, put in drainage and everything. So he had this ditch dug. It was a lot of backbreaking work. He did it all by hand. Got to respect that. But it took him forever to do it. It took him years to do it. So I used to accuse him of having a moat. It's like, Tom, what's the deal with the moat? So anyway, again, I had a buddy of mine over, and it was the wee hours of the morning, and we were enjoying some libations and some cigars. And actually, my buddy, who's got my sense of humor, he's like, "Hey, Joe, is that Tom's moat? What's up with that? Doesn't he want that thing full?" I'm like, "That's a good point. Why have a moat if it's not?" So anyway, we turned on his garden hose and started filling the moat, and then we're just laughing and like busting a gut. And then Tom came out. He's pretty freaking ticked off that we're filling his moat with water. I mean, he woke up to the sound of running water. Like, why is water running in my house? And hey, man, we thought we were doing you a favor by filling your moat. He was out of there within 6 months. Open circuit, is this good or bad? Depends. On my pressure washer, this would have been highly desirable. When pressure builds up, it opens the switch, interrupts the flow of current to the motor, right? Another circuit condition is called a short circuit. Have you all heard of a short circuit before? God bless my wife. But she's been my wife now for a long time. And I've been in this industry since puberty. So, hanging out with a guy that teaches electronics and does electrical stuff, you'd think something would rub off. Constantly, I get a call, and it's kind of like, the blender's not working. I think it's got a short circuit. And I'm like, holy crap, you tell short circuit to me, I'm like ready to call the fire department. I mean, short circuit is like what you see in Star Trek when they get hit by a phaser, that's a short circuit. That literally is what a short circuit is. A short circuit will cause an electrical fire. And then on further probing, well, what exactly is the blender doing? Well, I plug it in, I hit the button, but nothing happens. Oh, you mean it's an open circuit, not a short circuit. Big difference. The majority of household appliances that I've encountered that have failed have failed because of an open circuit condition. That's where nothing works. Now you got to be careful because sometimes a short circuit will cause a protective device to open and render the piece of equipment dead. So you've got to get in, and like that DirecTV, that was dead. That was open intentionally. I found the open. It was that fuse with heat shrink around it, trying to disguise it to make it look like a fuse with heat shrink around it. Make sense? So keep that in mind. Open circuit, short circuit is always bad. There's never an intentional reason to short anything. Current flow in a circuit can be varied by changing the voltage applied to the circuit. As voltage increases, current increases. As voltage decreases, current decreases. And also changing the resistance in the circuit. As resistance increases, current's going to decrease. So these first values, we call these directly proportional, right? If voltage increases, current increases, directly proportional. Voltage decreases, current decreases, directly proportional. Resistance increases, current decreases, inversely proportional. Now in the beginning when Ohm gave his sermon, I don't know if it was a sermon, Ohm's Sermon on the Mount. Somehow I think I'm getting my history messed up. This is what Ohm said. I think this speech was given down at the King Dome. And he was at the King Dome, and he got up, hello, hello, hello. This is, I'm the happiest man alive. Because, I know, Ohm's law. Y'all ready for this? E is equal to I times R. And the crowd went nuts. 45,000 people on their feet. Ohm's law. Ohm has spoke. Actually, I think I'm getting my history mixed up a little. I don't think it went down like that, quite like that. So this is Ohm's law. This is what Ohm really said. Voltage is equal to current times resistance in the circuit. And of course, instead of the letter E, we could use the letter V. V is equal to I times R. Now, remember that trick that I showed you with the triangle? T in the center? Let's put this in that. V, I, R. So now you've got all the other variables. If I ask you how much resistance is in there in a circuit, you cover R up. It's voltage divided by current. If I ask you how much current is there in a circuit, you cover up the I and you say it's V over R. If I ask you how much voltage is there in a circuit, it's I times R. So by knowing that one formula, you can figure out all the other algebraic manipulations of it. Does that make sense? So in essence, that is Ohm's law in all of its variables. Or variations, I should say. Algebraic variations. So you don't even need to be a math whiz to be able to do it. Ohm's law states relationship between current, voltage, and resistance, or I is equal to E over R. Or E is equal to I times R, or R is equal to E over I, however you want to look at it. But, in the beginning, it was V, or actually E is equal to I times R. 45,000 people on their feet, applauding. The man with the beret. I don't know if he wore a beret or not. If I was Ohm, I'd wear a beret. Some of the algebraic formulas, if you will. And when I say that, I know there's some people in here that cringe, like, oh, I got to know all this math or whatever. All this is a recipe. That's all this is. By laying it out like this, it shows you how it needs to be laid out to explain the behavior. In a series circuit, the same current flows throughout the circuit. Total current is equal to the current through resistor 1 plus the current through resistor 2 plus the current through resistor 3, etc., etc., etc. It's a fancy way of saying current is constant in a series circuit. Total voltage is equal to voltage drop across 1, across 2, across 3, etc., etc. This is a fancy way of saying a series circuit is also known as a voltage divider. Total resistance in a circuit is the sum of the individual resistances in a circuit. This is a fancy way of saying you got to add it all up. Resistance is additive in a series circuit. In a parallel circuit, total voltage is constant across the parallel network. That's this formula. Down below, total current is equal to IR1 plus IR2. This says that a parallel circuit is also known as a current divider. Oops, that is. That's that other formula, right? The reciprocal of the sum of the reciprocal of the resistances equals the reciprocal of the sum of the reciprocals equals the total resistance in the circuit. Because when we add resistors in parallel, what are we doing? We're actually adding up the conductivity of the individual branches. To determine unknown quantities in a circuit, you can kind of use this as a checklist. Draw a schematic of the circuit. You got to start off with a schematic of the circuit. If one has not been provided to you, you need to draw one, okay? Because just troubleshooting circuits off the top of your head doesn't really work well. Got to be looking at the big picture, pun intended. Label all known quantities. Sometimes you may need to get these known quantities from manufacturer data sheets. Solve for equivalent circuits. Solve for equivalent circuits. Redraw the circuit. When I say redraw the circuit, remember like when we were dealing with a parallel network, two resistors in parallel with each other? You could redraw that circuit and just show one resistance. Two resistors equals one resistance. I could do a simplified, you want me to do a simplified drawing of my car electrical system right now? Want to see this? Battery. Car. And to be honest with you, I'm not being silly, I could redraw every circuit on my car and come up with an equivalency, and this is what it is. And I'll tell you what, if you go out to your car and you turn the key and there's nothing, and you open the door and the dome light doesn't come on, nothing works in the car, and all of a sudden, this is exactly what you've got, and there's an open in this circuit, and it's a pretty big open, or your battery's dead. I don't think your whole load is dead. It's like, oh my goodness, oh, my load is dead. Oh, I got to replace the load. Save the battery, but we're going to... You know what I'm saying? Doesn't work like that. But do you see the power of troubleshooting like that? What's working in the car? My car's dead. What do you mean it's dead? It's a conversation with my wife. The car's dead. What do you mean it's dead? It's dead. When you turn the key, does it click? No. No. When you open the door, does the dome light come on? No. Oh, it's dead. But you got to ask those questions because it's different. When you open the door, the dome light comes on. But you turn the key, does anything? Do you hear a click or anything? Immediately you're troubleshooting. You're narrowing it down to what circuits perhaps could be faulty. So redraw to simplify. There's another big law out there. It's Kirchhoff's law. G.R. Kirchhoff extended Ohm's law with two important statements. Kirchhoff's current law, the algebraic sum of all currents entering and leaving a junction is zero, equal to zero. Kirchhoff's law is kind of like this. Everybody know the intersection down here at the bottom of the hill? Okay. Let's say that you're a traffic cop and you're directing traffic down there in the center of the intersection. Okay. And you got 3 cars coming at you this way, and you got 5 cars coming at you this way. In a few moments, how many cars are going to be going away from you? 8. Because 3 are coming from one way, 5 are coming the other way. You know, chances are cars don't come and then, oh, we were just kidding, we're going to back up. You know, I mean, I've seen them do that down here. But generally speaking, you know, 3 plus 5 equals 8. Pretty profound, isn't it? That's what Kirchhoff came up with. And he made the textbooks. You laugh. His name's in the textbook. My name's not. That's Kirchhoff's current law. And what Kirchhoff is saying is, again, the total current entering has to exit. And it's really a profound troubleshooting tool. Because what you could do is I say, I've got 3 amps of current flowing at me, and I've got 8 amps flowing away from me. What does that tell me? I must have 5 more amps coming in from another direction that I'm not aware of. And there's only one other circuit, so I must have 5 amps. And I tell you what, you could take that information to the bank. It's a law of physics. And it's so powerful in troubleshooting. It's extremely powerful in troubleshooting. There was a guy that was in my division, one of our techs in the Navy. Goofy guy. I'll tell you some stories about him and his wife in the future. But this dude, it just, you know, every day was a mystery what you'd see this guy into. So military equipment is put together really, really, really well. And we didn't have cordless screwdrivers, so you used to have to take stuff apart by hand. So I come in and I'm like, you know, what are you working on? He's like, yeah, we got a problem with this unit here, and I want to take this current reading, you know. And, you know, in order to take a current reading, I got to open the circuit. So you're going to remove this access plate here with 64 screws. And you're going to remove that. You're going to get in there and take that reading. You know, why don't you use this here, which is called Kirchhoff's law, okay? You got this amount of current going this way, this amount of current coming in, and the unknown is what you want to measure here. You could use Kirchhoff's law and determine with 100% accuracy how much current's flowing through that point. You don't have to take the panel off. You don't have to remove the screws. You don't even have to use a meter. You could use math. Put the meter down. Math. Solve the problem. And to be honest with you, these are the technicians that I look for. These are the technicians that I want to hire. If you start the troubleshooting process with the manual, and then you're going through tracing, redrawing, applying these principles, these laws, before you go ripping into stuff, you're going to save yourself a lot of grief. A lot of grief. It's like going to work for Boeing. Boeing builds big airplanes. On the tail of their airplanes, they put a light that blinks, so other airplanes don't hit their airplane when it's flying. You know, I'm not making this stuff up. It's kind of like the light doesn't work. Well, let's get a man lift and get up there and take it apart and whatever. You get a man lift, you get all harnessed up, you know, you're 5 stories in the air, you're manipulating the controls, and all of a sudden, oops, you put a dent in the rudder. When you could have done some troubleshooting, probably through an access panel down below, using Kirchhoff's law. How much current do I have flowing up there? What's going on? Then make some determinations. Is it really essential for you to get up there and take that assembly apart? Get a man lift, harness yourself up, run the risk of plowing into the rudder accidents happen. So always look at that kind of stuff. Is there an easier way of going about getting the reading that I want? That's the power of Ohm's law. That's the power of Kirchhoff's law. Kirchhoff's law also has a voltage application. And Kirchhoff says the algebraic sum of all voltages around a closed circuit equals 0. This is a fancy way of saying voltage rise equals voltage drop. And you know how much you're left over with? 0. We talked about this last week, didn't we? We talked about this last week. If you put 12 volts in, how many volts are going to get used? 12. If you're troubleshooting and you can only account for 11.5 volts, that half a volt is somewhere that it doesn't belong. You got 120 volts are supposed to be coming out of these outlets. If you plug it in, you only get 98 volts. Something's wrong. If you could go to that box and prove that you got 120 across each leg, but you go to an outlet in your home and you get 98, something's wrong. You find where the missing voltage is, you find the problem. So again, does this sound really basic? What goes in must come out. It is. But I'll tell you what, when you get to industry, you'll deceive me. You're going to get your head all, wow, it's complex. I never worked on one of these before. Oh, sheesh, it's got to be something really, it's got to be the flux capacitor must have failed. You know, and I missed that day when Joe talked about the flux capacitor. No. Keep it basic. Keep it basic. The fundamental parts of the circuit, the source, the load, the internal wiring, the controlling device, the protective device. You got to be able to prove every one of those parts, functional parts, is functional. And how are you going to learn how to do that? In the lab, by doing your labs. Theoretically, how are you going to come to appreciate that? By attending a lecture and doing your written assignments. Because that's what this industry is about. It's about the written theory, which is kind of cool. Some of you had back-breaking jobs in the past. Okay? I never worked a hard day in my life. Actually, I did, but it was all mental. And I'll tell you what, there were days working on my system. That's the other thing, too. You know, it's one of the reasons that we all try to treat you as professionals here in this program. When you go to industry, you're going to be professionals. If your equipment ain't broke, they don't care what you're doing. But when it's broke, they expect you to be there bringing it back from the dead. No questions asked. Well, I'm a union guy, and do I get time and a half? Fix the freaking gear. Get it up and running. That's all they care about. And actually, there are some union maintenance jobs that, you know, do pay you well if you've got to put in that overtime. But generally speaking, this is where you make your money. This is the most, I tell you what, I'm taking a lot of time with this chapter. This is one of the most important chapters of the book. It's one of the most important chapters of this entire program. I could talk for a week about just this chapter. And you know what the beauty of it is? You've all been here. This is your third week in this program. Do you understand what I'm saying? Do you understand what I'm saying? The message isn't going to get any worse. It's not. The most complex electronic systems could be rapidly troubleshot, keeping these fundamental skill sets in mind. Ohm's law, Kirchhoff's law, 5 basic parts of a circuit. Is my source good? Is my load good? Is it the interconnects? Can I prove that? The other thing you got to do as a technician is just pay attention to what can you check quickly. What can you check quickly? Again, like my former esteemed colleague on the submarine, Mike Wyrup was his name. Wyrup, weird name. Okay? He'd be the kind of guy like, well, you know, I think it's the wiring, Joe. I want to do continuity checks. I mean, you're talking these big multi-pin connectors, and you're going to disconnect, you check the continuity. It could take months. You really think that's the problem? You really think a wire like broke in the middle of the night behind that equipment rack? You know, I don't think so. I think it's, you know, maybe something like controlling device. Have you tried reloading the software? You know, the version of software that we have in that safe. Why don't you try reloading the version of software? Controlling device is what I'm thinking, right? Reload the firmware, software. Reboot the system. See how the problem manifests itself. Oh, Joe, the most amazing thing happened. Reloaded the software, started working. Wow. Good thing you didn't take, 6 months and check the continuity of all them wires in the back of the equipment rack. What would the odds have been? In summary, the electric circuit contains a voltage source, a load, a conductor. The 2 optional ones, controlling device, protective device. Don't second guess those. Hey, want another troubleshooting hint? Another type of protective device? It's called a resettable fuse. Resettable fuse. A lot of consumer electronic products, DVD players, VHS players, stuff like that, tuners, TV tuners, have these resettable fuses. And a lot of times what happens is the device will not work. So it's kind of funny. You know, my family, they all know, you know, Joe in the family, he's the electronics guy. You got a problem, you know, and they always call me with the problem. So it's amazing how many things I've fixed from afar. They tell me what the problem is, you know, and a lot of these have been with DVD, VHS players, things like that in the past. So, well, what I'm gonna have you do is I've got a ritual that I'm gonna go through here on the West Coast. Okay, I want you to unplug that device, okay? And what's the most comfortable chair you have in the house? I want you to remove it and put it in the most comfortable chair of the house overnight. And I've got some rituals and some telepathic, you know, things that I'm going to do. And then I'm going to call you back in the morning and let you know when I'm done. Okay, and I'll go plug it in. Holy cow, it works! How did you do that? You know. It's all about chi. Okay. Freaking resettable fuse. For whatever reason, there was a glitch that tripped that. You got to unplug it, totally discharge the whole unit, plug it back in. It reboots thinking it's back at the factory. The first day it was ever made, problem goes away. You got to make sure you give it overnight to be able to do that. So I've brought back countless. I've had a lot of people come in here, colleagues. Hey, Joe, my amplifier, this amp doesn't work anymore. You could have it if you could fix it, okay? Because I went out and bought a new one. I figured this thing is toast. I go plug it in, it works. By you unplugging it, you fix. I don't even go into it with people. You'd be surprised the amount of stuff that you could fix by simply unplugging it for 24 hours, plug it overnight, not even 24 hours, plug it back in, you're good to go.
Why does it take time? Why wouldn't it be instantly?
Because these resettable fuses, there's a time delay before they're actually solid state devices, before they physically reset and allow the circuit to function properly again. So you want to get it back to that neutral state of when it left the factory. I don't know, in mobile audio, did you encounter any of that stuff? Where by disconnecting it for a period of time would fix the problem?
Yeah, I mean, when if you did a hard reset, touch positive, negative together, make sure the circuit's completely unenergized. Mm-hmm. Airbag lights, mm-hmm. Some control systems, if you did a hard reset, would do that.
Okay.
To make sure that everything dissipates inside. So the fastest way was to...
Yeah. And that's the other thing that you can do even with like a DVD player. If you just not unplug it, make sure it's unplugged, and then keep the leads shorted together, then that's a kind of a fast track. But still, there are some capacitors we'll talk about in the future, store energy in the form of an electrostatic field that may keep stuff alive for a considerable amount of time. So, flux capacitors. Current path. We talked about series circuits, parallel circuits, and complex circuits, series parallel circuits. We talked about current flow, negative to positive, varied by changing the voltage or the resistance. We talked about Ohm's law. And also determining unknown quantities in a circuit, as well as Kirchhoff's law. For current is constant in a series circuit. Ohm's law. All the current entering a node must exit the node. Kirchhoff's law. Powerful, powerful stuff. Prevents you from removing 64 screws by hand to take one reading. He used to think I was an a-hole. This here is Kirchhoff's law, you know. I stayed awake during that class. You could use this here tool to prevent yourself from removing 64 screws. Gryniuk, you're a freaking jerk. No, I'm not. I think the guy that's removing 64 screws and then's going to strip the screws, okay, break the heads off. That's another story. There was a dude, a local company, can't make this stuff up, okay, broke heads of screws off. The product's ready for shipping. Got freaking instant glue, glued the heads back on. First time it was out in the field, and they took a panel off for maintenance, snap. What the heck is this? What is that on there? They look at it. It's like, this is instant glue. Who worked on it last at a company? Why'd you do that? But, well, I didn't want to get in trouble. You're out of here, you know, that instant. You can't make stuff like this up. Try to avoid it. Questions?
Electricity is a theory, right?
Yes, and that's basically what we're studying is the theory.
Ohm's and Kirchhoff's laws, rather than theories.
Laws of physics. We have proven that although this is theory, these are laws of physics. Voltage, the relationship between voltage, current, and resistance, the relationship between voltage, current, and power, Kirchhoff's laws, they're laws of physics. We know that we could prove with 100% accuracy that this is how they behave. Okay. Mr. Graham.
Also, in science, generally, a theory is something that is provable almost to an infinitesimal degree, and a postulate is something that's unproven.
Very good. Thank you. Okay, hey, before we wrap things up, because we got another chapter to do, okay? But fortunately, one of the reasons that I took this amount of time here is this other chapter is not a chapter that I am going to lecture on. It's another chapter that you've got to watch some videos on. There are 4 videos. When you go to the Google site, it's going to say, follow this link to watch test equipment videos. Okay? And there are 4 videos that I want you to watch. And you're responsible for the information. I think all of you kind of figured out that I'm the kind of guy that likes lectures. Okay? I like to have fun with lecture. Hopefully you're not falling asleep during my lectures. But I like lectures. And it gives me quality face-to-face time with all of you. However, that being said, I'm not the smartest guy, but I know that a picture is worth 1,000 words. So if I could have you watch a 15-minute video, that's a lot of frames. That's a lot of pictures. That's a lot of data. More time than I have to preach to you about this stuff. The 4 videos. The first video is going to be a basic introduction to digital multimeters versus analog meters. Okay? The analog, when I speak of analog, this is what I'm talking about here. Kicking it old school. The digital meter is going to be based on a Fluke 70 series meter that, quite frankly, all meters are really measured against. The second video is going to talk specifically about how to perform resistance and continuity measurements using an analog meter and a digital multimeter. Resistance and continuity. The third video is going to talk about measuring current and voltage. So by the end of those 3 videos, you're going to know how to measure resistance, current, and voltage. If you know how to do that, let me tell you, you got it going on. You got it going on. Because those are 3 of the big 4 properties that all of this is based on. So these are very, very important videos. One of the reasons that we have them on videos and uploaded is so that you can watch over and over again to make sure you understand exactly what the process is. So by the time you get into the lab, you can apply that. Very, very critical. Like how to defuse a nuclear bomb. You want to get it right the first time. Okay? The 4th video is produced by Fluke Corporation. How many of you know about Fluke? Okay, Fluke is the real deal. The real deal. Expensive, local company. John Fluke. John Fluke, former submarine guy. Right? Got to support his product. He was before my time. But yeah, John Fluke is a former submariner. They produced this video, and it's a drama, not a drama like, oh, I can't believe he's going to test the voltage. It's got a story behind it. There's a kid who's working on the job, and he blows up something, and his boss is like, you need to go out to the community college and talk with the electronics professor. And basically, it reviews how to perform basic measurements, resistance, current, and voltage with a Fluke 70 series DMM. That's the 4th video. So all of the information in those videos is testable. The link is on the Google sites. You can watch it in the privacy of your own home. You can watch it on these machines. But that is what we are doing in lieu of this chapter on test equipment. Does anybody have any questions on anything that I covered tonight? Yes?
So you just go to Google and type in something?
No, the Google site. It's the sites that were in the syllabus.
Oh, okay.
Okay? This right here, if you go to that Google sites, the electronics, LWTC electronics, you're going to see a link in there. Follow this link for test equipment videos. You click on that, and then it brings you to some server in Peru that we've uploaded those videos to. We got stuff all over the place. But you know what the alternative is? You got to sit here and watch it all. Okay, we've really tried. I got my TAs working very, very hard to get as much stuff as we can uploaded to the web so that you could look at this stuff morning, noon, and night. Any other questions on anything in general? Okay, make sure you get that video watched over the next 24, all those videos watched over the next 24 hours. All right, a chapter that I really like talking about. It's chapter 7. Because the title is Power. And I like power. I like power. Remember, what was it, Tim the Tool Man? Remember power? You can never have enough power. You know, the gas-powered blender. I think it's a great idea. You know, if you've ever mixed any frozen concoctions, having a little bit extra power there to chop that ice up and, you know, get just the perfect consistency is not a bad thing. So I've never driven a car. I've never driven a car that's had too much power. I think, actually no, and I did have the opportunity. I went through Richard Petty's driving school 2 years in a row. This is probably about 10 years ago. And I thought these cars would have governors on them. You know, you go through and they're going to turn some goofball like me loose in a, you know, in a Winston Cup car at the time. No governors. That car had a lot of power. Okay, put in the right hand. It scared. I got to drive Las Vegas Motor Speedway, and I turned the. I'll tell you the whole story sometime, but I got the fastest times of the day. I was at the top of the reader board, Joe Gryniuk, you know, it was pretty freaking cool. So I was thinking about quitting my day job and becoming a NASCAR driver. So luckily I have good friends that, you know, woke me up to reality. But the power was fabulous. So I think, though, as much as I love aviation and aerospace, you know, I see the Blue Angels in town, I look at those F-18s, and knowing my own piloting skills, and I think I'm a pretty good pilot, but knowing my own pilot skills, I'd probably last 5 or 6 seconds in one of those things before there'd be a fireball going down the runway. A little bit too much power for me. Power in electronics is in electrical is very, very important because it's the metric that we use to determine output. It's the metric that we use to determine efficiency. It's the metric that we use to show us how much energy we're converting into work. So this is a really big chapter. If you fully understand the implications of power, you're going to be a better technician. You truly are, because looking at inconsistencies in power output is going to start to paint a story, tell you a story, and paint you a picture of what's taking place with a system. So with that being said, let's jump and immerse ourselves into Chapter 7, Power. After completing this chapter, we're going to be able to define power as it relates to electric circuits, state the relationship of current and voltage, solve for power consumption in an electrical circuit, determine the total power consumption in a series, parallel, and a series parallel circuit. Now, power relates to the rate at which work is being done. Relates to the rate at which work is being done. Work is done when a force causes motion. I'm sure my kids, I got 3 kids, 3 boys, you know, they're all like grown. The youngest is going to graduate the UW here in June. Business finance, he's going to make a bunch of money and then like hire me to like hang out with him. He's going to do really well. But my kids probably all think I'm a jerk because I know stuff like this. You know, we'd have, you know, family cleanup day around the yard. And I'm out in the front yard digging ditches and doing whatever, and the kids are in the backyard supposed to be raking leaves. And I come around the corner, and they're standing there leaning on the rake. What are you guys doing? We're working. No, you're not, because work is done when a force causes motion, right? So by simply standing there, bracing yourself against the rake, you're definitely not working. To get back to work. So obviously me knowing this stuff, they think I'm a jerk. So work is done when a force causes motion. Now check this out. Force, voltage. Current, motion. Voltage creates current, causing electrons to move in a circuit. So if you've got a voltage and you've got current, you're doing work. May not be the work you want to get done, but you're doing work. Because a force causes motion. Voltage causes current. And we know voltage is pressure, current is movement. It's got to be power. Make sense? Now, electric power rate is the instantaneous rate at which work is done. Instantaneous. That means take a snapshot right now. How much work is being done right now? What's the pressure? What's the current right now? Instantaneous value. Make sense? Now, that's not how the power company, it's actually odd the power company is called the power company. Let's go back to that. Power relates to the rate at which work is being done. Work is done when a force causes motion. How many of you here pay money on a monthly basis to the power company? The power company. Why are they called the power company? All they're really providing us with is voltage. You know who the power company is? It's you. It's to take money out of our wallets, exactly. Who's the power company? You're actually the power company. You're providing the current path, if you will, for the current to flow. They're just providing you with the voltage. They should be called the voltage company. Okay? I mean, realistically, that's all they're doing. When you pay for electrical service to your home, all they're providing you with is a voltage, a electrical pressure at your box. It's up to you to hit the breakers, turn the circuits on, turn your lamps on, turn your appliances on, turn your loads on. That gives current a path to flow. Now you're consuming power. Power company. I always, I take this stuff too literal, which is one of the reasons that I'm here and you're there, okay? But it just doesn't make sense, does it? It really doesn't. Now the power company, the voltage company, charges you in watts. Actually, the power company charges you in what are called kilowatt hours. Kilowatt hours. I'll talk about more of that in a second. Measured in watts, wattage is greater when work is done in a short period of time than when the same amount of work is done in a longer period of time. Wattage is greater when work is done in a short period of time than when the same amount of work is done in a longer period of time. All right? A mild example of this, it's an area of, I enjoy motorsports in general. I enjoy mechanical things. No offense to any of you here that are into any of the fine arts. But if I had a chance on a Sunday afternoon of going to the opera, which I've attended, the opera, a symphony orchestra, musicals, plays. I'm not a big musical guy, no offense, but it's not how I roll. Or going down a Boeing field and standing at the edge of the fence and watching the heavy metal take off. Okay, I'd probably be down a Boeing field. It's just how I roll. So I've always been a big advocate of motorsports. One area of motorsports that I never was really that intrigued with, I respect it, but I'm not that intrigued with pursuing it, is drag racing. But I respect it immensely. Drag racing is about getting as much power out of the engine and coupling it to the wheels and getting the car down the track, quarter-mile track, as quickly as you possibly can. And if any of you ever watched drag racing, some of them rockets, strap yourself in, go, pow, wow, quarter mile, a matter of seconds and they're down that quarter-mile track. I've always been, I've enjoyed NASCAR racing, and Formula One is just, Formula One for me is it. Because they not only go down the track that fast, but they turn around and come back, and they make some turns in between. So that's really amazing technology. But follow what I'm saying, drag racing takes all of that power, couples it to the wheels, the tires, traction, and accelerates, okay? So they're consuming a huge amount of power and converting it into energy to get down the track.
Would that be the same concept if you had a car that did 45 miles in 1 hour versus a car that did 80 miles in 1 hour? You would be consuming more power.
Absolutely.
Miles an hour, but you'd get there faster.
Absolutely. Yep. And to get that work done in a shorter period of time, it's going to take you more power. So that's one of the reasons that, with gas prices going up, getting off that pedal does make a difference. Does make a difference. The epitome for me, and it's a toss-up. It's a toss-up. NASA's was involved in both of them, right? Space shuttle. Space shuttle, or kicking it old school NASA, the Saturn V rockets. Saturn V rockets, a little tiny capsule up on the top, big, huge freaking rocket, okay? Light it. The dude that lights it, and then goes like 3 miles away and goes into a concrete bunker, okay? And then literally with the space shuttle, it's the same thing. They light it, and then they like run 3 miles away, and thing goes off, right? 7 minutes later, they're in outer space. 7 minutes later, they're in outer space. NASA throws power at the problem to get the space shuttle into orbit. Okay, so obviously we're talking about if NASA could meter out that power, you could probably light several cities for a good deal of time. Instead, they say, how can we get that power and concentrate it in liquid fuels, solid rocket boosters, and then be able to concentrate that energy so we could get that space shuttle, which is freaking huge, it's a big thing, into outer space in 7 minutes. Not 8 minutes, not 9 minutes, but in 7 minutes, they're in orbit. Tremendous amount of power. Have any of you here ever seen a space shuttle launch? Okay, I had the opportunity back in the 80s. I actually saw the Challenger. Fortunately, not the time that it had its malfunction. I saw it before that. And actually, ironically, Dick Scobie, who's from Auburn, Washington, I saw a mission that he flew prior to the catastrophic accident that they had. But I was in Titusville, Florida. And you're listening to the radio and you hear the countdown and everything, 3, 2, 1, and I don't know how many miles away you are, like 10 miles, 12 miles. You see it going up, and then all of a sudden, then the wall of sound hits you, and it's just a sound like I've never heard before. It's like, wow, that is freaking cool, And next thing you know, it's gone, man. It's in orbit. They're in orbit, orbiting around the Earth. Tremendous amount of power. Okay, so it's the same thing with electronics. It's the same thing with electronics. The more power we throw at something, the more work we can do. So, basically, if you're attending a concert, the Pink Floyd Orchestra is performing in an auditorium, they are going to have to throw a lot of voltage and current at the problem to create a lot of acoustic energy to satisfy the masses, because that's what we've all grown accustomed to, is loud music, right? Okay. Watt is the basic unit of power. That is not a question, it's a statement. Watt. Watt is the basic unit of power. It is literally equal to the voltage across a circuit multiplied by the current through the circuit. It represents the rate at which work is being done. And Watt is the guy that came up with it. And what he said, I think he gave this presentation down at the Kingdome back in the day. 45,000 people. Ohm gave his spiel. Right? Remember that? V is equal to I times R, right? That was Ohm's deal. Watt got up there, not to be outdone, and he said, P is equal to I times V. And that's what he said. That's what he said. So, again, P, I, V. Triangle with a T in the center, power is equal to voltage times current. If I ask you how much voltage is there, and you know how much power there is, right, in current, then you could calculate out the voltage. If I ask you how much current is there, if you know the power and the voltage, you could calculate out the current. And of course, power, current times voltage. That's all your variables. Simple math. And this is called Watt's law. Watt's law. So far, for those of you at home keeping track of what's going down, we've gone over Ohm's law, we've talked about Kirchhoff's law, and this is Watt's law. These are laws of physics. They allow us to calculate what's going to take place with 100% accuracy. Very, very useful tools. We're not teaching you this stuff because I got nothing better to do with my time. We're teaching you this stuff because this becomes very valuable for an electronics technician. It paints a picture, tells you what's going on. Literally tells you what's going on. Okay? A little known fact about yours truly. I used to work in radio. Okay? I worked on the air. I was an on-the-air personality for an AM radio station in Connecticut. And it was one of the things that got me interested in electronics, because I worked kind of hard and I didn't have a whole lot of job security. There was a guy at the station, the chief engineer. This guy, every year he'd have a new, he'd buy a Formula Firebird, trade in the old one, get a new Formula Firebird. And he always kind of had a girlfriend with him that was kind of had it going on, if you know what I mean, okay? And he did very little. He came every week to the station, and he'd get all of the readings that all the on-the-air people took from the transmitter. We were able to take the readings from the transmitter remotely, but we had to log in these voltages and these currents. And then he would come. He'd come with a calculator, much like this, right? And he'd sit there and he'd perform these calculations all the way down, and then he'd sign the logs, take them, stick them in a folder, and then they'd be held by the station. What he was doing is that the station, commercial station, was licensed by the Federal Communications Commission to only broadcast so much power. And the proof of how much power was being transmitted was the voltage of the final transmitter tube, the current flowing to that transmitter tube. If you knew those two, you could calculate out the power. And then there was approved engineering design criteria for the antenna system, that the antenna system had certain number of losses. So you could prove to the FCC, you see, we were not broadcasting more power than we were allotted. We were not interfering with that station in Pennsylvania, okay? We couldn't have been, because we're only broadcasting out what you've allowed us to broadcast out. So as a technician, calculating this out through the current and voltage readings, that I think it was every 4 hours we had to take. Every 4 hours on the air personnel, and it was right there in the studio. It was an equipment rack, and you could go and just sequence through, you know, and take the voltage readings, the current readings, and log those in, and that became part of the permanent record. So it was kind of fun. It was kind of funny. It really was inspirational for me seeing this guy as the chief engineer. He was a chief engineer, and he was assigned several radio stations in Connecticut on contract. Guy made really good money, you know, and I'm like, how do I get his job? Well, you need an FCC license, you know, basically the general radio operator's license to be able to maintain a commercial radio station like that. So anyway, I'm an examiner now for the FCC, and I give that exam, and I've never in my life owned a Formula Firebird. So I have had some girlfriends that kind of had it going on, if you know what I mean.
It sounded like a pretty easy job he had, though, huh?
Until it hits the fan. Until the station gets hit by lightning, okay? And then it's like, oh. And then you got the general manager, right, the program director, and all of that advertising dollars that were spent, right? You're losing that money because the station is off the air, and that's how stations pay the bills, is all the advertising. So when you're off the air, you're in a pickle. People will tune to another station or whatever. So it's kind of a big deal. Ironically, though, kind of behind the scenes story, like here, we had a woman in our program that completed this program, and I got her an internship. She interned for a period of time at KISW. And the engineer at the time over there, Brian, he hadn't had a vacation for 3 years. Because again, as a chief engineer, you just don't go on vacation. Yeah, I'm taking my vacation next week. You can't do that, because if the station goes off the air, who's gonna, you know? So there was nobody that he could hand the station over to. Once she got in there and she built up some credibility, he actually went on vacation and gave her the keys, and it's kind of like, hey, you've got it, Cindy, you've got the stations. She was a student here at Lake Washington Technical College, and she was the acting chief engineer for KISW. Also, because all these engineers and all the radio stations in Seattle, they're all in cahoots with each other, okay? So if the station goes off the air, you know, call Tony over at Cairo. He'll come over and help you out. You know, you've got all these engineers that will lend a hand, even though you're the competition on paper. If I need something, you'll help me out. If you need something, I'll help you out. And it kind of goes, it's a, you know, unwritten law, if you will, in radio to help everybody else out. So kind of exciting. So anyway, this power reading is very, very critical, so that you could tell the performance of your equipment. And it's something that, if any of you go into commercial broadcasting, you're going to be doing the exact same thing, taking those power readings. How much energy are we getting off the antenna? The only way of telling is how much voltage you got, how much current you got going. Same thing. You come from an car audio background, same thing. You got a 1,000-watt amplifier. It's a math problem, okay? 1,000 watts, you know what this is, okay? 12.6 volts DC. You know what this is? Well, this is going to tell you how much current it is. It's a math problem, you know? Now, it's 1,000-watt amplifiers, that's peak performance, and how often you're going to be cranking out that peak performance, but you've got to design everything backwards to make sure that if you crank it up all the way, you're not going to cause an electrical fire and subsequent meltdown. So you've got to design, and it all integrates. Really, it's a beautiful thing. Now the electric company, like that, the voltage company, they charge you for kilowatt hours. Kilowatt hours. That's 1,000 watts, a kilowatt, right, per hour. So that's you consuming 1,000 watts over an hour, okay? I don't know if any of you go to the gymnasium periodically, the gym, workout. Some of the life cycles, stair steppers, these things, some of them have integrated in calories that you're consuming. Some of them have a screen that you could go to for watts, okay? So I often thought, I hate working out. I really do. It just is, I'm not afraid of hard work. Okay, if I got to dig a ditch in the backyard, I love doing it. You know, I'm all about hard work. But going to the gym and for an hour just doesn't make sense. At least hook the thing up to a generator. Let me charge my cell phone or something, and let me save a nickel or something. If that makes more sense to me. But anyway, some of these screens have watts, and if any of you have ever done that, how hard you have to work to generate a watt. I mean, it's amazing. So the electric company, the voltage company, is selling us 1,000 watts per hour. That's the unit of measure that they charge us. Okay? Does anybody know off the top of their head about what we're being charged here in the greater Seattle area per kilowatt hour? Bzz. That's way too much. You're being ripped off, man. That's Gryniuk power and light. It's about 8 cents. About 8 cents. Some of you, depending on your scale, 6.5 cents, 7 cents per kilowatt hour, which is the thing that I kind of struggle with. I go this year alone. Since January, I got invited to attend a green energy conference, Good Jobs, Green Jobs, in Washington, D.C. And then I was invited to be a guest speaker in Milwaukee at the Green Summit. So some world-class speakers I get to be in the presence of. So I go to this Green Summit in Milwaukee, and I get seriously jazzed. I'm going to go home and I'm going to do an energy audit. I'm going to see. And then I get home. It cost me 6.5 cents per kilowatt hour. How much effort do I have to put into really saving? How much am I going to save? It really doesn't make sense. I mean, it really doesn't. There needs to be consumer incentive for you to really hunker down and save, because electricity here in the Northwest is very, very inexpensive. And that's a good thing. I'm not complaining about it. And there are some things that you could do to save energy, but there's only so much that you could do, and we're really not paying that much for it. Even like with electric cars, I know my colleague did some of the math with purely electric cars that they're coming out with, and really it equates, for the price of gas at $4 a gallon, it comes out to being that it's about 99 miles per gallon that you would get equivalent to travel 99 miles than it would cost you for that fill up. And that's what it equates to when you're paying 6.5, 7 cents per kilowatt hour, which isn't bad. I wouldn't mind having a car that got 99 miles per gallon, 100 miles per gallon. But is it worth the investment of me scrapping my my V8? I mean, because unless I'm driving a Tesla, which is out of my range, I don't think I like that V8. V8 Taurus, pour some fuel into the situation, a little bit of air, get out of the freeway, set the pace. Not keep up with the flow of traffic, set the pace. And I have documentation from Washington State Patrol that will attest to that fact. Okay? Circuit analysis to determine the power dissipated by a component and voltage drop times time. So I'm talking about for a component now. Okay, this works for loads. This works for like an amplifier. If you got an electric load, an amplifier, a transmitter, you could do this. But this also works for individual components. So if you know how much current's going through the component and you know the voltage across the component, then you could figure out exactly how much energy that component is dissipating. Now, remember resistors? Remember resistors? Resistors are devices designed to possess the property of resistance. Resistance is that force which opposes the flow of electrons. The byproduct of resistance, when current encounters resistance, it generates heat. That's how we determine the power of that resistor, because all resistors are not created equal. There's 1/8 watt resistors, 1/4 watt resistors, 1/2 watt resistors, 1 watt resistors, 5 watt resistors. How much energy could they dissipate? And literally, it's the voltage across the component times the current going through the component that's going to give you that power that's being consumed by it. If a resistor, if you ask too much of a resistor, it will fry. It will fail if you exceed its rated capability. So all electronic components are really like that. If you know the voltage, you know the current. We're going to talk about some exceptions in the future. They're not resistive components, they're called reactive components. That'll come later this quarter. We'll talk about that. And that these are components that don't consume energy in the form of heat. That's why they're called reactive, but something we'll talk about in the future. Hey, the neat thing with power dissipated in series or parallel is equal to the sum of the power dissipated by the individual components. Power is always additive. It doesn't matter if it's series or parallel or whatever. Power is always additive. If I've got a 400 horsepower engine on my airplane and I remove it and get another 400 horsepower engine and mount each engine on each wing, now 400 times 2 is I'm up to 800 horsepower worth of power. As where before in a single engine aircraft, I was only up to 400 horsepower, okay? It's kind of funny. I know a little bit about airplanes, but the odd thing about airplanes is when you do that, instead of the airplane costing twice as much, that ends up usually costing you about 3 times as much. So for a twin engine airplane, you're going to pay through the nose. You know, much higher performance, a lot more going on with it, a lot more structural that they have to do. But power is always additive. That's why the space shuttle, right? Solid rocket boosters on the space shuttle, right? They have 2. You know how much power that is? Twice as much as 1. Okay? That's why they put 2 of them on. And actually, from what I understand, I think the space shuttle can, I don't know if it can get a shallow orbit, if it's just on one solid rocket booster or not. But those things are literally like Roman candles. Once they light them, they're going for a ride. There's no shutting them down. Oh, we changed our mind. Let's back it back to the pad. No, you're going for a ride. Power. So power is always additive. Always additive. This is the thing like with your home. Forget about what I said. Energy conservation, a bunch of hocus in your home. Every device that is on in your home right now that has a voltage across it and current flowing through it is consuming power. Okay, there's a lot of phantom loads in your home. Stuff that's plugged in but it ain't turned on, but it's still consuming power. Why? You got voltage across it, it's got current flowing. You're playing. How many of you have a nice flat screen TV at home, right? How many have it, is it turned on right now? You leave it on 24/7 or is it turned off? Still consuming power. Still consuming power. So that way when you go home and hit that remote, that screen comes right up. If not, there'd have to be a period of time with some electronics for it to warm up, come up. Everybody wants instant gratification with systems. Especially some of the old tube systems, right? Those really consumed a lot. You had to wait for the tubes to heat up and everything. But most electronics are really in a standby mode. Your battery charger right now, your cell phone charger at home, if it's plugged in the wall and it's not plugged into your cell phone, it's still consuming some energy because it's got current flowing through a coil there. When you plug in your phone, it consumes more current, right? So a lot of these, again, are phantom loads that exist in your home. You're consuming energy. Real small amount, but it all adds up. It all adds up, you know. Actually, one of the things I can give you a sales pitch for tomorrow's meeting, where I can watch a documentary called Power Surge that was just done on public television last week. It came out. They talk a lot about that. You know, it all adds up. It's all about power. You know.
About the lady that unplugged everything in her house for a month.
Oh, I didn't hear about her.
No. As soon as she was done using it, there was nothing that was plugged in.
Did she save money?
Yeah.
Really?
Decent amount, yeah.
Huh. I'm not going to do that. All my plugs are like behind the couch and crown. I'm not going to climb back there. It's all a power strip with an on-off switch.
Hit the main breaker.
You know, that's it. And in all honesty, that actually, I thought about that. You know, my wife and I travel a lot, and we, you know, well, we go away, and really would make sense, just shut off that main breaker of the house, you know, leave for a month, come back, and then, you know, you go get your electric bill, and they still charge you the same, you know, they're just messing with you, man. They're just messing with you. You got to have your ducks in a row, man. You got to pay attention to that meter, so. Now, in electronics, the power dissipated in a circuit is often less than 1 watt. Electronics, microelectronics like you're studying here, typically the value is going to be less than 1 watt. Typical values will be the milliwatt. This is times 10 to the negative third, or 1,000th of a watt. And the microwatt. 1 million microwatts equals 1 watt. So we're talking 1/millionth of a watt. That's typically what's consumed in microelectronics. There's not going to be heat or energy being consumed. For some of you playing around with amateur radio, you want to get your amateur radio license and play around with some of that stuff. Some of them are higher power transmitters. You need to make sure you have the available current and voltage to get the signal out. If not, you're not going to be able to do that. Because again, the formula here behind the lie, power is equal to current times voltage. So if you're on a low voltage system, like a car or a boat or an airplane, and you want to start jacking this value up, that means you're going to have to start using a bigger cable, physically bigger cable, because you have more electrons that you're going to have to transport from the source to the load, and that's what you're measuring. Okay, so the math doesn't lie. Total power dissipated in a series or parallel circuit is equal to the sum of the power dissipated by the individual components. Meaning, power is additive. Power is additive. There's no such thing as negative power. There's nothing that's going to take, you know, but this is putting power back in, you know, perpetual motion machine. You get something like that going, give me a call. Okay, give me a call. I'll have my attorney contact your attorney, and I'll personally fly you to Bimini. And you could watch the sunset drinking out of a coconut with one of those screwy straws, and an umbrella on the top of your drink. I'll take care of you. Okay? Now all we do is consume voltage, current, we consume power. Nothing puts things back in. So it's not. I guess it'd be like me getting an airplane engine, you know, mounting one like going this way, and then the other engine going this way, and then you just sit there, you know, you never go anywhere.
Wait, spin around in a circle.
One being that way. You know, then they lift off. I mean, you know, it's a UFO. No, it's a doofus. it's a doofus. What's that guy doing? Does that make sense? All right, summary. Power is the rate at which energy is delivered to a circuit. Power is also the rate at which energy or heat is dissipated by the resistance in a circuit. This isn't, that second bullet statement there isn't something we dig, it's something we got to deal with. We don't want our electronic equipment to get hot. It's one of my problems. I got a lot of electronics in my family room. Got my audio, I got surround sound, I got my plasma screen TV, I've got all this equipment, I got several computers. I got a computer that monitors the weather at my house. Why? Because I'm just into that kind of stuff. I got my other main computer. I've got all my network gear for router. I got a switch that powers the other internet connections in the house. I got all that stuff. In the summer, that room really gets freaking warm. Okay, in the winter, it's kind of cool. Warm, I mean, you know what I mean. You come in there, and I got all this electronic stuff that's keeping that warm, relatively in temperate. But, you know, was it last year, 2 years ago, we had that heat wave? It was like, holy cow, man, I had to start shutting stuff down. I'm like, you know, how important is this? I want to shut this stuff down so I don't have a Wi-Fi system in the house. Not that that generates that much heat, but everything else in there does generate the heat. We don't want that. We don't want that. It's something we have to live with. So a lot of times when equipment is densely packed, that thermal profile tells us what's going on. Former member of our advisory committee here at Lake Washington Technical College was the chief engineer for Channel 9 out of Seattle. And we went down there for a tour one day. Their transmitter is located up on Capitol Hill. And he was showing me the air inlet temperature and then the exhaust temperature, right? The air that they're sucking in to run through the transmitter to cool it. And by looking at that, you know, this is the inlet air temperature, this is the exhaust. By looking at that difference, obviously if it's a warmer day, they go up like this, right? I mean, it is what it is. By him looking at that, okay, if this stays stationary and then this one goes up, it immediately tells him what? The transmitter's consuming more power. That means there's a problem. Because when it was brand spanking new, this is what it was. This is the inlet. The difference between the two is a critical number. Temperature. You raise the temperature, shows you something's not operating efficiently. Plain and simple. One of the tricks, because I paid attention. I'm not that smart of a guy, but I did pay attention when I was in school, formal schooling like this. One of the things that I used to do is when I was in the Navy, we had very, very complex circuits. And there was this one board that had memory chips on it. And it used to fail. And running the diagnostics to determine which chip it was just very, very laborious. And I've always kind of been a lazy guy. And I'm like, there's got to be an easier way of doing this. So what I did one day is just for giggles. I knew we had a failure. We already figured out what it was. I put it back in there, fired the whole system up, right? And then immediately shut the thing down, pulled the circuit card out, right? My finger, and I started going across the chips. Got to the hot chip, and guess which chip was the hot chip? The failed component. So anyway, it was kind of funny. My colleagues thought like I was like into black magic and like voodoo and because there'd be a problem with the chip, and then I'm like, okay, I'll figure out which one it is, but you're all gonna have to leave, okay? And I actually started doing. I had a little mojo bag with some bones in it and a crow's foot, and I played the whole thing up, And we'd shut the thing down. I'd come out, U44. It's like, how the heck did you do that? I was looking at which chip was getting hot. The one that gets hot is the one that failed, and it's generating more heat, and that's what the problem is. So you could really determine, using a troubleshooting tool later on, if something's getting hot, and if you know what the norm is beyond that. Now they've got stuff on the market. They've got thermal imaging. Power voltage company actually uses thermal imaging. They'll go ahead with a thermal imaging gun and look at their power runs, and where two wires are joined together, if it starts to generate a lot of heat, they know there's a problem up there, okay? Because if it's generating heat, that shows that connection has too much resistance. Because resistance generates heat. So you can analyze, with thermal imaging, you can really see a picture of physically what's working and what's not working. So that's an advancement that's taken place really within the past decade. Thermal imaging now is pretty much mainstream. It's not that. Heck, you could get a non-contact infrared gun. You can get one at Harbor Freight Tools, for $19.95 with a laser. You pointed at it, and then that would have shown me exactly what I used to burn my fingertips finding the hot chip. Okay. Now you could just use one of those and say, oh yeah, this chip here is hotter than all the others that are doing the exact same job. This is where the failure is. Power is measured in watts. Watts is what power is measured in. It's not a question, it's a statement. Power is literally the product of current and voltage. Current times voltage. Any questions on power?
You were saying that to determine the total voltage drop across any component is a different formula than what it would be to calculate power, but in the book it says they both say P equals I times.
No. I'm just saying to determine how much power is being consumed across a component, you need to use that voltage drop across the component, not total voltage value. All right, let's go ahead and take a 13-minute break, and we're going to start up again at 6:35. 6:35. Chapter 8, DC circuits. DC circuits. One of the things that you need to understand about this chapter is it's the concepts that we're going after. We want you to understand the basic concepts. You're not going to make a lot of money necessarily going out and working on circuits like this in industry, circuits that are made up of a power source and a bunch of resistors. But what this is designed to do is to show you an approach on circuit analysis. We are going to use circuits that contain a bunch of resistors in industry, and those resistors are going to be used to establish voltage operating points around transistors or other semiconductor devices. So, although you're never going to go out and necessarily work on circuits exactly like this, you have to absolutely, positively understand the steps and the competencies of circuit analysis as it pertains to DC circuits. Okay, that goes without saying. And quite frankly, we've already talked about these concepts. This is just the chapter where we pull it all together. After completing this chapter, you're going to be able to solve for all, and let me emphasize the words all, unknown values. That means voltage, current, resistance, and power. Always solve for everything, because if you know everything, I could never ask you anything that you don't know, because you know everything. In series circuits, parallel, and series parallel circuits. Understand the importance of voltage dividers, and design and solve for all unknown values in a voltage divider circuit. We are going to spend time on voltage dividers. Some of the stuff I'm going to blast through, but voltage dividers are something that I'm going to spend some time on the board here to make sure you got a handle. Because quite frankly, the book is okay, but the author really drops the ball with voltage dividers. He pulls a couple numbers out of the air that I still don't have a clue where it comes from. So I'm going to show you how to approach that. As you know, a series circuit is a circuit that provides only one path for current flow. The simplest example of a series circuit, you ever have those holiday lights, the Christmas lights that a bulb burns out and the whole string goes out? It's a series circuit. Because the filament of one bulb interrupts the flow of current to all the other bulbs. It's a series circuit. If you've got a string that one bulb burns out and maybe 10 other bulbs go out, what does it tell you about those 10 other bulbs? They're all in series. The whole string may be a combination circuit, but that individual section that went out is in series. So there's a lot of lessons behind looking at festival lighting and when it goes out, what exactly is taking place there. Factors governing the operation are the same current flows through each component. Literally the same current. The same electrons. They only have one path to go. That's from negative to positive, so they have to travel the entire route. Total resistance in a series circuit is equal to the sum of the individual resistances. Right? This is what, chapter 3, 4 review? Right? You got resistance, you add it up in series. Always additive. And that includes the resistance of a bad solder joint, the resistance of a bad splice. Remember how I said the power company, the voltage company, will actually use thermography and look and say, wow, we got a splice up there and it's generating a lot of heat. We got to shut that section down and replace that, because it shouldn't be generating any heat if it's a good splice. The total voltage across a series circuit is equal to the sum of the individual voltage drops, meaning total voltage is equal to voltage across component 1 plus the voltage across component 2 plus the voltage across component 3. This is a review. This is the same thing you could quote me, right? I love it when you quote me, right? Voltage rise equals voltage drop, okay? So here, voltage rise, ET, or VT if you prefer, equals voltage drops. ER1, ER2, ER3, those three voltages better equal what I put into the circuit. If not, you got a problem. If you find where the missing voltage is, you probably found the problem. Where was the missing voltage? Where was it? Oh, it was in a bad splice. Oh, okay. You fix that problem, boom, you're up and running. The voltage drop across a resistor in a series circuit is proportional to the size of the resistor, meaning the bigger the resistor, I'm talking about in ohms, I'm not talking about physical size. The more ohms, the less current. The more ohms, the higher the resistance, the bigger the voltage drop across that resistor. I always think of a resistor. Remember how I used Seattle traffic flow as an analogy, right? A big resistor is like a big accident. If you just got a fender bender, is that going to slow the traffic down? Yeah. Fender bender, they pull over the side, people stop, slow down, look or whatever. Now you got a 5-car pileup. It's a big accident. That's a big resistance. A big resistance is going to create, I gave it away already, a big backup. A big backup is a big difference in potential. A bunch of people here that want to get to work and a bunch of people here on the other side of the freeway that an empty freeway, basically. That's a big difference in potential, okay? I love flying in my airplane over traffic jams. As a matter of fact, being a pilot, owning an airplane, being stuck in a traffic jam drives me freaking nuts. Like, why am I stuck in this traffic jam? But from the air, it's so obvious where there's an accident or a problem, because all the traffic's backed up and then just a few cars are making it through. Difference in potential, big resistance. Make sense?
In the book, it says ET is equal to ER1, equal to ER2, equal to ER3.
It's a mistake. That's for parallel. You sure that's not parallel you're looking at?
Total voltage across the series circuit.
Bzz, typo. Typo. Yeah. Total power in a series circuit or parallel circuit or complex circuit. Power is additive. PT is equal to PR1, PR2, PR3, PR4. Just add up all the power, and that's going to give you your total power. The bottom line. You want the bottom line or you want the BS? Bottom line. In a series circuit, the most important thing to remember about a series circuit is current is constant in a series circuit. Period. The second most important thing to remember about a series circuit is also synonymous with voltage divider. When I say series circuit, I want you to think current's constant, and I want you to think voltage divider. That's just how I want you to look at them. And if you're not looking at them that way, you ain't looking at them right. Houston, we're going to have a problem. Okay? Those are the most important things. I'm going to have you repeat that back to me in the future. Do not deceive me. Okay? Remember that stuff. The most important thing in a series circuit is current is constant. Why is it constant? It's only got one path to flow, so it better be constant. The second most important thing about a series circuit is also known as, right? AKA, like in police lingo, AKA, also known as a voltage divider. Voltage divider. In this particular circuit, I mean, I look at it, and yeah, I've been doing this since puberty, but I look at this, and what do I see? I see a voltage source and 3 voltage drops. Voltage rise and 3 voltage drops. 3 loads. I don't know what they are, but I know these loads are connected in series. And I know that all the current that flows out of the negative terminal of my voltage source has to travel this complete path. No place else for it to go. So the current's going to leave the negative terminal of the battery. It's going to make this corner, 90-degree corner at the speed of light. This is cool stuff, ain't it? The speed of light. Come on down through here, the back stretch, hit resistor 3, and create a voltage drop, a difference in potential. Current's going to finally make it through that obstruction. Another 90-degree corner at the speed of light. Come up here to R2. It's going to create another voltage drop because there's another obstruction. There's more resistance here. Current's going to continue on, another 90-degree corner through R1, another voltage drop. This voltage drop, this voltage drop, this voltage drop have to equal this voltage rise. If anything's missing, you got a problem. Find where it's missing, and you found your problem. Power, additive. Resistance, additive. What else is there? So anytime you've got, the other way I want you to look at it is anytime you've got one way into a circuit and one way out, what does that tell you? It's a series circuit. It's a series circuit. Because I cannot show you every possible series circuit ever invented. If you've got one way in and one way out, it's a series circuit. Even if it's one component. One component, could that be series? Yeah. One way in, one way out, it's series. Tight? Tight. To solve for values in a circuit in order, the first thing I recommend you do is try to solve for that total resistance. Once you determine RT, total resistance in the circuit, then try to solve for total current in the circuit, IT. Once you know IT, then you could determine what your individual voltage drops are, right? So solve for your total resistance. Total resistance with your total voltage will show you how much current you're allowing into this circuit. Current flowing through the circuit encountering the resistance V is equal to I times R. The total current, the same current that travels the entire path, times the amount of resistance there is in a circuit. So this is going to drop a portion of that voltage. This is going to drop a portion of that voltage. This is going to drop a portion of that voltage. These three portions better equal the voltage that's put into the circuit.
In regards to the slide previous to this, which is
This one?
the 3 steps.
Yep.
It doesn't say on the slide series or parallel. So these, will they primarily cross over between the 2 applications?
Yeah, but I gotta warn you. This here is just like generic. This is like generic.
Sure.
And the thing of it is when you get out into industry or in lab, I may give you this, I may give you this, I may give you this, but this is encased in epoxy. You can't even get to it. You can't even get a part number off of it. You can't even take a reading of it. So you're going to have to use these laws and say, well, sheesh, I remember Joe said that this is equal to this plus this plus this. I know what this is, I know what this is, I know what this is, but I don't know what this is. So then you could say this, the remainder is equal to this. And it's a safe assumption because you're using a law, Kirchhoff's voltage law, basically to determine what the unknown is. And if you're using a law in industry to figure out what part you need to buy, whose money you need to spend, it's a pretty safe assumption. I mean, it really is. So that's why we're teaching you this. So don't necessarily use this as a checklist and like, oh yeah, I took copious notes. I listened to what Joe Gryniuk had to say in lecture. I went home this weekend to try to do my homework and it didn't work because I couldn't determine total circuit current because I didn't know what this value was because Joe didn't say. Sometimes we might not know what this value is or we need to find it on the internet off of a data sheet from a manufacturer. So the bottom line I want all of you to realize with these circuits and analyzing these circuits, you always need to find at least 2 bits of information. If I only give you 1 piece of information, you're not going to be able to get very far. But if you could extract 2 bits of information, then you could remanipulate these 3 to suit your needs as long as you get the right answers. Make sense?
Absolutely.
Okay. Parallel circuits. I might as well get the cat out of the bag right from the get-go. Parallel circuits, the most important thing you need to remember about a parallel circuit is voltage is constant across a parallel network. Voltage is electrical pressure by being constant across a parallel network. What am I talking about? I'm saying that that voltage will be constant across all components that are connected in parallel. Your house is wired in parallel. The freaking voltage coming out of the outlets better all be the same. If not, you got a problem. You got a problem. Voltage is constant across a parallel network. Most important thing you need to remember. So when I say that, what's the most important thing about a parallel circuit? Like church, you all repeat after me. Voltage is constant across a parallel network. Okay? The second most important thing about a parallel circuit is that a parallel circuit is also known as, police lingo, AKA, also known as what? If a series circuit's a voltage divider, what's a parallel circuit? It's a current divider. Divides up current. Some of the current goes one path, some of the current goes the other path. Remember the Seattle traffic pattern last week? Was I here with talking to you folks about that, or was it somebody else? Was it a dream I had? I had a dream. It was about current. And that's what it is. So some of the current's going to take the 90, some of it's going to take the 520, some of it's going to take the north end of the lake, some of it's going to take the south end of the lake. Make sense? I've been a commuter for 20 years. I know Seattle traffic. I've gotten out of here and gotten on I-90 and driven eastbound to get to Tacoma, to Highway 18, just so I could avoid traffic. So I know a little bit about traffic. Look at these circuits like that. Factors governing the operation of a parallel circuit, the same voltage. The same voltage. Not an equivalent voltage, the same voltage exists across each branch of the parallel circuit and is equal to that of the voltage source. So literally, this is what we're up against. Total voltage is equal to voltage across component 1, it's equal to voltage across component 2, it's equal to voltage across component 3. It's not only mathematically equal to, it's the same pressure. I'll show you in the schematic. Same pressure. And that, in and of itself, will help you solve problems. If you know something's in parallel, you could assume, if it's connected in parallel, I should have the same voltage across that. Well, sheesh, the thing's still not working, or it's working kind of goofy. It's hard to get to. Well, sometimes you have to remove that access panel, go in there and take the reading. Holy cow. Everything else in parallel is at 12 volts. This is only at 9 volts. I'm missing 3 volts. You find the missing 3 volts, you found the problem. It's that simple. One of the most powerful tools. How many of you here like tools? I got tools. I got like every tool known to man in my garage. Just ask my wife, she'll tell you. Okay? I like tools. One of the most powerful tools in your box is this stuff right here. The second most powerful tool you're going to have is the digital multimeter. Because the digital multimeter is going to allow you to get out there and find the missing 3 volts. You find the missing 3 volts, you found the problem. You found the problem, you save the day. You save the day, you hit your boss up for a raise, he gives you a pink slip, cut you loose. No, just kidding. You get a promotion, life is good. You make so much money, get married, start a family, get a girlfriend on the side, it's all good. And I don't mean that. The current through each branch of a parallel circuit is inversely proportional to the amount of resistance of the branch. I is equal to E over R. I is equal to E over R. So that means, because R here, it means E over R, right? E over R. We use the slash here. But that means that this is on the bottom of the slash. So whatever we do to R is going to have an opposite effect on I. We call that an inverse proportional relationship. An inverse proportional relationship. So if resistance increases, current decreases. Bigger accident, less flow of traffic. Smaller accident, traffic flow increases. Plain and simple. So keep that in mind. The value of least resistance in a parallel circuit will have the highest current flow through it. The total current in a parallel circuit is the sum, literally the sum of the individual branch currents. That's why we call parallel circuits current dividers. Thank you. Current dividers. The reciprocal of the total resistance in a parallel circuit is equal to the sum of the reciprocals of the individual resistances. This is a fancy way of saying when we put resistors in parallel with each other, we actually add up the reciprocals. We add up the conductance of those paths, not the resistance of those paths. And the conductance of those paths literally is the reciprocal of the resistance. And that's what Siemens came up with, right? That was his whole trip. The other formula that I want you to be aware of, and I know some of you are reluctant to use it, it's the product over sum formula. If you've got 2 resistors or 2 resistances in parallel, use the product over sum formula. Product means R1 times R2 divided by the sum, R1 plus R2. And it's a real easy way. I mean, it's what's the, you got a 1/2-inch nut that you need to get loose. You could either use, the box end wrench, or you could use your teeth. Use the easiest tool. The easiest tool is the product over sum formula. Well, that's another formula we got to memorize. Don't memorize these formulas. Use them and learn them. You understand the difference? Memorizing stuff never worked for me. I mean, that's always my fear that I'm going to get pulled over. That's why I don't drink and drive, because I get pulled over, even if I haven't been, or if I'm not totally under the influence, they're going to ask me to do the ABCs, and I'm probably going to screw that up. They're going to throw me in the hooskow because I don't know my ABCs, because I never really memorized them. I kind of learned them. Saying backwards? I'm going to have you do that crap. I can't freaking do that. What the heck are you doing? While hopping on one foot, recite the alphabet backwards. No, man, officer, with all due respect, let's see you do that. Huh? Jeez, you're killing me. Total power consumed in a parallel circuit is equal to the sum of the power consumed by the individual resistors. No mystery here. We just talked about it last chapter. Power is always, that's beautiful.
Hey, what were you saying about the product sum formula? When you can only use that in a parallel parallel circuit?
Correct. If you only have two components in parallel. Two or more, you got to use your favorite formula. The reciprocal of the total resistance in parallel is equal to the sum of the reciprocals of the individual resistances. A lot of people like that one more than mine. Mine is only good for two. Also with that, don't forget your thumb rules. Remember your thumb rules, right? If it's equal resistance, you simply count up the number of resistors, that value of resistance, and divide it by that number. If I have 4 100 ohm resistors in parallel with each other, what's the total resistance? 4 100 ohm resistors in parallel with each other. 100 divided by equals 25 ohms of resistance. The other thing for resistors in parallel, the total resistance will always be less than the value of least resistance. It'll always be less than the value of least resistance. Thumb rules. Okay? You pay attention to those thumb rules, your GPA is going to increase drastically because you're going to have something to check yourself against. I don't know if I used the right formula, but I remembered you always said the value of least resistance will be less than the value of least resistance. My answer meets that. I'm comfortable with that answer and stick with that answer. Power is additive. It's a parallel circuit. Remember how we said voltage is constant across a parallel network? That's because this electrical pressure being exerted by this source is distributed equally across these three loads, period. It's the same. It better be the same. If it's not, we got a problem. If it's not, we got a problem. Where's the missing voltage? This is how your house is wired in parallel. The outlet in your bathroom better have the same voltage across it as the outlet in your family room, as the outlet in your garage. If not, it's not wired properly. Something's up. I got a big circuit like this at home because I do everything big. That's how I roll. I made some significant improvements to my backyard about 10 years ago. My backyard used to come out and it used to drop off a hill, and it was just an unusable backyard. I wanted to like do stuff back there, you know what I'm saying? You know what I'm saying? So I was looking at, I had to build a retaining wall, talking big bucks to put in a nice retaining wall. So I was looking at different options, and I like to utilize the resources that are available to me. So I have a good friend of mine that worked for the railroad, Burlington Northern, and I said, hey, you know, you guys use those railroad ties. You know, what are the chances of getting some of those railroad ties? You know, like, you know, what are you talking about? Well, like a truckload. You know, those are hard to come by, Joe. You know, it ain't what it used to be. You know. So for like 3 years, I kept hitting him up for railroad ties and wasn't getting anywhere. And you know, we had a great relationship. And finally, he said something. He was kind of hitting around about going for an airplane ride. You know, it's hitting me up for an airplane ride. And finally, you know, I'm not the quickest study, the smartest guy out there, sharpest tool in the shed. And I finally like, oh, I get it. So I gave him a call, like, hey, Larry, what are you doing Monday night? You know, want to go for an airplane ride? I picked them up in Arlington, and we went out over the Cascades, beautiful sunset, whatever, landed, right? That Wednesday, my cell phone's ringing. Hey, Joe, still want those railroad ties? Yeah. Well, I got clearance not only to give you the railroad ties, but I got clearance to use a Burlington Northern crane to load them on a truck for you, okay? You just got to get the flatbed. So I went out and rented a flatbed. I drove literally. It was funny, it's Burlington Northern, but it was a yard up in Burlington. So I had to drive all the way up there. He loaded them on, 148 ties. Long story short, I built a beautiful retaining wall. Actually, had a former student of mine that was an engineer. He designed the wall for me. You know, did the prints and everything, built this wall, and landscaped it, beautiful. So now I have a backyard. My neighbors, they weren't digging it, because now they're looking at like, you know, he's got a perfect yard, and we still, you know, just like a wall, you know, railroad ties. Funny part of that story too, I built that by hand, 148 ties. I don't know if you've ever picked up a railroad tie. They are heavy. I built that by hand, backfilled it by hand with a wheelbarrow, gravel, drainage, by hand. You know how much weight I lost that summer? 0. Probably had something to do with the pizzas and beer I was consuming while I did it. But anyway, what I wanted to do is when it was all landscaped and everything, in the process, before landscaping, I wanted to put in low voltage lighting. low voltage lighting around the perimeter. So you know, like these, the goofy lights you stick in, and you know, but I wanted to put in conduit. I wanted to do this right. And as a pilot, I kind of wanted almost to look like a runway, and you know, an airport. You know, the lights around the periphery. So I used these low voltage lights. I had a big power supply in my garage and an equipment rack. Dug conduit all the way back. Did my calculations, and the other thing about calculations, determining what size wire you should use. The kind of wire that I use is the kind that falls off the back of a truck, you know, and the kind that contacts provide me with. So I went with this gauge wire. It was a little bit substandard, but you know, I figured, the math kind of works out and it's kind of good. So I've got all these low voltage lights, and ironically, it came out nice. Came out really, really nice backyard. But I could tell. If I brought you back there, you probably wouldn't even notice it. But I could tell which light is the furthest from the power supply. Just looking at it. And it kind of bothers me. It doesn't bother me enough to rip up the conduit and pull new cable, okay? But I know. I know by looking at it. And what does that tell me? That tells me that the load furthest down the line is not getting the same voltage as the load closest to the source. And gradually, as you get further away from it, you just notice a little difference in illumination.
But shouldn't voltage remain the same in a parallel?
Yes, that's my whole point.
Length of
Why doesn't it?
copper is resistance. So at the longest distance, you just need a different bulb that's more efficient.
I needed to use basically a heavier gauge of wire. In doing that, if I had done that, then I could, there's ways I could fake it. Soldering, what are you doing out there? I'm soldering in resistors to these other lamps. Why to get it? My wife would probably finally really give me the boot, but it bothers me. It bothers me because I like doing things right, and I guess I did do it right, because you know how much that wire that I used cost me? You know, literally fell off the back of a truck. So, you know, don't judge me. I have a friend that's a police officer. I asked him, I said, you know, what's the whole deal like if I got something that fell off the back of the truck? He like sat up and he's like, you know, I'd love to cite the driver for driving an unsecured load. You know, so. Anyway, so this is a parallel circuit. Now, yes?
You flooded the conduit with liquid nitrogen, would that light be nice and bright?
You know, that's one of the other things I was kicking around. Can I stick an inert gas in there and you know, increase the dielectric properties, and you know, she'd throw me out, man. She'd throw me out. And you know what? I know you find this hard to believe, maybe you won't, but I actually have a nitrogen bottle at home. Doesn't everybody? And I don't necessarily use it for welding. Series parallel circuits. This is the easiest part of this entire chapter. Circuits that consist of both series and parallel circuits. To solve most series parallel circuits, simply apply the laws and rules of each type. There's no mystery. There's no silver bullet. There's no easy way for me to describe it to you. Use series formulas for the series parts of the circuit. Use the parallel for the parallel parts, period. That's all it is. That's all a series parallel circuit is. That's what it looks like. R2 and R3 are in parallel with each other. You got to solve for that before you could solve the total resistance. Because R2 and R3, one of the things that I like to do is identify these points right here. These are called nodes. I'm going to call this node A and node B. The resistance between node A and node B is equal to the parallel resistance of R2 in parallel with R3. I'd use the product over sum formula to determine what RAB is. Follow what I'm saying? RAB, the resistance between node A and node B. The total resistance in the circuit is equal to R1 plus RAB. That's what equals total current, or excuse me, total resistance. Total current can be determined by that. Once I know what total current in the circuit is, total current is going to create a voltage drop across this resistor. Total current is going to create a voltage drop across this resistance. The resistance I'm talking about is the resistance of AB, which is the combination of 2 in parallel with 3. Make sense? So once you do that, it's just easy to slice and dice. The worst thing is when you see, I mean, obviously we gave you some problems in the assignments in the book that are take time for you to solve. But the first thing you got to do is break it down. The other thing too is if I had a resistor in series with another resistor here, I'd need to solve for these two first, because they're in series with each other, but in parallel with this. So then I need to solve for this section of the circuit, which is in series with this section of the circuit. So, a lot of students get frustrated and think there's a checklist they could follow or a protocol. No, you just got to pay attention to the individual laws and rules that we established, but there are no two circuits alike. One of the things that I've heard over the years of teaching here, I get a lot of new students that come, or quite frankly, a lot of people that are working in industry already, and they want to come in and they want to learn how to read schematics. Joe, if I come to your program, can I learn how to read schematics? Well, yeah, but we don't have a schematic reading class. There's no schematic reading class. And quite frankly, I wouldn't want to have a schematic reading class, even if I could fill the schematic reading class, because you wouldn't learn anything. What are you doing here by studying this? You're learning how to read a schematic. You're learning to differentiate between those sections of the circuit that are in parallel with each other and those sections that are series components. Later on, when we talk about transistors, right now, those of you in the full-time program did a component ID test today to be able to recognize different types of components. You're going to see what happens when we put a transistor, a diode, a capacitor, different components in different configurations. If I put a capacitor in series, all as it is a capacitor in series. It's still a series circuit. And everything that we've talked about this week still applies. There's going to be some things that are going to be a little bit different with a capacitor in the circuit. We'll cross that bridge when we come to it. But it's still a capacitor connected in series. And there's really only three types of circuits that you're ever going to deal with in your entire career. And that is series, parallel, and complex. So if any of you this week have been grunting, groaning, outside, weeping, gnashing your teeth, you know what? It's all right. Because once you master series, parallel, complex, there's nothing else I'm going to throw at you. There's nothing else that Peter's going to throw at you. Now that being said, we're going to have you looking at some complex circuits in the future. And you know what? You will deceive me. As much as you could pass this test on series, parallel, complex circuits, you're going to forget about it in the future. Because we're going to give you some schematic to read that's got some different components on it, or it's got some components drawn at weird angles or something, and you're going to get your freak on. And you're going to say, boy, they never taught me that. I don't know what to do. You know what you do? You fall back to the basics. The only circuits you're going to encounter in industry are series, parallel, complex. And if it's complex, what laws do you use? Those of series and parallel. You just got to figure out which components are in series and which one are in parallel. I can't say it any stronger. If it's in series, there's one way in, there's one way out. If it's in parallel, that means there's interconnection of all the components. Make sense? Voltage dividers used to set a bias or operating point of various active electronic components. We use voltage dividers to create the voltages that turn on transistors and integrated circuits. They're used to divide a higher voltage to a lower voltage, and this process is often called scaling. Because what are we doing? Voltage rise equals voltage drop, or voltage drops. So voltage drops will always be a fraction or scaling of the total voltage that we apply to the circuit. Does that make sense? We're going to use Ohm's law to solve that. That's the current through a circuit. I'm not done with voltage dividers. Trust me, I'm not done. I'm done when the screen goes black. Then I'm not done when the screen goes black. Then I'm going to show you some stuff on the board. So sit tight. That's not my spiel on voltage dividers. Ohm's law, the current through a circuit is directly proportional. The voltage across the circuit inversely proportional to the resistance. Ohm's law. I is equal to E over R. Current division. Current is directly proportional to voltage across the circuit. If a voltage increases, current increases. If a voltage decreases, current decreases. The voltage drop is equal to the percentage of the dropping resistor to the sum of the dropping network. You know what? I'm giving you this formula. If you dig math, great. If this confuses you, just tune me out. Because everything could be solved with Ohm's law and Watt's law. If you dig math, this is another tool in your box. Let me show you how this thing works. If I want to calculate out my voltage drop across a load, across a resistor, this voltage is going to be equal to my voltage source multiplied by the voltage drop divided by the voltage total. Okay? Let's keep this really, really simple so we can understand how this formula works. If I've got two 100 ohm resistors, if I have two 100 ohm resistors in series with each other, and I want to know what voltage I'm dropping across one of those, I'm going to draw that. You know what I'm talking about? I should be able to use words because the test I give you, the quiz, is going to be words. So that's why I try not to draw too much on the board. I'll draw some stuff on the board, but I don't want to draw too much because Joe, all week you've been drawing stuff on the board and then you ask me a bunch of words. Okay? You got to pass the quizzes and they're words, word problems. Okay? But if I've got this, if I've got this, and I've got 100 volts, let's keep this real simple. Okay? What this formula is showing me is what is our drop here, V drop is equal to voltage total times R drop over R total. Okay? So let's take a look at that. Voltage total is going to be 100 volts times our drop, which is one of these voltage drops, whichever one you're trying to calculate for. Let's say it's this one. It's going to be 100 divided by, what's my total resistance in a circuit? 200. Okay, what's 100 divided by 200? What is it? 0.5. 0.5. What does 0.5 mean? What percentage? Half. It means 50%. So 100 times 50% equals what? 100 divided by 0.5. What does it equal? 50 volts. We could do this one in our head. That's why I want you to do this in your head so you understand the formula. You understand how the formula works? So if you know what this value of total is, and you want to calculate out, let's say that I went ahead and I changed this now, that this is, this is 500 ohms, right? And this is 100 ohms. And I'm asking you what voltage is going to be across this voltage drop here. 100 divided by 5, basically 1/5. 1/5, right? What percentage is 1/5? 2, 4, 6, 8, 10, 20%, right? So that means 20% of my voltage is going to be dropped across this. If 20% is being dropped here, actually no, right? Because this is 100 over 6, 600. So what percentage is that? I was off on my math, I'm sorry. You guys were buying it, man. I want to be your banker. What's 100 divided by 600? Because total resistance is 600. 17. So basically 17% is going to be dropped right here. 100, 17 volts is going to be here. The remainder is going to be, where's the remainder voltage going to be dropped? This is an easy question. Right here. It's got to be. Because this plus this has to equal this. Does that make sense? So this is just another formula for those of you, the math addicts. Want another tool? I like tools. Just ask my wife. Got every tool, right? This is another tool for you. So if I'm giving you, I could sit here all day long and tell you how much voltage is dropped here, how much is here. It's a lot easier to use this formula. Although you could calculate the same thing using straight Ohm's law. It's just going to take you a little bit longer to get to the answer. Make sense? All right. In summary, a series circuit provides only one path for current flow. Series circuit formulas include IT is equal to IR1, equal to IR2, equal to IR3, et cetera, et cetera, et cetera. RT is equal to R1 plus R2 plus R3, et cetera, et cetera, et cetera. Voltage. A series circuit is also known as a voltage divider. So therefore, the sum of the individual voltages must equal source voltage. I is equal to E over R. Well, that's Ohm's law. Power is additive in a series circuit. Power is additive in a parallel circuit. A parallel circuit provides more than one path for current flow. Parallel circuit formulas include IT is equal to IR1 plus IR2 plus IR3. The reciprocal formula for resistance. Voltage is constant across a parallel network. Again, I is equal to E over R. If you want to calculate out how much current is flowing through an individual path. And power total is equal to PR1 plus PR2 plus PR3, et cetera, et cetera, et cetera. Series parallel circuits are solved by using series formulas for the series parts of the circuit, parallel formulas for the parallel parts of the circuit. We talked about voltage dividers, more to come. And we talked about current division, the process of current division in a parallel circuit. Any questions on this? Okay, let's talk about voltage dividers. Kind of get emotional when I talk about voltage dividers. It's kind of like your first real circuit that really does something. Trust me, it'll be good. We're going to need some help, though, because we got some electronic experts in here. We're going to need some help. What kind of a circuit would I use to divide voltage? Series. You got 3 to choose from. Multiple choice answer. Series circuits, parallel circuits, or complex circuits. The correct answer is ding, 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 series. Okay? So a series circuit is also known as a voltage divider, right? Y'all believe me? Okay, so let's go ahead and draw that. This is a voltage divider. Any questions? Unfortunately, this is a voltage divider, but unfortunately, this isn't going to do much for us. This will do a lot for us, but if we effectively want to use it, it really can't be represented like this. Can't be represented like this. First of all, we got to ask ourselves, why would we want to divide up voltage? We want to divide up voltage, like I said in here, to power transistors, to power integrated circuits, to power different types of loads, to power different types of devices. Make sense? Okay. So let's say, as an example, that I have a 48 volt power supply. This is a big rack-mounted power supply that sits there and drones and puts out 48 volts DC. But I've got some different appliances that I want to power from it. Okay? One of the devices that I want to power from it is a 12 volt radio. A simple 12 volt radio. Okay? And that 12 volt radio is a citizen band radio, CB radio. So what I need to do is I want to connect that radio to this resistor right here and have this resistor produce 12 volts across it. So when I go out here and connect my radio, which I'm going to represent, anybody know a symbol that I could use to represent a radio? What's that? R. Yeah. Yeah. There's no special schematic. What I'm going to do here is I'm going to draw a resistor, and that represents the load that a CB radio has. And I'm going to connect it in parallel Do you agree that that's in parallel? So whatever voltage is here is going to be right here. Okay. When I did this, I just changed the dynamics of the circuit. What I just did is I just loaded the voltage divider. So we're going to call this a loaded voltage divider now. And quite frankly, a voltage divider in and of itself, without any loads connected to it, it's kind of stupid. So you guys, if you had read ahead and you really had mastery of it when I'm showing you the voltage divider, you could have said, Joe, that's stupid. What are you going to do? Just put 3 resistors, divide the voltage? What good is that? Okay? What you got to do to make it viable is connect a load to it, a loaded voltage divider. This is a real circuit. We're really going to do something here. We're really going to power a CB radio. Okay? So, to figure out, we know that this is 12 volts because the manufacturer said this is a 12 volt CB radio. You could plug it in your cigarette lighter, you could wire it into your car, and you too could be breaker 19. Make sense? So we know the voltage is going to be 12 volts. The other piece of information that is critical for us is we have to know how much current is required by the CB radio to operate properly. So what we're going to do over here, okay, P, I, V, okay? I know that the CB radio, right, a typical CB radio is about 5 watts. And I know that CB radio, because I got the box, and the salesperson at Radio Shack, we know how smart they are, said I could wire it up into my car. It's a 12 volt system. Okay? So this is going to be 12 volts. So how much current is going to be required to power that radio when I key the microphone and I broadcast out 5 watts? What's the and that's by the way, that's the maximum you'll ever consume in a CB radio. If it's a 5 watt radio, the maximum you're ever going to consume is when you're transmitting. If you're just receiving, that doesn't consume much energy at all. It's when you key that mic and transmit that you're going to start consuming the most power. So I'm thinking worst case scenario here. Okay? So all we need to do here, right, with your calculator, go 5 divided by 12. What did I come up with? 0.42, rounding off, right? 0.411, 0.41666666. Right? That's what I got. Everybody get that? Everybody see how I came with that? Okay. That's assuming the radio is 100% efficient. You know what I mean? Like every ounce of current is going into generating that, which there's going to be losses. How do I know there's going to be losses? When I use the radio, it's going to get hot. All that energy is not going to get out the antenna. If you get that working, you get all the energy getting out the antenna, give me a call. I have my attorney contact you. I personally fly you to Bimini. I'll set you up. Pour you your first cocktail. Okay? I'll set the tab up for you. So what I'm going to do with this, just for the case of example, is I'm going to round this. Generally speaking, a CB radio is going to take a minimum of half an amp at 12 volts. A minimum half an amp, and probably it's going to be even more than that. But in order for it to transmit out 5 watts, you see the math. Does everybody see the math? Okay. So I am going to assume that this here is 0.5 amps. So we know everything about the CB radio now. It's a 12 volt, 5 amps, 5 watt radio. I feel pretty good about it. We could calculate out the internal resistance of it if we wanted to. I don't see the benefit of doing that now. We don't need to do that right now. Make sense? Okay. Voltage divider. Voltage divider. I've got another device. And this other device that I have is, by the way, we're not going to put this in your car anymore. We're going to put this radio, CB radio, on my boat. Why I want a CB radio on a boat, I do not know. It's a power thing, man. I want to talk with truckers, so I'm going underneath the bridge. Ha ha, you're stuck in traffic, I'm going underneath it. Ha ha, I'm on my boat. Okay. I'm going to install a radar system. And the radar system that I could represent with a resistor is going to be connected across these two resistors. The voltage of my commercial radar system is 24 volts DC. And it puts out 200 watts. How much current is going to be needed to go through this device in order for it to transmit out 200 watts? Again, if you get confused, draw the triangle, P, I, V, 200 watts divided by 24. What do you come up with? How much? 0.12, 0.12?
120 milliamps.
How much? We got a big disparity here.
8.33.
That makes sense, right? If a half an amp can power a CB radio, it's going to have to be more than a half an amp to power a 200 watt transmitter, right? Yeah, even at double the voltage. So all I got to do here is power is 200 divided by how much? What's our voltage? 24. $8.33, and that assumes what? That assumes 100% efficiency. Do we get 100% efficiency out of this stuff? To be honest with you, if we're lucky, if some of this stuff operates at 80% efficiency, 20% of the energy gets consumed as heat. Okay? So just for the case of example, I'm going to say that this thing really, in order for it to work properly, is going to need 10 amps. And this might be what the placard data on the back of the radar says, or the manual says. Okay? But you understand that which one of these are real. If you do the math, this number could be good, this number could be good, and if that's the case, then we know that the answer is going to be 8.33 amps. But in reality, because of the losses, because of the property of resistance, we're probably going to be consuming really about 10 amps. Make sense? Okay. So, now what I have is a circuit, a viable circuit. And by the way, if I want 24 volts here, and I am getting this voltage across these two resistors, what voltage must I be dropping across this resistor right here? How much?
12.
Why 12?
Because it's double this, 12 volts.
Yeah, and I am connecting this radar unit in parallel. I love it when you talk that way. Parallel with these two resistors that are in a voltage divider network. Okay, so what we did is we just built a voltage divider, a loaded voltage divider. But we've got to analyze it now. We've got to analyze it. And this is where the author pulled numbers out of his backside, and he really didn't justify it, and I don't even know where that's coming from. That's why we're having this lesson. Question?
But there's the other resistor up there that's hanging out by itself doing nothing.
It's 24.
It has to be 24, right? You get 48.
Why wouldn't that?
This, remember, this here, I bought this military surplus. This is a 48 volt power supply, okay? So it converts my ship's power to 48 volts DC.
That's still 48 volts at the end of it. It's all coming back together.
Yeah. So if this is 48 and this is 12 and this is 12, what's this got to be? 24. Why?
Because you got to drop it down.
Got to go to 0.
Come on, guys. Quote me what I've been quoting you.
Your drop has to equal the rise.
Absolutely, because the drops have to equal the rise. I'm putting 48 volt rise in. I'm getting 48 volts a drop. 12 here, 12 here, 24 here. All voltage drops present and accounted for. Make sense? Okay, so this is cool. It's really going to work like this. But we don't know the math. We don't know what values of resistance to use here. This is where it gets tricky. This is where there's another thumb rule. That's why you come to lecture. Okay, if the book was that good, you could be home in your underwear studying right now. and I could be home in my underwear correcting your work. Instead, here I'm dressed up wearing lab coats, you're wearing lab coats, and we're having this interactive lesson. The thumb rule is, you ready for this? The bleeder current needs to be 1/10 of the total load current. The bleeder current needs to be 1/10 of the total load current. How many of you buy that? You better buy it, I just sold it to you. Now the question is, what the heck is he talking about bleeder current? The bleeder current is the current flowing through the first resistor that starts the voltage division process. So by me saying that, first of all, we got to determine what is our total load current? What's our total load current in this circuit? 28? 48? Bzz, total load current. Current is measured in amps. What is my total load current in this circuit? 10.5. What? Pounds, ounces, kilograms, amps. I love it when you talk that way. Total load current is 10.5 amps. Everybody see how we did that? The only loads in this circuit, this is a voltage divider. These are my loads. The only loads in the circuit here are, what the heck was this, a CB radio? Breaker 19 CB, right? And then this was a radar system. Radar system consumes 10 amps. This consumes a half an amp. So my total load current is 10.5 amps. Do you all agree with that? Okay. So I said the thumb rule is that the bleeder current is 1/10 of the total load current. What's 1/10 of 10.5?
1.005.
Okay. So 10.5 divided by 10, 1/10. So 1.05 amps. Do you all agree with that? Getting some puzzled looks. 1/10 my total load. 1/10 of 10.5 is 1.05. Agree with that? So that's how much current. I'm going to do something here. I'm going to change the color to make it stand out. Okay. Is going to be passing through this first resistor. Very good. Okay. And this is going to be 1.05 amps.
Book gave an arbitrary number of 10 milliamps.
And again, that's where's that coming from?
Pulled it out exactly. The text was definitely vague on that.
So at least remember my deal. So right there, we just unlocked the entire circuit. We just unlocked the entire circuit because what we've got here is 1.05 amps coming up out of this node. How much current do we have coming up through here?
1.5.
Where'd that number come from?
Printed the paperwork.
Thank you, the paperwork, okay? Or your calculation based on, if the paperwork left out the current demand, you know it's a 5-watt radio, and you again, as long as you can prove it. Got to be able to prove it to somebody, okay? So we called that 0.5. So we've got 0.5 amps coming up through here. All the current that comes up through the radio is going to come here into this node right here. So I got 0.5 amps coming in from this angle. I got 1.05 coming in from this angle. Can any tell me about how much current's going to be going through this? How'd you come up with that? And how'd you come up with that? Is that just is that a notion?
It's a current divider.
It's a current divider. It is a current divider.
The node they have to combine again.
Okay? But again, what's going to bring tears to my eyes is if you quote me laws. Are there any laws that govern what's happening here in this node? What is it? Absolutely. Kirchhoff's law. I got 1.05 coming up here. I got 0.5 here. We got a traffic cop standing in the middle of that intersection. How much current's driving away from him? 1.55 amps. It's gotta. If this thing's functioning, it's gotta work like this. So I've got 1.55 amps coming up through here. Okay. How much current is coming up through this load? How do we know that? Placard data, technical documentation, calculation utilizing Watt's law. I don't know. Because Joe said so. Actually, I didn't. All I gave you is that 24 volts and the 200 watts. You folks really calculated that out. The only curveball that I shot you in any of this was the efficiency bit. I'm talking about efficiency. The book doesn't even talk about that. But you don't get 100% of anything. You don't. There's nothing that's 100% efficient. So I got 10 amps coming up through my radar system. That means that 10 amps makes a 90-degree corner at the speed of light. Right? 10 amps.
11.55 amps.
How do we get an extra amp?
How'd you get an extra amp with what?
Well, we got 10, we got 0.5 amp, half an amp.
What was the rule here? What was the whole thing on unlocking this entire circuit? What did I call this resistor? The bleeder resistor. And that's what's starting the whole process. We have to have some current going through that to create. And the reason that we use 1/10, so is that these loads come on and offline, the circuit's going to have stability because that CB is not always going to be on. And when we turn the CB off, we don't want the whole circuit to go cattywampus. We want it to be somewhat balanced. Same thing with the radar system. So it's a thumb rule. It's not an absolute, it's a thumb rule that should give us consistency of operation for this circuit. Make sense? So we know that we have 11.55 amps coming up through here. Boom. If I've got 11.55 amps flowing into my power supply, how many amps must I have flowing out of my power supply? The same. Okay? So that means I've got 11.55 amps flowing into this node. If I've got 11.55 amps flowing into this node and 1.05 amps flowing out of this node, how much current do I have flowing in this direction? How much? 10.5 amps. Do you agree with that? If I've got 10.5 amps flowing into this node and I got 0.5 flowing in this node, how much current am I going to have flowing in this direction? Isn't that the same number we started off with? So I just proved that this works. I just traced all the current through this circuit in doing this. Now, the easy part of the analysis VIR, let's calculate out resistance, voltage over current. Voltage over current, right? Voltage 12 over 1.05. 12 over 1.05 is going to give me this value of resistance. R is going to be equal to 11.428 ohms. That's what I came up with. Are we going to find 11.428 ohm resistor?
No.
Can we find something close? Maybe we could find one with tolerance as a 10 ohm resistor that's on the high side, 20% tolerance. We could find one that's within that, right? Because a 10 ohm resistor could be anywhere from 12 ohms to 8 ohms. So yeah, we might be able to find something close to that. It's not going to be that critical.
What happens if your resistor only actually has 8 ohms if you get that big of a tolerance?
You're going to get less of a voltage drop there, so that is kind of critical.
Higher up than lower?
The bigger the resistor, the bigger the voltage drop. The smaller the resistor, the smaller. So we can do the same thing up here, right? 12 volts divided by 1.55 amps. 7.7 ohms. And then finally here up at the top, 24 divided by 11.55. 2.08 ohms. And this is how you analyze a loaded voltage divider. It's really nothing unique, is it? All we did is apply Ohm's law, Watt's law, Kirchhoff's law. You know, one of the other things that's kind of fun that I could do with this circuit, I think it's fun. You'll probably think I'm horrible for doing that kind of stuff. What is it? It's the exact same circuit. And to be honest with you, this is how this thing would really be connected. This is how it would be really connected. Your 48 volt power supply would be connected to what kind of ground? Electrical ground. Not necessarily earth ground, electrical ground, which is typically a chassis ground or a frame of a vehicle or a boat, the hull of a ship, right? The frame of a train car. This is how it's going to be done, because we're going to use the frame as a conductor. Circuit's going to operate exactly the same. We're going to get the bottom of the circuit here, the bleeder resistor, connect that also to ground, chassis ground. Okay? We're going to connect the negative lead of our radio directly to chassis ground. We're going to connect the negative lead of our radar. The radar's kind of mounted in an unusual position, you know. I got that, you know, the pulpit up there, I drive the boat, I want the little radar there. So I'm going to have to run quite a bit of cable, but I'm still going to connect it to chassis ground. And this is the exact same circuit that you just analyzed. I just made it more complex, complicated looking by putting these grounds in. Basically, when you see this in a circuit, you know that electrically all of these, wherever the heck that thing is, right, all of these are interconnected. Don't let me screw you up with this kind of stuff. And it's assumed that you know how to interpret this type of stuff. Questions?
With the beginning part where you need to figure out the meter current,
Yeah.
take the total current, which is 10.5, and divide that by 110.
Yeah.
Well, I'm not coming up. It comes up with 105, not 1.05.
10.5 divided by 10.
Oh, divided by 10.
1/10 is 10, right? 1/10 is 10. Make sense? 10.5. 1.05.
You can multiply it by 0.1, you get the same answer.
10% of 100.
Another question? No? Questions? So you could sit here, and again, that's a thumb rule, but you could use it for analysis, and then if somebody asks you, how the heck did you come up with that? How did you, what, you want me to buy these parts? How'd you come up with that? Well, I used it as a thumb rule that I want my bleeder current, oh, okay. As opposed to the author who just, again, I don't know where those numbers came from. I don't know, I don't want to know, it is what it is. So in the future, use that 1/10. I use that 1/10, you're not even going to get the, I mean, you won't get the answer that the author gets in the book. I don't know what you got to do it wrong to get the number that the author gets in the book. So there's, in the future, when you see loaded voltage dividers, use that 1/10 rule, unless you're told otherwise. You know, there might be an engineer that knows a lot more math than we know. They say, no, we want you to assume 15% or 20% or whatever. But you need some guidance. We're not engineers. You guys remember that? You know that? We're not engineers. Anybody here want to be an engineer? Honestly? No offense, honestly. Okay? If you want to be an engineer, that's good. You're going to immerse yourself more in the world of theory. We immerse ourselves more in the world of reality. So we're going to do what we're told to do. Actually had a meeting today with engineer. We're looking at some engineering starting some engineering classes here at Lake Washington, a parallel program to pursue your engineering degree. And the way he was talking about it too, like a pyramid. It's like a pyramid. You got your research science, a handful of research people up here at the top of the pyramid. Then you've got engineers designing the stuff, and then you got technicians making the stuff work. So there's a lot more technician jobs out there to support engineering, and the engineering supports R&D. You know, Boeing only has a handful of people that sit around and think about weird crap all day long. Thank God, right? Because then what they do is they farm it out to the engineers and say, hey, make this work. Make this work. And then the engineers figure it out, the calculations and everything, and then they give it to the technicians and they say, make this work. And then we are the last line of defense. And the only thing that we have to fall back on are the laws of physics and the theory of operation. That's all we have to fall back on. And if you can apply that, then you're going to be ahead of the game. There's no question about it. No question about it. This actually worked out pretty well for us with last week doing 7 and 8 and then saving chapter 9 for this week because that's the only thing that we're going to do tonight is going to be chapter 9, magnetism. And this is a huge chapter. I don't think there's any other property that has had such a profound impact on society as magnetism, as you're soon going to see. I mean, if it weren't for the property of magnetism, electronics and electricity would not be what it is today. It's really that simple. So with that introduction, let's forge ahead with chapter 9, magnetism. After completing this chapter, you're going to be able to identify 3 types of magnets, describe the basic shapes of magnets, describe the difference between permanent magnets and temporary magnets, describe how the Earth functions as a magnet, state the laws of magnetism, explain magnetism based on the theory of atoms and electron spin, explain magnetism based on the domain theory, identify flux lines and their significance, define permeability, describe the magnetic effects of current flowing through a conductor, describe the principle of an electromagnet, describe how to determine the polarity of an electromagnet using the left-hand rule, define magnetic induction, define retentivity and residual magnetism, define a magnetic shield, describe how magnetism is used to generate electricity, state the basic laws of magnetism, describe how the left-hand rule for generators can be used to determine the polarity of induced voltage, describe how AC and DC generators convert mechanical energy into electrical energy, describe how a relay operates as an electromechanical switch, discuss the similarities between a doorbell and a relay, discuss the similarities between a solenoid and a relay, describe how a magnetic phonograph cartridge works, describe how a loudspeaker works, describe how information can be stored and retrieved using magnetic recording, and describe how a DC motor operates. I don't think we've had any chapter up to this point that has had so many objectives, and this just shows us the far-reaching hand of the property of magnetism. It's everywhere. All the magic that's done in today's society is brought to us really by magnetism. I'm not bragging about it. It's really what takes place. Magnets, natural, there's really several different types, 3 types. Natural magnet is derived from magnetite. And it just so happens that I've got a couple pieces of magnetite in my pocket. These are natural magnets, okay? It's like found in the Earth's crust. Here it is. So we'll pass this around and we'll let you play with polished magnetite, okay? So that's kind of cool stuff. So that's found in the Earth's crust, and it's just a natural magnet. Artificial magnet could be created by rubbing a piece of soft iron with a piece of magnetite. So if you've got a piece of soft iron and, I see you underneath what the heck are you doing under there? I'm creating an artificial magnet by rubbing a piece of soft iron with a piece of magnetite. And what it's going to do is it's going to pull that magnetic property off of the magnetite and transfer it to your piece of soft metal. Actually, that's a trick with a lot of mechanics, right? If you magnetize the tip of a screwdriver, it comes in handy for picking up things that you drop into odd places. Finally, the third type of a magnet is an electromagnet. This is created by current flowing through a coil of wire. Basically, when we pass current through a coil of wire, we're going to develop a magnetic field. And in concentrating that, that's how we have an electromagnet. So electromagnets range in size from very, very small to, if you've ever seen like at a junkyard, a scrap yard, on a crane, they've got an electromagnet. You turn it on, it like, you know, picks up a car or whatever. Actually, my favorite application, I'm a big James Bond fan. Remember that Jaws dude? It was like, you know, like biting things, like train cars and stuff. And, you know, they turned on the big electromagnet and boom, pow. He gets pulled right up to the ceiling on that. So that was a giant electromagnet. I'd hate to have your credit cards anywhere near that, as your credit cards have magnetic strips on it, and a strong electromagnet will probably desensitize those cards. Here's some examples of some magnets. Come in variety. It's my personal collection. Just kidding. This is torrid core, meaning it's a donut shaped. It's circular. This is a standard bar magnet. This would be like a horseshoe magnet because it kind of looks like a horseshoe. The thing to remember is that all these magnets are going to have a north pole and a south pole. Even that magnetite that we're passing around there, if you try holding it unusual, it won't even attach each other. Basically, the reason that those four pieces of magnetite are attracted to each other is because the north pole is attracted to the south pole of the other magnet, which is attracted to the north pole, the south pole of the other magnet. North and north ain't gonna work. Permanent magnets retain their magnetic properties. That's why they're called permanent magnets. Temporary magnets are only going to retain a small portion of their magnetic properties. That's why they're called temporary. Okay, and over time that magnetic field may deteriorate or be altered. So permanent magnet will retain the magnetic properties. Now this is kind of cool, and I'm sure it's no surprise to any of you. The Earth is a giant freaking magnet. Okay, and it has to do with the core of the Earth and then the crust, right? But we basically have a giant North Pole and we have a giant South Pole. The problem about the North Pole and the South Pole, I got to give you a geography lesson here. If I wanted to go find Santa Claus, where would I look and how would I get there? How could I navigate my way to this place? With a compass. And where am I trying to get to? Okay, so you want me to use a compass to try to get to the North Pole to try to find Santa Claus?
Magnetic pole.
To get to the magnetic North Pole. If I get to the magnetic North Pole, am I going to find Santa Claus? No. Nowhere to be found. In order for me to find Santa Claus, what am I going to have to do? I'm going to have to go to the True North Pole, or the North Geographic Pole. The North Geographic Pole, which is literally the top of the Earth. Anybody want to take a wild guess what the best way of getting up there might be? What's that? Well, I'm talking about means of transportation. What's that?
Santa's reindeer.
Submarine. Submarine, yeah. You could be in a short sleeve shirt and go up there, surface at the North Pole, because it's underneath the Arctic Ocean. So you could surface at the North Pole. So I just happened to flaunt that. I actually have never been to the North Pole. My submarine has been to the North Pole. At home, I've got water from the North Pole in a vial from my submarine that went to the North Pole. My submarine actually delivered, believe it or not, Al Gore to the North Pole. It was after I was off the sub, but they did a mission and went to the North Geographic Pole. And typically on the ice, they put a lot of research camps to conduct research, magnetic research, and that's the place to do it. So the North Magnetic Pole is, this illustration, it's an artist's depiction, it's not very accurate. The North Geographic Pole is going to be somewhere up here, up north of Labrador. And it moves about 2 kilometers per year. And it's actually moving in a northwesterly direction. And the variance, the magnetic variance. Does anybody know the magnetic variance? The difference here between the North Pole geographic pole and where the North magnetic pole is? I know because I'm a pilot, and it's kind of important, okay? Because if I start flying northbound or whatever, which am I going geographic north or am I going magnetic north? And the difference here in the Seattle area is between 19 and 20 degrees difference. It's pretty significant. So this hallway right out here in this wing is aligned pretty much with the North geographic pole. If you could walk straight, which none of us could do, we've got a dominant leg, and you walked out this hall and just kept walking north, eventually you're going to get to the North Pole, find Santa Claus. It's all going to be good. If you had a compass and you stepped outside the door here and you looked, that North magnetic pole is going to be literally over in this direction here. So it's very important because, again, in the aircraft, you've got a compass. You set your gyro compass for that magnetic heading. And I bet you folks never realized magnetic properties had such a profound impact on all these different things. If any of you are familiar with airports, airport runways are designated based on their magnetic heading. So SeaTac Airport's got 3 runways, but they're all parallel with each other, so they all have the same numbers, okay? If you're headed southbound, like typically when we have crappy weather here in Seattle, if you look up and you see an airplane going on the SeaTac, what he's going to do is he's going to fly out over Lake Magnolia, right, then turn inbound, and then what he's going to do is land on runway 16. Because if you rounded that, it's on a compass heading of 160. So how do you make sure since there's 3 runways down there, because we all remember, those of us that have lived in the area a while, that 3rd runway when they put it in, it was very controversial. It's 16 left, 16 center, and 16 right. That's how they designate which runway you're cleared to land on. Add 180 degrees to that, and you end up with what? Runway... No, 16 plus 180 degrees, runway 34. So if you're landing northbound at SeaTac Airport, you're cleared to land on runway 34 center, 34 left, or 34 right, okay? Ironically, and the reason that they select runways is they do wind studies to determine where the prevailing winds are. You want to take off into the wind and you want to land into the wind. So primarily here in central Puget Sound, that's pretty much how all the runways are. Auburn Airport, 1634. Renton Airport, 1634. SeaTac, 1634. Boeing Field is a little bit different. It's runway 31 northbound, so there's going to be a slight variance in runway 13 in the opposite direction. It's just how the winds are kind of funneled there by the location of Boeing Field. But Renton Airport used to be runway 33, but because of that magnetic precession, what they've had to do is they've had to renumber. And you think, oh, it's no big deal. You send a guy out there with a can of paint and you paint the new number on the runway. It's not that easy. All of the procedures, all of the approach procedures, all of the publications, all of the databases all have to be updated. It's really a big thing. So eventually, all runways are going to have to change their number as that north magnetic pole continues to fluctuate. Why am I telling you this in an electronics class? A lot of you are going to go to work in industries that are associated with electronic navigation. And you got to know this. I mean, you don't have to memorize it. I'm not going to quiz you on this magnetic precession and the 19-20 degrees variance here in Seattle, but a lot of you are going to go to work in electronic navigation systems, and you need to understand the difference between the two. Make sense? The laws of magnetism, I think most of you probably remember this from elementary school. Unlike magnetic poles attract each other, right? Unlike attract. So a north is going to be attracted to a south, the south is going to be attracted to a north. Like magnetic poles repel each other. North and a north, they're going to push each other away. South and a south, push each other away. This is actually kind of interesting too, because it has some applications now, like magnetic levitation. Some of these rail systems that they're actually, the whole train levitates magnetically. That's how they're doing it. That's how you get a whole train to levitate, because North Pole and the North Pole, They'll basically push each other away. And then once you've got something floating like that, it doesn't take a whole lot of energy to move a train. I mean, think about that. I don't know if you've ever even thought about why do we use trains. I mean, trains, that wheel on a rail, very little friction. So it takes very little energy to move a bunch of stuff, right? If you could kick it up even a notch further, I mean, we still have to overcome the friction of the bearings and the axle and the wheels on the track. Now, if you could levitate the entire train magnetically, then just give it a little push, and that thing's going to be able to move with hardly any energy. So these are a lot of the advancements that we probably want to stay tuned for because in the name of efficiency, we're trying to play with a lot of this stuff. Color code for magnets. Color code for magnets. Red is the color code that we use for North Pole. Blue is the color code that we use for the South Pole. So if we were going in search of Santa Claus, and we got to the North Geographic Pole, how would we know we got there? What would we see? Bzz. There'd probably be reindeer, but what color pole would there be? Red and white, very good. Red and white pole, we know that. Candy cane, right? If you're at the South Pole, what color would the pole be? Blue and white. Striped pole, right? I mean, if you got to follow that same tradition. If you're outside a place that has a pole that's red, white, and blue, where are you? Bingo. Excellent. Very good. I got students that just, same students that don't know what a barber shop is. I like the barber shop. That's how I roll. That's my thing. So yeah, that's the color code for magnets. Magnetism, the property of magnetism, can be traced to the atom. As electrons orbit the nucleus, they also spin on their axis. This electrostatic charge produces a magnetic field. So even these electrons are going to have magnetic properties. The direction of the magnetic field is the same as the electron's direction of spin. So even at a subatomic level, we're going to have properties of magnetism. Ferromagnetic materials, ferro meaning materials that contain ferrite, this is the stuff that will rust. Okay, if the metal will rust, it contains a high amount of ferrite. So any ferromagnetic materials are materials that respond to magnetic fields. Any of you have magnets at home stuck to your refrigerator? Okay, your refrigerator is made out of a ferromagnetic material. If it were not painted, it would rust. Plain and simple. If not, the magnets wouldn't stick to it. It's actually the old trick too, if you're going and buying a used car or whatever and you're looking for Bondo, right? Put a magnet over it, and obviously if it sticks, you know that's all original with no Bondo. You know, you all of a sudden get to an area and that magnet doesn't want to stick. Don't try this with a Corvette, of course. Corvette is fiberglass. And actually with all the cars now, with all the plastic on them, magnets aren't going to stick well to plastic. Atoms combine into domains or groups. When unmagnetized, the domains are random. This is what we're looking at here in this illustration. This is random domains. Okay? This is an unmagnetized piece of ferromagnetic material. As soon as we magnetize it, watch, this is kind of cool. Boom! When magnetized, the domains align in a common direction and the material becomes a magnet. So if you've got my magnetite that we're passing around and you rub a screwdriver up against that, this is ultimately what's going to happen. You're going to align those domains and it's going to become magnetic.
What was the difference between a ferrous and non-ferrous metal again?
Ferro contains ferrite, and that's the iron content that makes stuff rust, basically. Now, a magnetic field A magnetic field, this is kind of where you got to hit the I believe button, right? It's invisible lines of force that surround a magnet. These invisible lines are called flux lines. We've got to be careful because those of you in ELEC 115 are learning about flux, right? It's a different kind of flux. There's two types of flux in electronics. There's magnetic flux that we're talking about tonight, and there's also flux that we use as a cleaning agent for soldering, okay? You're not going to use a magnetic field for cleaning and soldering. To the best of my knowledge, and a magnetic field has never been used as a cleaning agent. Flux, however, is used as a cleaning agent, different type of flux. Okay, so this word has two meanings in electronics. And don't forget, one of the reasons that you're here is to learn the language of electronics. I wish I had had me as an instructor, okay, because I was kind of like flux, and I was like, well, we're going to use magnetic lines of force to, clean something to make it more solderable. Just, nobody ever explained that to me, and I wasn't the smartest student. These flux lines have polarity, and that polarity is north to south. North to south, and it always forms a complete loop. They do not cross each other, and they tend to form the smallest possible loop. Some of you may have done this like in 3rd grade. You got a magnet. Bar magnet, you got a piece of paper, and on top of that piece of paper you sprinkle iron filings. The iron filings will actually form a pattern, and that pattern that you see is the invisible lines of force. It is the flux lines. That's exactly what you're doing by spreading those iron filings on that, is seeing the lines of flux as a visual aid, if you will. Permeability, there's a new word for you. Permeability is the ability of a material to accept magnetic lines of force. An example of something that has a high level of permeability would be your refrigerator at home, if you've got magnets stuck to it. My last refrigerator that I bought, and how many of you here buy a refrigerator because you got nothing better to do? And how many of you buy a refrigerator because your food is all spoiled and your old one died? That's normally how you go about it. So, my last refrigerator, I was in a panic and I found one, and and they never fit right. They've actually made them bigger. So if you want one to fit into the small hole, you got to get a custom refrigerator. So a smaller custom refrigerator costs more than the big one that doesn't fit right. So I just got the big one. It doesn't fit right. It's bigger or whatever. But I get home and I paid a lot of money for this thing. And then I get my magnets. And I got, the magnets to put Junior's work up on and everything else, and my favorite pizza place. Magnets won't even stick to this thing because it's like this designer facade. So you could, what the heck is this? So you got to put the magnets on the side. You got to put them on the side because the front is so that you could make it, I don't know. I just want something to keep my stuff cold. That's all I want. So permeability is a material that readily accepts these lines of force. If a magnet will stick to it, it has a high level of permeability. Now there's a direct correlation between electricity and magnetism, probably why we're talking about it tonight, right, in electronics program. A magnetic field is generated when current flows through a wire, period. Period. Let me say that again. A magnetic field is generated when current flows through a wire, period. So, when you plug something into an extension cord, is it generating a magnetic field? You betcha. When you connect a speaker up to an amplifier and you've got current flowing through that wire to the speaker, are you generating a magnetic field? Yeah. Okay. Anytime current flows through a conductor, you generate a magnetic field. So, if you could see magnetic fields and you had an energized piece of equipment, you would see all of these lines of flux that are being formed by simply turning a piece of electronics on. By simply turning a piece of electronics on or an electrical circuit on, you're generating lines of flux. Sometimes it's something that we need to be aware of, other times it's something we need to discount. An example would be in your home, okay? Typically how your house is wired up, the magnetic fields that are generated by your home are not sufficient enough to cause you any worries. They're not going to demagnetize your credit cards, they're not going to, you know, screw up your brain, you know, but still, they are generating magnetic fields. There's no way around it.
Wasn't there talk a while ago about staring at a computer screen for too long, the magnetic fields could affect you after a while?
Yeah, and again, with some computer screens, there's some higher frequencies that are used, and I mean, it's the same thing. You know, is it harmful or harmless? I don't know. There's also some laws on the books about building schools underneath power lines. You know, so if there was nothing there, why are there laws on the book about that? You know, I've never had an interest of, well, my only interest of living underneath a power line would be able to perhaps tap into that magnetic field and lower my power bill, which of course would be illegal and not above board, and I would never do that. But I never really had a whole lot of interest of like living underneath power lines, you know, because it's just an unknown. You just don't know, because those high voltage wires, they move a lot of current through it. I mean, you create huge magnetic fields. I don't know if you realize this, but if you get a fluorescent tube and you go underneath a lot of these high voltage wires, you could excite the gases inside the fluorescent tube and light it up. Look, Mom, it's lighting up with no strings attached. So if it could ionize gas inside a fluorescent tube, you know, what's it doing to your, you know, I don't know about you. You know, but I've had a pretty good life. I got a lot of good memories. I do not want to scramble those memories. So I'm going to keep my brain away from magnetic fields and anything else that will alter some of these fond memories that I have from my youth.
My journeyman told me that exact same thing. My mom was going to buy a house by power lines. And he said, well, go out there with a fluorescent tube and hang it up. And if it lights up, she don't want the house.
Yeah. So this is exactly what it would look like here. We have current flowing through a conductor, and we're going to generate this magnetic field around the outside.
I don't know if this is stupid question or not, but if you have a magnetic field, doesn't mean stuff's going to stick to it, right?
If the magnetic field is strong enough, stuff would stick to it. Normally, the magnetic field is not that strong, so stuff won't necessarily stick to it. Like iron filings are not necessarily going to be attracted, you know, to a low energy circuit that's energized. But that being said, there's still a magnetic field there. It's just not strong enough to, you know, attract an iron filing, you know, to stick to the circuit. Thank goodness. You know, or whenever we turned anything on, it would be, you know. Now, yeah, it would have to be a significant enough field to attract, you know, current to do that. The current going through it would have to be sufficient enough to create a big enough magnetic field to attract an iron filing. Electromagnets, composed of many turns of wire close together. Because as I just said, one piece of wire may not be strong enough. What happens if you get that and then you wrap it around again? Now you just doubled it. You do it a third time, you tripled it. Fourth time, quadrupled it. The math is simple. The math is that simple. So every time with a winding, you add a winding, you're increasing it, that magnetic field that you're generating by it. So the principle of an electromagnet, when wire is twisted into a loop, the flux lines are brought together. The flux lines are then concentrated at the center of the loop, and we establish a north and south pole. Anytime you create a magnetic field, you're creating both a north pole and a south pole. The strength of the magnetic field can be increased three ways. The more turns of wire, the more flux lines are going to be added together and concentrated. The greater the current, the greater the number of flux lines that are going to be generated. Okay, this only carries you so far though, because what happens, you're passing current through what? A piece of wire. What property does wire have associated with it? Resistance. So you just can't keep increasing the current, because if you keep increasing the current, eventually what's going to happen? It's going to become a fuse. I mean, even if the wire is this thick, you have enough current go through wire that's this thick, eventually you're going to part that wire, okay? And it's going to begin to get hot. And so it could cause an electrical fire. So you just can't keep saying, and let me take another step back. You know what kind of wire we're going to use to make these coils? We're going to use what's called magnetic wire. And magnetic wire is not wire that's inherently magnetic. Magnetic wire is wire that's used to make windings. And what it is thin copper wire, but it has a lacquer coating on the outside. There's an example right there, outstanding. That's magnetic wire. Okay? And it looks like copper wire, and it is copper wire, but on the outside is a thin lacquer coating. That lacquer coating acts as an insulator, an electrical insulator, to prevent the wire from shorting. Because if I wound wire over itself, why would current want to go all the way, keep going through the wire? It would just short right out. Okay, so we have to keep it insulated by using that lacquer on it. So let's get back to this bullet statement here. The greater the current, the greater the number of flux lines generated. I'm going to get to a point that I cramp so much current through that coil, it's going to begin to get hot. If any of you have ever done paint removal, you know that paint removal, when you're using a heat gun, works really, really good for removing paint. It works good on removing lacquer too. So once you have too much current go through that coil, you're going to compromise that lacquer coating, and that's the end of your coil. By the way, if any of you have ever smelt a coil, that's the end of the coil. By the time you smell it, it's over with. You've already compromised the integrity of it. It'll never work right again. Transformers, motors, coils, any of that stuff. Any of that stuff. If you smell it, if it gets that hot, forget it. Another way that we could increase the magnetic field is we could insert a ferromagnetic core into the center of the coil, usually iron. Iron has a high level of permeability. By putting it into the center of the coil and then wrapping the coil around it, it's going to enhance the magnetic characteristics. So by putting in a ferromagnetic core, it's going to enhance the characteristics. Now, magnetic induction is the effect a magnet has on an object without physical contact. The effect a magnet has on an object without physical contact. This is the cool thing, and I think some of you were playing around even with these magnets here, right? And how they're not even touching, but yet it's having an effect on the other magnet. That's magnetic induction. Residual magnetism is the magnetic field that remains when an object is separated from a magnet. We used to have literally a big problem with residual magnetism. This is something that I don't know if any of you want to make a wild guess at this here. I'm thinking of a very, very large object that developed magnetic properties, and those magnetic properties needed to be removed or it could compromise the position of this large steel cylindrical object. Submarine. Submarine. Big, big, big problem in submarining. Because the submarine, being made out of a ferromagnetic material, would pick up the Earth's magnetic field and gradually it would become magnetized. And the problem was there was equipment that would detect the magnetic anomaly. So there's no way of seeing a submarine, and some of our submarines are so quiet you would never even hear the submarine. But if you're flying in an anti-submarine warfare aircraft and you pick up a magnetic anomaly, a large submerged contact that's creating a magnetic variation, chances are you found a submarine. So this is exactly what, if any of you ever go up around Whidbey Island and you see those the big 4-engine turboprop aircraft, P3s. No, not those. Those are AWACS. Those are like airborne command posts. The P-3 Orion is a submarine hunter, and off the back of it, you'll see like this little thing that looks like a stinger, and that's what that is called MAD gear, magnetic anomaly detection. So when you're flying around, typically what they just wouldn't be looking for a magnetic anomaly. What they would typically do is have a circular scan radar, so when they stick up a periscope, all of a sudden they get a blip, blip. If it's a good radar operator, that's all it takes, are two blips, and then he'll shut the radar down. So what they'll do is they'll continue to fly, and then he'll go to a sector scan. Okay, so from a circular scan, blip, blip, then he'll shut it off. Then he knows where he's looking for because he saw it on the radar screen. He'll go to a sector scan, right? A sector scan is back and forth like this. So then all of it's going to be then he'll shut the radar off. And then he'll drive his cursor over to where he had that contact and hit enter. Autopilot will bring the airplane to that point in the ocean. And then the operator is looking at the MAD gear. And then all of a sudden they start to get a magnetic anomaly. At that point they pop a flare out over the target. If you're at war, at that point the aircraft is going to go into a bank, start to open the bomb bay doors, fly right over that point, put a torpedo in the water. It's a smart torpedo. It's going to find the target and blow it up. That's how you die in a submarine in a combat situation. Okay. The only thing that we would know, my job was to detect that, so I was good at picking up the blip, blip. But again, the good guys, the good operators, two sweeps and they'd pick you up. The British came out with a radar that basically 400 miles away could spot a beer can floating in the water. So it's kind of like when I saw that technology come out, I'm like, I think it's time for me to move on to a different career. Because if this turns into a shooting war, we're dead really quick. Really, really quick. So, to get rid of this residual magnetism, if any of you are into boating or fishing and you ever have the opportunity to get on Hood Canal, don't get too close to the submarine base because they have gunboats and stuff and it's all restricted area. But over at the submarine base in Bangor, they've got a giant pier. It's a degaussing pier. And what they'll do is pull an entire Trident submarine into it and pull off that magnetic field and get it back to just an unmagnetized piece of steel. But over time, that magnetic field will build up again and it needs to be stripped off periodically or you're going to have a real profound magnetic signature.
Ship
How
can't
long
do
is
that itself though. It has to go to a dock and have it removed.
Correct, yeah.
How long does it take for it to build up?
If I told you, I'd have to kill you. A lot of it depends where you operate to and what the magnetic, if you're doing a lot of stuff up north and there's some stronger magnetic variants, you're going to pick that up a lot quicker.
Is that stuff really classified on how long it accumulates?
Oh, yeah. Yeah, because then if you keep track of what boats go in, and it begins to paint an image.
Somewhere you get magnetized, and you're not rubbing against metal or another magnet.
Earth's magnetic field.
Makes a giant piece of metal.
Yeah, Earth's giant magnetic field.
So theoretically, at the equator, the flux lines are at their weakest point, being that they're at their widest dispersion from the two ends.
Yep. Yep. And then again, we see this manifest itself like with the Aurora Borealis. If any of you have ever seen the Aurora Borealis, I had the opportunity in February. I went up to Fairbanks. And they say that if you're up there between October and April for 3 nights, basically you stand a 90% chance of seeing the Aurora Borealis. So we were up there for the flight up there, we saw them from the airplane. The first 2 nights, it was phenomenal. We couldn't have planned it any better because there was a huge solar flare. And that's exactly that Earth's magnetic field is attracting the charged particles. So as soon as they get the upper regions of the atmosphere, they ionize. So literally it's like a neon light, except it's in the sky. So I should bring in some pictures and show you. It was breathtaking, just phenomenal. You're just standing there, minus 23 degrees. It warmed up. The week prior it was like minus 47 or whatever. And I seriously, even though I had gloves on and everything, I had to take off my gloves to manipulate the camera. I ended up burning the tips of my fingers. And it took about a week for me to get the feeling back. And it's very, very dangerous, but way cool. Way cool to see this. And, people spend thousands and thousands of dollars to go up there and see that. But It's the magnetic field that's actually attracting that near the poles. Retentivity is the ability of a material to retain its magnetic field after the magnetizing force is removed. So unfortunately, a submarine hull has a high level of retentivity, and that magnetic signature, you want to strip that off because it's not desirable to have a submarine magnetized. Now, magnetic shields are made of low reluctance materials. They're used to protect electronic equipment from magnetic flux lines. Okay? Sometimes we need to protect equipment from these lines of flux because they could cause interference or even worse. Let me kind of back up for a second and see if you could connect the dots on this. We all understand that when we apply current to a conductor, we create a magnetic field, right? So, bear with me. If we have a magnetic field that happens to pass through a conductor, what do you think we're going to do? I'm going to create current. Yeah, so basically if current creates a magnetic field, an electromagnetic field can create current. This is one of the things that they kind of figured out the hard way when we started lighting off nuclear weapons. One of the side effects of a nuclear weapon was an EMP, an electromagnetic pulse. And this electromagnetic pulse was a giant magnetic pulse that would go through the atmosphere, and when it came in contact with a conductor, it induced a current where current didn't belong. Fry radios, back in the day when they first started lighting off nukes, basically we all used tubes, and tubes are high voltage devices, and it would cause some interference and some wacky symptoms, and that was about it. With us going to microchips now in integrated circuits, that amount of current is going to fry, that's our technical term for the night, fry these circuits. Okay, because we're dealing with minute amounts of current to get the job done. So all of a sudden you have an EMP, you're gonna fry stuff. And quite frankly, it really concerns me. I know enough about this where, basically if you had, everybody's afraid of a dirty bomb and everything, and yeah, that's really bad news. But I tell you what, one strategically placed high altitude nuke going off over the central U.S. is going to totally wipe us out and send us back into the Stone Age. Okay? And it's the high altitude ones that really screw things up because they're far reaching because of the line of sight. And I mean, can you imagine a world, in a world that your ATM doesn't work, in a world that your grocery store, which uses a computer to order new food and supplies from the distribution center, doesn't work, your cell phones don't work, your internet doesn't work, your computers don't work, your car computers don't work. The only people that are going to be driving around are the old people kicking old school diesel, where, compression and fuel and you've got the diesel engine running. Okay? Science fiction? No, pure science. This is how it works. So these magnetic shields are actually used in some military applications for hardening the sites, because we know that this EMP is going to cause problems. None of the consumer stuff that we use is hardened. Air Force One, what the president flies around in, is hardened. Okay, they brought that down to Kirkland Air Force Base outside Albuquerque, New Mexico, and that's where they do this EMP testing and basically prove what it's able to withstand. And again, that's all really highly classified information. The same thing with the autopilots, now it's all fly-by-wire technology. So this electromagnetic interference could cause big problems. I don't know if any of you remember years ago there was a problem with Airbus. Well, there's always been a problem with Airbus. Just different problems as time progresses. But this was the problem with Airbus was with the A320 aircraft. And the A320 was the first commercial aircraft to use what was called fly-by-wire technology. And it's actually funny, I like messing with people that are flying on it. A lot of people don't realize that up in the cockpit, there's no control yoke like this on an A320. They're flying with a joystick. And, the pilot's seat, and he's got the instrument panel in front, and right off to his left here is a joystick. And that's how the pilot, captain, has got his on the left, the co-pilot's got his on the right. So there was an air show that they were doing a flyby. And what happened is the airplane died to the symbolic low pass, and then kept going and going and going right into the trees at the end of the runway, and there was a huge fireball and explosion, and a bunch of people got killed. But there were a bunch of people, including the pilot, that survived. And he was like, man, I don't know what happened. I was pulling up the whole time. The aircraft was not responding. So in basically the investigation, they determined at this big air show in Europe, there were military aircraft that were present. They had their high energy weapons fire control radars turned on, and they think that high energy got into the computers and basically put current where current, and it got confused. So he's pulling up on the stick, to pull up and dip the wing, and the maneuver. At least I know the maneuver. It's a classic maneuver. Instead, he's pulling up and just right into the freaking trees. You can look that up on YouTube, A320 crash, and they very well documented crash. They added a lot more magnetic shielding to it. Boeing's first airplane to dabble with fly-by-wire was the 777, and it was kind of a gamble. Military aircraft have used it for years, but military aircraft are kind of a different animal. If you got a problem in a military aircraft, eject, 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 pow, you punch out, and you live to fight another day. In a commercial airliner, you got hundreds of people behind you. There's no eject, eject, eject. It's like you got to ride it out and you fix the problem. So Boeing's first airplane with fly-by-wire technology was the 777. And believe it or not, it was kind of funny because Boeing opted for standard controls, not the joystick. They could have done a joystick, because basically the standard controls are controlling the equivalent of a joystick, but it makes a pilot feel like they're kicking it old school, and they're not kicking it old school. They're still putting in inputs that create small currents to feed a computer, and then the computer controls the control surfaces of the aircraft. So in a lot of cases like that, suffice to say, you reckon Boeing's got some really good magnetic shielding on their flight control systems, fly-by-wire? Absolutely. It's to prevent current from being where current doesn't belong. And any time there is a magnetic field, you run the risk of putting current where current doesn't belong.
So would like a lightning strike?
Absolutely.
Okay.
Absolutely. And that was actually one of the other problems, too, that Boeing had. Every commercial airliner statistically gets struck by lightning once a year. So next time you go on your dream vacation or whatever you got on that airplane, suffice to say that airplane was probably struck by lightning in the past year. As Boeing went to, and for most aircraft it's not that big of a deal, because what happens is when an aircraft is struck by lightning, it follows what's called skin effect, and that current passes over the skin of the aircraft. I mean, it could scare the dickens out of you if you're on board. It's going to be a big, and in some cases, fireball coming through the cabin, and, it's going to scare the dickens out of you, but it's not going to bring the airplane down. One of the manufacturing trends now with aircraft, though, is not to build airplanes out of aluminum, it's to build it out of composites, okay? If you're using carbon, they're not always using carbon, they're just using various composites. So one of the things that they're doing on aircraft now, especially control surfaces, flaps, ailerons that control the roll of the aircraft and such, these would typically be made out of composites. So you get struck by lightning, it's quite simple. The lightning gets in there, has nowhere to go, it blows the control surface apart. Not good if you're in the airplane. Okay, because now you're going to lose control because you don't have the ability to control the aircraft anymore. So what Boeing actually started doing is that by basically putting in a conductive layer into the composites, so that will allow current from a lightning strike a place to dissipate. So kind of get rid of the aluminum only to put a conductor back into the composite. It's still highly efficient and lighter and stronger and everything else. I guess lighter and stronger. I don't know. When they fail big. But I guess aluminum, when aluminum fails, it fails big too. So I don't know. I like kicking it old school. Electromagnetic induction is the principle behind the generation of electricity, and I think all of you know where I'm going with this because we just talked about EMP. A magnetic field passing through a conductor is going to induce current. Current is produced when a conductor passes or is passed by a magnetic field. As the conductor passes through the magnetic field, a deficiency of electrons is going to be created. This results in a difference of potential between the ends of the conductor. So again, if you've got a long piece of wire, you pass a magnetic field through it, you're going to induce current. Many years ago, I think the space shuttle conducted an experiment like that. And literally what they did is they trailed a long wire loop, and what their goal was to try to drag it through the Earth's magnetic field and see if they could, generate current from that. Basically, they vaporized the wire. That's how much current they generated from the Earth's magnetic field. So if there was a way of harnessing the Earth's magnetic field as a generator, our energy woes would be over. But I don't think there's a, adequate way of harnessing it at this point.
What was the experiment they did? They tried to do what with it?
Basically trailed a wire and pulled it through the Earth's magnetic field and vaporized the wire. So when the conductor is removed from the magnetic field, the free electrons return to their parent atom. So what we're doing is we're getting electrons to move in a conductor. By getting electrons to move in a conductor, we call that current. So we're creating current. Faraday's law. The induced voltage in a conductor is directly proportional to the rate at which the conductor cuts the magnetic lines of force. Okay? Going to make this real simple for you to understand Faraday's law here. Okay? Envision up here that I have a big north pole, big magnet sitting here, boom, big, giant. And here I have a big south pole. You all agree that I've got lines of flux that are going from the north pole to the south pole? And all that stuff that I talked about earlier, the straightest line, the shortest distance, right? So in between here, I'm going to have a strong magnetic field if I had a giant magnet right here. Do you agree with that? Okay. Faraday's law says that if my conductor, if I got a conductor, this is a conductor. When I say conductor, I'm not talking just a piece of wire. I'm talking about a piece of wire that has a loop in it. So the current's got to have somewhere to go, and it has to have a load, right? If I get this and I move it perpendicular to the lines of flux, I'm going to generate my maximum amount of current because I'm doing what? I'm cutting the lines of flux. If I get the conductor and I move it parallel to the lines of flux, nothing's going to happen. I mean, nothing is going to happen because the lines of flux are going north pole to south pole. So me with the conductor moving it like this all day long, nothing's going to happen. All of a sudden I move it like this, I'm moving it right through those lines of flux, perpendicular. So I'm going to get maximum effect of cutting those lines of flux. So that's, in essence, Faraday's law.
Now, what would happen if you move that more towards the north or the south end of that?
It's me cutting those lines of flux. So I'm still going to have a strong effect by simply cutting it. Now, if I'm doing it at a 45-degree angle, what am I going to be doing? I'm really half effective. It's not this, and it's not this. It's going to be half at 45 degrees. Faraday's law.
My wife, we still got him.
But I'm cutting it at a 45-degree angle, so I'm not cutting the maximum lines of flux. By cutting it at 90, I'm getting the maximum out of it. So that's Faraday's law. This here, don't try this in your car on the way home. Somebody will think you're like doing gang signs or something, Yo, I'm an electronics student. Yo. This is called the left-hand rule. And the way that this thing works is that your finger points in the direction of flux. Which way does flux go? Which way does flux go? From where to where? Positive to negative? East to west? Bzz, bzz, north to south. I said that earlier, right? Flux goes north to south, north pole, south pole. So this means north to south. That's the direction that the flux is pointing in. Make sense? My thumb is going to point in the direction of motion. So as an example, let's go back to me with this wielding the yardstick here. Is this a yard? This is a yardstick, 36 inches. That's one of the reasons that I'm real happy that we're not on the metric system, or we weren't when I grew up. Because having attended a Catholic church for school for a period of time, the nuns, if the nuns had been equipped with meter sticks, as opposed to yardsticks, there's a good chance I wouldn't be here with you today. Okay, because that additional 3 inches would have been just enough probably for them to connect. And yes, I was beaten by the nuns. Anyway, so I've got a north pole here, a south pole here. Remember that, north here, south here. Okay, so that means the lines of flux are going which way? North to south. So I got to do what? Make sense? I'm going in this direction. Okay, so with the left-hand rule, now my thumb is going to point in the direction of motion. So this means the conductor is moving down through this scenario. And if that's the case, my middle finger is pointing towards me. Which way does current flow? This is not a trick question, folks. Negative to positive. So that means I am positive with respect to my finger, negative to positive. Current is going to flow towards me. Okay? To make it easier, let's make this the North Pole. Let's make this the South Pole. And let's move our conductor. Let's move our conductor down. By moving the conductor down, current now is going to be flowing away from me. Negative to positive. Make sense? So again, will you ever use this in industry? I doubt it. But this is a way of determining which direction we're going to induce current in a generator based on relative motion. Now, magnetic and electromagnetic applications. Probably the biggest and most important is the AC generator. AC generator converts mechanical energy to electrical energy by utilizing the principle of electromagnetic induction. And this is the most popular way of producing electricity. Now, whether we turn this AC generator, we're going to turn it by the shaft, right? Whether we turn that shaft from steam and a turbine that's generated from coal, oil, nuclear, hydroelectric, it's irrelevant. The key is that we're turning the shaft. And turning the shaft, we turn the generator. That's what produces the electricity. Now, if we take that another step, are there means that are more efficient than others? Are there means that are more ecologically minded than others? Are there, what we watched last week in our program meeting on Wednesday? I mean, even that dude, who was, pretty much a tree-hugging kind of guy saying, hey, I've rethought nuclear, and although nuclear is dangerous and it's something we need to be aware of, polluting the environment with coal is worse. So things for us to think about. But the key here is by turning that shaft, we generate AC electricity with an AC generator. This is how it works. This is how an AC generator works. And the thing that I want to point out to you here is that these are the magnets. And these magnets could be permanent or they could be electromagnets. They could be permanent or they could be electromagnets. As a matter of fact, this is exactly what is taking place in your alternator in your car. Okay? In your alternator in your car, are those permanent magnets or are they electromagnets? Does anybody know? Alternator in your car, which produces voltage for us. It's a generator. Are they permanent magnets or are they electromagnets?
Are they electromagnets?
That's my question to you. What's that?
I'd say they're natural magnets.
No.
No?
No, because there's you have power going to it.
And what do you call that? If some of you have ever played around with an alternator, you might remember. As soon as I say it, you're going to know if you've played around with it before. It's called your field windings. Your field windings. Your field windings produce an electromagnetic field. This is why if you know how you can push start a car? You can push start a car if it's dead. You can push start a car if it's dead. If your battery is totally dead, you're not going to push start a car. Some of the older VWs are different magnetos, different system. Okay. Different on my aircraft. My aircraft doesn't have a system like that. It has a magneto. So if I get that prop rotating, I'm creating a spark that will support the combustion process. Okay?
Like a kickstart motorcycle?
Kickstart motorcycle. So, your car, if your battery is totally dead, if you remove your battery and try to push start your car, pop start it, it ain't gonna work. Okay? If your battery is kinda dead, not enough to crank the starter, but enough to go click, 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 that's probably enough to create enough of a magnetic field so when you push the car, pop the clutch, start the combustion process, get the engine turning, immediately you're going to start to increase the voltage to these windings. So these windings could be I don't really know of any applications that use permanent magnets here. Most all use windings. The same thing for a power generating plant like at Grand Coulee Dam. They got to start off with a little bit of voltage to create the magnetic field and then get the generation process going. They're not permanent magnets. Okay, so this loop of wire, this is an artist's depiction, this loop of wire has a light side and a dark side. This is just so you could see it for the purposes of illustration. But this here is actually a loop of wire. The loop, the armature here is connected to these slip rings. These slip rings allow the armature to stay connected 360 degrees of the rotation. So if we look at this right now, North Pole, South Pole, North Pole, South Pole, the armature right here, with the winding here at the top and the winding at the bottom. Is the winding right now parallel to the lines of flux or perpendicular to the lines of flux? Parallel. It's right at the top. You see how it's right at the apex here, the top? So right at this moment in time, it's parallel to the lines of flux. How much current do we generate when we're parallel to the lines of flux? Faraday's law. How much? 0. And look what we're generating right here. 0. When we rotate that armature now, we're going to rotate it. We're going to connect the shaft to this and we're going to blow on it and make the shaft turn through a wind turbine, or we're going to steam and rotate the shaft through a steam turbine or whatever. But when we rotate the shaft now, how many degrees have I rotated it from my peak? 90. So right now, is the armature parallel or perpendicular? Perpendicular. What does Faraday's law say? When I'm perpendicular to the lines of flux, I generate my maximum amount of current. Well, look what we did. When we rotated it 90 degrees, now I'm at my maximum peak value. When I rotate my armature another 90 degrees, see how I started out here at the top? Then I rotated it 90. Now I rotate it another 90, so I'm actually 180 degrees from where I started off. Am I parallel or perpendicular to the lines of flux? Parallel. What does Faraday's law say? 0. What am I generating? 0. I rotate it another 90 degrees. Now I'm coming up on the back side, 270. Parallel or perpendicular? Perpendicular. What am I going to do? Generating Faraday's law, maximum, cutting my maximum field. I'm right here. I complete that cycle. I've just created 360 degrees of a sinusoidal waveform. This is an AC generator. Half of this is positive, half of this is negative. If you're actually an electron caught in this whole thing, basically what happens is you get moved X amount in this direction, then you go back to 0, and then you get moved X amount in this direction, and then you go back to 0. You never really go anywhere, but you do get shaken back and forth, back and forth, back and forth. Make sense? It's an AC generator. A DC generator, and actually, by the way, does anybody know who the father of the AC generator was? Who do we give credit to AC generation?
Tesla.
Tesla, very good. Nikola Tesla. He said AC was the way to go. There was another guy, big in history, who said DC is the way to go. Anybody know who that dude was? Edison. Actually more of a household name. Everybody knows Thomas Edison. Actually, when I first entered this industry, nobody even knew Tesla. Tesla recently has gained some acclaim or a cult following, depending on how you want to look at it. But Thomas Edison, he wanted to wire up everything in DC. If you go back to New York City, which is actually the power company back there is Consolidated Edison, Con Edison, really started out by Edison. Edison got the first contract to wire up the New York City, and he wired up a lot of the buildings for DC. And again, we're not going to get into it here in class. You could look at YouTube Edison experiments, electrocuting animals, you know, Tesla experiments, and they'd get like an elephant and like, you know, electrocute it and like, you know, kill it dead and say, you see, this is why you don't want to use DC. This is why you want to use AC. AC is much safer, you know, and sort of like killing animals and stuff on, you know, so you can look that up on your own YouTube. We're not going to do it here. But I mean, these dudes were at each other because it meant world domination, you know, who's going to get the contracts. And again, Tesla was right. AC is much more efficient to transmit. We'll talk about that later on. So DC never really caught on. But a DC generator, this is how what a DC generator looks like. Again, you've got an armature, but note here, as we rotate this, we're coming in contact here with, this is called a commutator. And the commutator only makes contact for 180 degrees. So what happens is as we rotate the armature through, we're going to generate a positive pulse. Then what's going to happen is we're going to break that electrical connection because the commutator only makes contact for 180 degrees. And then what we're going to do is harness another positive pulse. So it's positive pulse, positive pulse, positive pulse. It's a definition of DC. Definition of DC. AC is half positive, half negative alternation. This is positive, positive, positive. This is almost like a battery. Not quite. This is a pulsating DC, as where a battery would be constant DC, created chemically. So the big thing you need to remember is that an AC generator has slip rings, and it maintains contact for 360 degrees of the rotation of the armature. A DC generator has a commutator, and it maintains contact for 180 degrees. But the same principle is applied. We're either cutting the lines of flux or we're not. Now, a relay. A relay. Anybody here have any experience working on any relays? Okay. Relays are popular. And they still are popular because for handling high amounts of current, it's still a very viable way of control. A relay is an electromagnetic switch that opens and closes with an electromagnetic coil. So real simple. With a relay, I create an electromagnetic field with a coil. What I have is an armature above that coil, and that armature has a contact on it. And it has a spring that basically, when the electromagnetic field is energized, it pulls the armature down, making an electrical contact. When I de-energize it, it has a spring that opens it back up. Energize, makes electrical contact, de-energize, opens up the circuit. Or I could do it the opposite way. I could be making electrical contact, and when I energize the electrical circuit, it's going to open the circuit. Relays also could have multiple ganged contacts, so when I energize it, I'm opening and closing a bunch of contacts. But a relay is an electromechanical switch. It's using electromagnetism to move that armature up and down. The good news is it's an electromechanical switch. It's going to fail often, and you're going to need highly qualified, competent technicians to go in and troubleshoot it. It's called job security. They replace that with something that's solid state, it's not going to need to be replaced. So as long as there are relays, there's stuff for us to fix. We use relays when it's desirable to have one circuit control another circuit. Typically one low power circuit controlling another high power circuit. These lights would be an example, although I don't know if we've got a relay integrated in. I know that there's a relay that's integrated with a motion sensor. So when the switch is energized, that motion sensor, you'll actually hear if you walk in here and the lights are off, especially over here, you'll hear the click. When that obnoxious, somebody's looking for a project, rewire this thing to keep that thing from ever shutting off when you're in the lab. It becomes pretty obnoxious. It's also used to control several circuits some distance away. So an example of like a relay would be, anybody here play with model trains at all? Model trains are nothing more than a small example of the real thing. If you look at a freight yard on how they switch and build trains, they basically have switches that move an entire, it's a motor that will move an entire railroad track so that trains, could be built on different sidings and such. Well, how do you control that? The switch alone would be like a Frankenstein, switch. You can't do that. Typically, in a switching yard, you'll have up in a control tower, a small switch that they throw that sends a small signal out to a big relay that ka-chunk makes connection and allows all that current to flow and turn the motor, which boom switches the track. It wouldn't be practical to have, wire this thick going to a control tower, knocking, it would pull the control tower down. Wouldn't make sense. So it's used to electrically isolate the two circuits. Make sense? Okay. Example of this would be a doorbell. Small signal voltage bringing about a large change. Large change is you getting woke up out of a sound sleep because the delivery man's outside delivering a package. Here are some examples of relays. Some of these relays are actually encapsulated so they could be put in a explosive environment, because when you open and close that contact, what are you doing? There could be a spark. There could be a spark. So if you're working at an oil refinery, you probably don't want that spark. You want that spark to be contained, so it's going to be in a sealed relay. This one right here, you can probably see the contacts. There's two contacts here, and that thing is going to open, close, big sparks. Now a solenoid is a coil when energized pulls a plunger that does some mechanical work. An example of this might be door chimes. I'm talking about the old school ding dong, right? Those are physically little hammers hitting chimes. Now most of the stuff, even like clocks, if you buy a clock that has chimes, it's not chimes, it's a recording of chimes, synthesized, okay? There's very few examples of real chimes being struck by solenoids. Another example is your automotive starter. When you turn the key, typically you turn the key, that energizes a starter relay. The starter relay energizes the starter solenoid. The starter solenoid on your car is probably about the thickness of this laser pointer, and on the top is going to be a big piece of metal that when you energize it, it's going to pull that metal down and make a big electrical connection. That big electrical connection basically takes all of the energy from your battery and dumps it into your starter. There has to be physically a lot of metal present to make that electrical connection. So a relay has a moving armature. A solenoid has a moving plunger, a moving core, if you will. If any of you have ever played a pinball machine, the flippers, solenoids. When you hit the button, the flipper, it's energizing a solenoid. That solenoid is attached physically to the flipper. That's going to move back and forth, energize, de-energize, energize, de-energize, energize, energize, de-energize. Pinball. Anybody here like pinball? It's the bomb. It's pure. It's the pure game. Look for a project. There you go. Restore a pinball machine. You could restore a pinball machine, contemporary pinball machine. It's got everything. Electrical, mechanical. You've restored one?
I have 3 that need to be done.
Really? There you go. There's projects.
Big project.
There's projects right there. What era?
60 to 70.
Really?
Old school.
Huh? I've got one. I've got F-14 Tomcat. It's the real deal, man. If any of you remember that one, it had the big gumballs on the top, red, white, and blue. When you get it into the advanced levels, those things light up. It was actually considered the most obnoxious pinball machine ever created. Because if you're in a bar, you know, and those freaking lights, you know, it looks like a police car parked there or whatever. When you get into the, you know, multi-ball, it's pretty slick. What's that?
Valley or
Williams.
Williams?
Yeah. Good stuff.
In your
87.
That's after Williams bought Valley.
One of my other favorites, I've been keeping my eyes open. If I find one and bring it home, my wife will kill me. Because that one pinball machine, she's freaking, when are you going to get rid of that thing? Never. I mean, it's so freaking cool, man. And I keep it operational, you know. But the other one I'm always looking for is Cyclone. If any of you remember Cyclone?
Oh, wow.
And it was a big, you know, during the Cold War, Ronald Reagan. And actually, there's a Cyclone roller coaster. And then the front car is Ronald and Nancy Reagan holding on for dear life. Great pin, great pin. Anyway, pinball brought to you by the amazing solenoid and relays. I love the applications for these things. Actually, one of the things too with relays that's kind of fun is some airports have what's called pilot control lighting. And one of the local airports here is Bremerton National. I don't, you know, probably a lot of you don't even know Bremerton National. You can land a 737 over there. Okay, it's a big airport. You know, they don't have any commercial traffic in and out. They've actually tried in the past, but it's just Bremerton's not that big of a market. But it's a big runway. Pilot control lighting. So one of the things that I've been known to do in the past, if I'm bringing somebody that's not accustomed to aviation, is what I'll do is I'll start the approach, and I'm flying the instrument approach. So I'm following an invisible glide path down to the runway. So when the lights are turned off at the airport, it's just a black hole. You're just descending into this black void. And then usually about a half a mile out, what I'll do is I'll dial in the frequency, and then I'll hit the code. And basically it's a matter of me just turning my transmitter on and off, on and off, on and off 5 times, turns it to high intensity. So all of a sudden you're descending into this black hole, and then before you, this runway appears with the chaser lights and everything. And it's kind of a power trip, you know. I think it's kind of cool, you know, by me simply, you know, clicking my radio, I just turned on, you know, this huge airport, you know, 5,000 feet of runway lights. That's all brought to you by, well, there's the pilot control lighting aspect of the radio, but what really makes it happen is relays. It was really, you know, really relays. It was actually fun with relays too. Also called, could be called an industrial contactor. I used to be really in the, I guess I've gotten old and I'm out of the swing of things with holiday lighting. I used to cover every right angle of my house. I mean, it looked like, you know, Christmas vacation material. It was kind of funny because my next door neighbor, he worked for Boeing, is electrical engineer for Boeing. The guy across the street was an electrical engineer for the Federal Aviation Administration. So these guys, you know, I'm out there kind of messing with them and stuff, and you know, you see them plugging in an extension cord and a bush lights up, and you know, you plug in another extension cord, another, you know, the roof line lights up, and with me, I wanted to control everything simultaneously. So I got this big industrial contactor that fell off the back of a truck. And what I have are 4 separate circuits. Each circuit is up to 20 amps each. So what I did is I put in, I basically rewired my home, and I have separate circuits for the outside lights. And then I have it on a timer. I mean, I could connect it to the freaking, you know, clapper if I wanted to, right? So simply when that turns on, boom, everything is on at once. It's like, how'd you do that? This here's an industrial contactor, you know. And it's kind of a cool system.
Have you seen that video of the guy's got his computer controller
Yeah, yep, absolutely.
with music?
Yep, Yep. And actually one of the things that brings that about, and was kind of where I was segueing into, is normally for a first quarter student, you'd be taking the PLC class, ELEC 116. PLC basically is an industrial computer that controls, open and closes, basically relays for industrial control. So after taking that ELEC 116 class, if you wanted, you could buy a PLC and basically set up a Christmas display on par with you know, what we've seen on video is that with the light synchronized to music and everything. Really easy to do with PLCs. Real easy to do. Well, not easy, but doable with PLCs. Phonograph pickups. I'm sure some of the younger students are sitting in here and saying, what is a phonograph, right? You know, what's this with the scratching, right? That's what they're scratching on a phonograph, right? Uses an electromagnetic principle, believe it or not. A magnetic field is produced by a permanent magnet attached to a stylus. The stylus tracks through the groove of a record in response to the audio signal recorded. Basically, back in the day, some of you are probably familiar with this, like a musical group were cutting an album. And literally what they were doing was cutting a groove into a blank, and they're cutting an album. They're recording an album. Okay, this is how it was done back in the day. Then what that would be is a negative. Then with the positive, you could start stamping out albums all day long and, you know, getting them to radio stations, play your music and start selling it, and that's how you'd make the big time. Well, with the MP3, that's all changed. We won't comment on that. But the stylus literally tracks through that groove in the record in response to the audio signal. The movement creates a small voltage that varies at the audio signal response to replicate the wave pattern that originally created it. The induced voltage is then amplified and used to drive a loudspeaker, producing the audio, a facsimile of the audio signal that produced it. And, you know, if anybody here own any albums? Do you have the ability, okay, anybody here have a means of playing any of those albums? I actually bought a phonograph a couple years ago because I had some older records, and, you know, all the stuff's available as MP3 now, but, you know, they don't. They don't. You know, and yet for that full experience, you need a phonograph player to play it. So, kind of a classic, old school, retro way of going, but.
Digital doesn't produce warmth.
No. It's almost too clear.
Analog produces warmth.
Tell you, some of the stuff, I have a hard time, because again, growing up in Connecticut, you know, I had my little 8-transistor radio. We'd go down to the beach in the Connecticut shore, Rhode Island, Musquamacut Beach. We'd go down there and whatever. And you're listening to the New York radio station. You're listening to the hits, the top 40 hits, you know. And now I listen to some of the high quality recordings. It's kind of like, is this a remake? Or it doesn't sound like the original. You know, the original, because the original I was listening to out of a little speaker like this. You know, 8 transistors, mono. You know, now the stereo version of it, it's a little bit different. And of course, I was on a limited budget, so I wasn't always going out and buying the albums or certain albums that you had, and that was high fidelity back in the day. So how a record player would work, magnetic, that little stylus tracking in there, magnetic cartridge. Loudspeaker, basically the opposite, constructed of a moving coil around a permanent magnet. So basically, if any of you have ever bought speakers before, one of the attributes you look in, basically he or she who has the heaviest magnet, the biggest magnet, wins. Because that's the permanent magnet. And what that means is that you could throw more energy in there to create either an attraction or a repulsion and move the cone of the speaker back and forth, rapidly replicating the original sound that created it. So that's how a loudspeaker works. So the key components, the size of the magnet, the coil, how much energy measured in watts, acoustic energy. But again, it's a magnetic device. That's how it works. Magnetic recording uses the electromagnetic principle to store information. A signal is stored on tape or disc with a record head to be read back later with a playback head. Some can be combined in one package. That means record head and playback head on the same head. The way that this works, and it's kind of important that you understand this. Basically, it's like getting a piece of tape and sprinkling a bunch of iron filings on that piece of tape. By passing that tape over record head, when I speak into a microphone, I'm creating a signal in the wire. Because the microphone, which also is a magnetic device, the vibration, the air molecules moving back and forth create that vibration. The microphone picks it up and transforms that into a small electrical signal that goes in, gets amplified, and gets connected to the record head. The record head is going to fluctuate its magnetic field, putting those iron filings on the tape into a unique pattern. That pattern will be stored on that tape, not indefinitely, because if it's stored here on planet Earth, what's one of the things that it could be under the influence of? The Earth's magnetic field. If you put it in close proximity to any other electromagnetic device, it could alter that. So magnetic recordings will not last forever. As a matter of fact, a magnetic recording, every time you play it back and you try to read that fluctuation in the particles that was put on there, it loses a little bit of what it was originally. Remember how the video stores, and get younger students know, what's a video store? Well, back in the day, we used to have to go to places and rent VHS tapes, okay? Why would you have to rent tapes when it's just get it on demand? Well, that didn't exist back then. You used to have to rent it on tapes, right? Be kind of rewind, absolutely, okay? And those were the good old days. They really were, I think. Those tapes, they used to sell, they'd only get so many uses out of them, and then they would sell them as previously viewed. You know, and I used to capitalize and add to my library, if there's a movie I really liked, buy it previously viewed. But you know what? The quality was always on its way out, because every time you use that, play that tape, you'll lose a little bit of it. So like for high-end production in video, what they would do is, let's say you're making a documentary for the Discovery Channel and you're shooting it on video. Now, there's some different ways of doing it, but if you're shooting it on videotape, what they would do is they'd go out and they'd shoot, you know, with a helicopter and these beautiful shots or whatever. They'd get the original tape, they'd make one copy for the purposes of editing. Then they'd put the originals in a vault, and they wouldn't touch the originals. Then they would figure out, well, we want to edit this scene, we want to edit that scene, we want to do this. Once they figured out where all the edits were, then they'd go back to the master tapes, and they would make a recording of the segments that they want and produce a video production, knowing that every time they run that tape through the machine, they're lessening the video quality of what was on that tape. So videotape, any magnetic recording media, will over time lose its integrity. There's no way around it.
For CDs and DVDs, kind of the same deal?
Yep, if you're burning them, with basically traditional, it's not magnetic per se, but over time it will deteriorate. The best method is what's known as actual RAM, like DVD RAM. And that's for archival purposes. You want to, do DVD RAM. So that's one of the problems that I actually, as soon as they had a DVD burner that was on the market that was reasonable, like VHS to DVD, because when my kids growing up, I shot a lot of home movies and stuff. And over time, I knew those tapes were going to diminish. Every time I watched them, those tapes are going to diminish. So I got them and then transferred them. But to be honest with you, I should have transferred them to DVD RAM, RAM. And it's kind of a niche thing, but that's going to last the best, and it won't experience degradation. All these other forms of media, even if you're burning your own DVDs, they will degrade over time. So the way that magnetic tape works, that tiny gap Between the ends of the core is a magnetic field. A piece of material covered with iron oxide, basically iron filings, is pulled across the record head, magnetizing it. Information is written in a magnetized pattern. To play back or read the information, the material is moved past the gap in a playback head. The magnetic field induces a small voltage into the coil winding. When amplified, the information is reproduced. And this really revolutionized the recording industry, being able to, I mean, I remember back in the day, I'm dating myself, but wow, could actually own a cassette recorder. And I could speak into a microphone and record my voice on magnetic tape, and then you could put it in and at a later date and hear yourself. Wow, that was really the big deal. Now, we have cell phones that we talk into and digitally record that. Examples that used this technology on tape would be cassette recorders, video recorders, reel-to-reel recorders that were used in a lot of production studios and such. Floppy disk drives. Floppy disk drive is nothing more than a disk with particle on it, with iron particles on it. And believe it or not, hard disk drives. If you've got a hard drive in your computer, it's using the same technology. A little bit better? No, a lot bit better. Okay, because now you could go out and buy a terabyte drive for $49, and the reliability of that data is extremely high. And if it's properly maintained, you're really not going to lose integrity of that data. And that's really, as far as I'm concerned, that's the best method of storage. My wife and I really enjoy amateur digital photography. And when we go out and shoot something, when it's on the card, we're at risk. As soon as we plug that card in and we copy it to one drive, my primary drive, okay, then what I do is I mirror that on a secondary drive, and I mirror that on a tertiary drive. And I also pay for a service to go back to that primary drive and back it up off-site. Okay? Let me tell you, in the middle of February, right, I fly to Fairbanks, Alaska, minus 23 degrees to see the Aurora Borealis to get some pictures. I don't want to lose those pictures because my hard drive fails. So I want to make sure I have backups to backups to backups. So as long as you do that, you're good. With me just transferring a home movie to a DVD, I could lose integrity of that over time. If it's backed up digitally on a hard drive and you could, again, mirror that, then you're good. DC motor operation depends on a principle that a current carrying conductor placed in and at right angles to a magnetic field tends to move at right angles in the direction of the field. Basically what we're saying is if we could rotate a shaft and create DC, why can't we apply a voltage to a winding and create motion? So the difference between a DC motor and a DC generator is perception. Most cases they could be used either way. It's actually one of the things that they use for power management over at the Grand Coulee Dam. I don't know if any of you go recreating over in central Washington. You ever go camping or anything out there? It's really amazing. If you have a chance, go out there. This is stuff, again, they were thinking about in the early 1900s. Okay? You got the Columbia River. They built a dam on it. Not just any dam, the Grand Coulee Dam. Okay? And what they did behind the dam is they created Lake Roosevelt. For the purposes of irrigation and to store energy during low demand times, what they did is they have the generators turn. You can't stop the Columbia River. It's a river. You're going to kill all the fish. So you can't just shut the river off. You got to keep the water flowing. But if it's low demand time, get that, harness the electricity, then with the electricity, drive pumps. And they pump the water from Lake Roosevelt up to Banks Lake. Banks Lake, very popular for water skiing and recreating. Banks Lake goes to feed agriculture, and then during peak demand times, what they could do is turn it backwards and catch the energy flowing back to Lake Roosevelt, producing energy, and then catch it falling back into the Columbia River and harnessing it twice. So basically you're using the water to store the energy by simply pumping it to a higher elevation during that low demand time. Brilliant. Brilliant. You know? And again, they figured this stuff all out in the early 1900s. So that's what they've got between Lake Roosevelt and Banks Lake, basically are motor generators that you could turn either way, and either you turn it backwards, pump the water up, or catch the water falling and generate electricity.
Those giant pipes that are off to the side over there.
Yeah. And this is simply the process of creating a magnetic field that attracts and opposes and creating motion instead of motion being used to create a magnetic field. Now we're harnessing the magnetic field to create motion with a DC motor. Another area that uses electromagnetic fields, TV, radar, computer terminals. What we're talking about is the old school monitor like that. Old school monitor like that. Basically in the back of a monitor like that, there's an electron gun. So you get to go home tonight. What'd you learn about in school? My instructor was talking about their electron guns. It's going to zap us. Now, an electron gun basically sits in the back of a cathode ray tube and shoots an electron beam out towards the screen. That electron beam is going to be controlled through deflection windings. The deflection windings are horizontal and vertical. And that's what's going to be used to basically paint the image on the screen. It's your x-axis and your y-axis. So that's how we'd use that to paint an image. Now with flat screen monitors, we're doing things a little bit different, but it's kind of an evolutionary process based on what we were doing with that magnetic field. In summary, we talked about magnets, natural magnets, unnatural magnets, artificial magnets, and electromagnets. Come in many shapes and sizes. Big thing to remember, unlike poles attract, like poles repel. Two theories of magnetism, electron spin and domains. Flux lines are those invisible forces that we can't see. This lecture wouldn't be complete if we didn't talk about, anomalies. You've all heard of the Bermuda Triangle, right? Well, science or science fiction? I mean, they've got some really good hard evidence of magnetic anomalies that occur there. So if you're navigating solely by compass and you encounter unusual magnetic fields, or you're flying an airplane that's, again, has a gyro compass in it, it could cause problems, big problems for you, magnetic disturbances. There's actually, on aeronautical charts, they put down areas that have big magnetic disturbance areas that they're used to. The Bermuda Triangle is one of them. It's actually one of the things that's kind of interesting too that I see a lot of these like ghost hunters using is equipment to basically sense magnetic fields. And there's a school out there that basically says that spirits possess this energy, and this energy manifests itself as a magnetic field. So if you have sensitive enough equipment. And, I don't know, anybody watch any of those shows on TV? I've watched enough that something's going on. Something's going on. And actually, quite frankly, I think we're very naive if we only believe what we could see with our five senses. So, I think there's probably some truth in some of this stuff. We talked about the magnetic field, determining direction of flux lines. We talked about electromagnets, strength, polarity, retentivity, electromagnetic induction. We talked about Faraday's law, right? Parallel, perpendicular. We not only talked about the left-hand rule for generators, but I gave you a specific warning of not doing that in your car on your drive home. As someone might think you're giving gang signs. We talked about AC and DC generators. Big thing to remember about an AC generator, right? Slip rings. DC generator, commutator. AC generator makes a wave that's half positive, half negative. DC generator makes pulsating positive waves. Relays, basically electromechanical switches. a moving armature, or a series of ganged armatures, contacts on armature. We talked about how we could use this for doorbells, solenoids, phonograph pickups, loudspeakers, magnetic recordings. And then finally we talked about DC motors, and yes, meters. That DR's involved meter movement is nothing more than a permanent magnets and a coil. When you pass current through that coil, you either attract or oppose, causing the needle to move. And then finally we talked about the electron beams created by electron guns, which are in the back of a CRT. It's how we used to create television signals, radar displays, oscilloscopes, and computer terminals. Anybody have any questions on anything that we covered in this chapter? There's a lot of new terms to familiarize yourself with this. Less math, more remembering new terms. Question?
This doesn't have to do with this topic, but do flux lines in here have anything to do with the flux capacitor and Back to the Future?
I have the flux capacitor in Back to the Future. I have no idea what that is, and I probably wouldn't recognize it, you know, if I saw it. So yeah.
There's no reference to the flux capacitor. It's just a completely made-up thing that they came up with, huh?
Pretty much. I don't know if there's any Wikipedia references to it.
Yeah.
You know, could be a fun project to try to build one, I reckon.
I was just wondering, you know, one of the things, you know, CRTs are called cathode ray tubes, but it's really the electron beams that do it. So why would they call it the electron beam?
Well, you guys are stumping me tonight. I don't know. That's what they've always caused it. Yeah, it should be like an electron beam tube. Cathode ray tube. Cathode sends out an electron ray, and it's a vacuum tube. Cathode ray tube. Electron beam. Yeah, I don't know. Got me. Good question. Yeah, let me tell you, if I was the Pope of electronics, all of this stuff would have been called something easier or simpler. You know? Some of the stuff you just got to hit the I believe button. But suffice to say, like say magnetism, it is really, really critical. That's actually one of the things too that I don't know if you, I can't confirm or deny, but the movie Hunt for Red October, you know, that was basically a hydrodynamic drive that was based on magnetic field. And, you know, you could look at that and say science fiction. Science or science fiction. I, of course, cannot comment on it. But if you research that type of technology, the Japanese, of course, is an island nation. They're very dependent, and always have been dependent on trade. They've played around with that technology on barges to see if they could, you know, move a barge using this, you know, hydrodynamic drive system. And, you know, again, it's not mainstream, but they've played around enough with it. So.
I heard that, yeah, I would think that, you know, it might be possible to think it's really silent, but it basically send up a flare in the magnetic field that they're creating such a huge magnetic disturbance that it's not going to make the sub any more invisible.
And to be honest with you, you know, and I haven't rowed a nuclear submarine in over 20 years. I know that we had submarines out there that were so quiet you wouldn't hear the submarine. What you would hear is the submarine blocking biological noise behind it. So it's like if you had something big going past your ear, you know something is there because it's blocking the sound. So, I mean, that was 20 plus years ago. So we've never had a problem keeping quiet and keeping things real quiet. But performance is another issue. See, if you want to go fast underwater, you're going to make some noise, and that will give give you your tell basically. So, any questions? Any other questions, comments, concerns? All right. The long anticipated lecture. Chapter 10, Inductance. This is going to be an unusual property for us to discuss compared to what we've talked about up to this point. What we've talked about up to this point really is conductance, resistance, period. in discussing inductance, you're going to see that things with inductance change over time. Okay, the property actually changes. The influence it has on the circuit changes over time. So you're going to see that this is very dynamic, literally dynamic component and property. Chapter 10, Inductance. After completing this chapter, you're going to be able to explain the principles of inductance, identify the basic units of inductance, identify different types of inductors, determine the total inductance in series, parallel circuits, explain LR time constants and how they relate to inductance. Now, the property of inductance is that characteristic of an electrical conductor that opposes a change in current flow. Opposes a change in current flow. The symbol that we use is the capital letter L. So in a circuit, if you see on a schematic diagram L equals, that means inductance is equal to whatever specific amount is identified. Now, an inductor is a specific device designed to possess this property of inductance. An inductor is a device that stores energy in a magnetic field. And it's important for us to understand this property because we're going to counter this next chapter when we talk about capacitance, right? I'll let the cat out of the bag. Capacitance is an electrostatic field. Inductance is an electromagnetic field. That's what's the magic behind an inductor. Now, once current is moving through a conductor, inductance helps to keep it moving. As the magnetic flux lines build up, they create an opposition to the flow of current. An opposition to the flow of current. Lenz's law talks about that. Lenz's law states an induced EMF in any circuit is always in a direction to oppose the effect that produced it. The amount of counter EMF is proportional to the rate of change. The faster the rate of change, the greater the counter EMF. So what this means, let's go back, last chapter that we talked about. Remember magnetism? Remember when we pass current through a conductor, we create a magnetic field? Lenz's law says if the current was going that way, it's going to create an electromagnetic field like this. Make sense? If we shut the circuit off, that electromagnetic field is going to collapse, and it's going to produce a counter electromotive force that goes that way, the opposite way of what created it. So if the EMF goes that way and it creates some magnetic field like this, the magnetic field collapses, it creates a counter EMF that goes in the opposite direction. So the second part there talks about the rate of change. The faster we turn that on and off, on and off, on and off, expand, collapse, the faster we do it, the more pronounced that effect is going to be. If you connect one of them there, inductors, to a DC circuit, it's going to happen once when you close the circuit and energize it. And when you de-energize it, that field's going to collapse and create that countercurrent. So it's only going to happen once. It's going to expand once and it's going to collapse once. Now I'm going to let out a little secret because you guys have all read ahead. AC. What's one thing that's constant about AC? It's constantly changing. Very good. Constantly changing. So the higher the AC frequency is that we apply to one of these devices, the more pronounced this effect is going to be. Does that make sense? Goes back to Lenz's law. And again, anytime that in class I say anything about a law, We should like ring a bell, dim the lights, hit some chimes, you know, hit a gong, boom. Because laws you could take to the bank. You answer a question on your quiz using a law, on an exam using a law. You approach a project or a lab assignment using a law, you're going to get good results. Now, inductance is measured by the Henry, and this was invented by a guy whose name was George. Guy by the name of Joe Henry, my main man. Henry, ironically, is abbreviated with the letter H. And 1 Henry is the amount of inductance required to induce an EMF of 1 volt when the current in the conductor changes at a rate of 1 amp per second. So 1 Henry is equal to 1 volt of EMF at 1 amp per second. 1 is equal to 1 over 1 over 1 second. Now in electronics, the typical values that we're going to see will be the millihenry times 10 to the negative third. The microhenry times 10 to the negative 6th. In some high power applications, you may see henries. But generally speaking, most of the stuff that we're working with in microelectronics, millihenries, microhenries. Now, inductors are those specific devices designed to possess the property of inductance. So they're designed to have a specific inductance. That's why come they be invented. They consist of a conductor coiled around a core. Remember, if we got like X amount of magnetism by creating 1 turn, how much would we get if we make 2 turns? Twice as much. It's that simple. It's easy math. Consists of a conductor coiled around a core, and it's classified by the type of core material, whether it's magnetic or non-magnetic. If we use a magnetic core material, we're going to get a higher amount of inductance out of it. If we use non-magnetic, we're going to get a little bit lower out of it. So sometimes they'll use that core material to get it just, not too much, not too little, but just right. This is the schematic diagram for a fixed inductor. And for those of you out there that want to go home and roll your own, you could do that. You just need magnetic wire. Magnetic wire is basically thin copper wire, solid core that has a lacquer coating on it. If you've ever looked into a transformer or a motor and you see the windings, that's magnetic wire. That's all you need. Some cases you don't even need magnetic wire because you could roll a coil, and as long as the wires aren't touching each other, you're using air as an insulation, you could roll your own. I've been known to roll my own on a few times with mixed results. I have no idea what I'm talking about. Actually, I know exactly what I'm talking about. This is a variable inductor created with an adjustable core material. Now, the way they come up with this is pretty fascinating. What they'll do is they'll get a ferromagnetic core material typically, like powdered iron, and then they basically form it into a material, press it into a material, and then they thread it. And then they thread the center of the core. And what you could actually do with it, right, is righty-tighty, lefty-loosey, screw it in. And as you screw it in, what are you doing? You're increasing the magnetic influence of the iron core. So by simply adjusting that, this is used for fine tuning in a lot of circuits that contain these. Very fine, subtle tuning. Another thing that you could do, and I used to see this old school, not as much now, they would use a brass insert. And when you screw brass in, what are you doing? Brass has a high level of reluctance, so it's going to oppose that magnetic field. So by screwing it in, you're lowering the amount of inductance. If it was iron core and you screwed it in, you'd be increasing it. So it's counterintuitive. And it gets worse. Because what would happen is typically the questions that I used to be asked in a lot of my military Navy equipment schools, what we would have were circuit card extenders. So what you would do is take the circuit card out, put it in the extender, and then now the circuit card was mounted above the rest so that you could get in there and make adjustments. A lot of times you'd have to make the adjustments from the back side. They'd have a little hole physically in the board that you could put your adjustment alignment tool in. So then they'd ask, if approaching it from the back side, which direction need you turn the inductor to see a decrease in inductance? So it's one of those things that, you kind of, let's see, if I'm turning it clockwise from the top, that's going to be counterclockwise from the back side, but it's brass core, so as I'm turning it counterclockwise, I'm really moving. I mean, it's just these questions that like you thought your head was going to explode. But you know what? You kind of had a, well, I don't see how that really ever helped me in life knowing that stuff. Because basically when you got out to the fleet and you put a circuit and you set up your test fixture, and basically as soon as you start turning it the wrong way, you see needles go the wrong way. And you turn it back and you get it to where it needs to be and you're done with it. You don't sit there and, well, let's see, if I approach, and if I'm using a mirror, I'm actually seeing the inverse. I mean, just crazy stuff. But think about that, because these still, and some of you may work on some legacy equipment. It's fun to repair legacy equipment, to retrofit, to do things like that. So you may end up finding some of this stuff. This is my personal collection of inductors. You guys actually believe me. This is an air core inductor. This is a fixed value inductor, and that's all it is this wire wound around a magnetic core. That's all it is. All of these can type here are adjustable. And actually, if you could look here, this almost looks like this takes a hex head, right? Like an Allen head. Whatever you do, don't use an Allen wrench to try to adjust this. Because typically the Allen wrench in your toolkit is made out of iron, steel, ferromagnetic material. So as soon as you get it in close proximity and you adjust it and get it just so, you're going to remove part of the magnetic influence and your numbers are going to go cattywampus. So all of these need to be adjusted with non-magnetic alignment tools. I've got a tool roll at home from back in the day. I should bring it in as an example. It's this big tool roll. It's like every alignment tool known to humankind. And they're basically all plastic heads. The other thing too is, you stick your a hex head in there, you stand a chance of damaging that. And even if you break off a little bit of material, that amount of material was designed, engineered to be there to create X amount of magnetic field. So you kind of gotta get it right. So don't start, if you don't have the right tool, don't touch this stuff. So it's typically called an alignment tool, or actually a tweaker in the classical sense of the word. A tweaker. And you could always tell who the technicians were, because they'd always have the tweaker in their pockets. And you knew, it was kind of funny. Back in uniform, submarine base in Connecticut, I'd be walking around, I'd see you with a tweaker in your pocket, at the deli or whatever, and I knew exactly what you did for a living. The only guys running around, only goofballs running around with tweakers in their freaking pocket were electronics techs that were regularly aligning equipment. Air core, this is an inductor, well, not without core material because it has air in the core. That's why it's called air core. It's used for values up to 5 millihenries of inductance, wrapped on ceramic or phenolic core. In this case, it was probably wrapped around a dowel or something and then removed, and it has form in and of itself. This is actually a really good photograph because you could see the magnetic wire here, and you could see where the insulation has been stripped. This is bare wire, and then this is insulated. A lot of times people see this and they think that it's bare wire. It's not bare wire. It's insulated. One of the best ways of getting this insulation off, if you're going to do a lot of this, is with a chemical stripper. Chemical stripper. And basically it's like a thinning agent. You dip it in, paint thinner, paint remover, and it removes that right down to the metal, and it makes it solderable. You have to put a neutralizing agent on it, but that's the best way of doing it. Other than that, you know, you're going to get your wire strippers, and your wire strippers are just basically going to scratch the stuff off. It's not going to really, because this is a lacquer coating on it. But this is an inductor, believe it or not. Just a piece of wire making those 5 turns. It's going to give you X amount of inductance. Might be enough for you to get the job done. Question?
On the last air core picture that you had, there was a piece of metal going through it. What's that for?
This piece right here?
Yeah.
I think somehow this is mounted. This serves as a form somehow to keep the shape of it. I really don't know.
Usually they're hollow though.
Yeah. Oh yeah, yeah. This is not here to influence the magnetic or all. It's either there for aesthetics or to help the way that's mounted or what have you. It's a good observation. Some of these things are actually pretty cool looking. Again, when you get into some of that older equipment, they made it with a certain level of elegance, you know, and this would be an example of that. If you opened up an old, in a 1930s radio, you'd probably find an inductor that looks like that in there. 1970s radio, no, you're not going to find that in there. Iron core. Iron core could be either ferrite or powdered iron. It's a typo, not ion. Ion core. Captain, the ion core is melting down. Damn. Damn you, Scotty. That's why I'm not into drama, right? Not a very dramatic kind of guy. It's iron core. Used for values of 200 millihenries of inductance, typically, up to 200 millihenries of inductance. Schematic symbol shows these 2 parallel lines next to the coil. That shows that there's an iron core next to the coil. Torrid core, these are donut shaped, but do not try to eat them. They offer a high inductance for a small size. These are very prolific in a lot of contemporary electronic applications because the magnetic field is contained in the core, offers a very high inductance for very small size. If you opened up a computer power supply, you'd find a bunch of these inside. A lot of inductance for a relatively small package. I've had graduates that have gone to work for companies and they had to do this as part of their job, roll their own. They're given the blank core, spool of wire, and you sit there and you thread it through and tighten it up, and thread it through, tighten it up, clean the leads, and solder it in the boards. Actually pretty good jobs. Most of the people that are playing around with this stuff are for RF applications, radio frequency, high energy radio frequency. Mr. Graham, what's going on, man?
Well,
Got a question? You're just back there waving, man. It's like, what's up?
Magnetic field contained in the core, basically the significance of that is that it's not going to, the inductance is not going to stray into things around it, right? It's just going to be contained in the core as opposed to like a normal transformer is going to have a field around it.
Yeah. Yep, so it's not wasting that field going outside, it's containing it basically. Increases the efficiency, which makes it more better.
Yes. And it stimulates my hunger also.
This is a shielded core. Shielded core. have a shield of magnetic material to protect them from the influence of other magnetic fields. Because if you've got a couple of these in close proximity to each other, one field could influence another device. Now, if you just saw this, if you didn't know any better, what would you think this device was? Now, it looks like a transformer. And the only tell that there is on this is there's only 2 wires. If you look on the other side, you wouldn't find any other wires. But it would look exactly like a transformer. As a matter of fact, you can use a transformer as an inductor. If you don't connect the secondary leads to the primary, if you only use just the coil, you could use a transformer as an inductor for some applications. That's why I've got a garage full of junk, because I won't throw a transformer away, because someday I may want to use it as an inductor. This is laminated core. And again, if you didn't know any better, you'd think it was a transformer. We know it's an inductor because there's only 2 wires coming out of it. And the top is stamped 4.5 Henrys, 4.5H. And this was going to vary from 0.1 Henrys all the way up to 100 Henrys. This is also sometimes referred to as a choke. As a choke. Used as a choke in automotive applications. Noise filters, meaning to choke off a change. It's going to choke the change. Just like resistors, inductors could be connected in series parallel or series parallel. When you're dealing with inductors measured in Henrys, in series, you treat them exactly like resistors, plain and simple. If I've got 2 Henrys and I put it in series with 4 Henrys, 2 plus 4 equals 6. I now get 6 Henrys worth of inductance. In parallel, you treat them like resistors in parallel. So the total inductance will always be less than the value of least, as long as you're dealing with the property measured in Henrys. Now this is where things get interesting. Everything else I've been talking up to this point, it's just been kind of, hey, just trying to get to know you. This, the real deal. This, DIS, is what it's all about. It's a series circuit. It's a series circuit. I've got a switch that has 2 positions. One is called the growth mode and the other is the decay mode. Okay, so this switch I could toggle from either growth to decay. When it's in the growth mode, I have a simple series circuit, do I not? And the circuit contains an inductor. Actually what? An iron core inductor, because I see the parallel lines to the inductor, in series with a resistor. Make sense? When I close the switch, as soon as I close the switch, it's going to allow current to flow through this circuit. Do you agree with me? What's going to happen is that current is going to come racing through the circuit, negative to positive, and all of a sudden it's going to hit this curly piece of wire. And that curly piece of wire it's hitting is an inductor. An inductor is a specific device designed to possess the property of inductance. Inductance is that property which tries to oppose a change in current. So current was at 0, it wants to go to 100%, and this device is going to say, I want you to stay at 0. Why? Because you've been at 0 and I like it like that. But eventually, as the current continues to come, that magnetic field builds and current eventually goes to maximum. It goes to 100% for this circuit. But the inductor, because of its property of inductance, is going to fight the whole time to try to prevent that change from occurring. But eventually it's going to lose. So close the switch, turn the circuit on. the inductor is going to fight, and eventually give up, and current's going to be at 100% flowing through the circuit. And by the way, when current is at 100% flowing through this inductor, electrons are like, what's up with that? It's a piece of curly wire. After a period of time, the electrons, it's like, why am I going through a piece of curly wire? It just has no effect on them whatsoever. And the circuit runs and runs and runs. Soon as we get the switch and move the switch from the growth mode to the decay mode, the magnetic field that was built up around inductor L1 is going to collapse. And it's going to collapse into itself. When it collapses into itself, what is it going to do? It's going to act like a... What happens when a magnetic field passes through a conductor? We induce current. If we move a conductor through a magnetic field, we induce current. If the conductor is stationary and the magnetic field moves through a conductor, we're going to generate current, right? So as soon as I move this to the decay mode, this magnetic field is going to collapse into itself, creating a counter current. Lenz's law, remember, the opposite of the force that created it. And then that current is basically going to flow through the circuit until it dissipates. But if this was just a series circuit made up of a resistor, and a switch, you turn it on, boom, you go to 100%. You turn it off, pow, you go to 0. Now, with an inductor in here, you turn it on, it's going to come up and eventually get to 100%. You turn it off, the magnetic field's going to collapse and eventually it's going to get down to 0%. You follow what I'm talking about? You guys know what I'm talking about. I'm beating around the bush. What am I talking about? Time constants. Time constants. The time required for current through a conductor to increase to 63.2%. So if I apply 100% to it and that first time constant, it's going to rise 63.2%. In the next time constant, it's going to gain 63.2% of what's remaining. The next time constant, 63.2% of what's remaining. The next time constant, 63.2% of what's remaining. The next time constant, basically after 5 time constants, we say enough is enough, it's 100%. But is it really at 100%? No, because it's nonlinear. So really, it never reaches 100%. We say after 5 time constants, it's reached 100%. It's good enough for what we do. To calculate out this time constant, it's actually relatively easy. LR is the symbol used for the time constant of an RL circuit. And the formula is T is equal to L divided by R, period. It's that simple. Take the amount of inductance, divide it by the amount of resistance, that's going to give you the time constant. Measured in seconds. That's what we use as our base unit of measurement in electronics, the second. T is equal to L over R.
That would be for individual and total too, right?
Yes. If I gave you 4 inductors, you'd have to calculate out the total inductance and plug that in the circuit right there. So I could give you some real nightmare circuits right now. Think about it. It'd be fair game. I could give you a circuit that's got, 13 inductors in combination series parallel and 22 resistors combination in series parallel. The bottom line is it's equivalent to this circuit here. You've got to figure that out. But you should be able to do so without a whole lot of fuss. This is what a time constant curve looks like. Here's that first time constant, 63.2%, 63.2% of what's remaining, 63.2% of what's remaining, 63.2% of what's remaining. What's remaining? And what is it that I'm actually looking at here? What is this in blue? Is this voltage? What is this?
Current?
It's a current. Current, number one, because the slide says so. But number two, most importantly, because it's current that's going from 0. The inductor is trying to prevent the change, 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 trying to prevent the change. All right. Current wins. Then as soon as you shut that circuit off, current's going to try to go from 100% to 0, but because that magnetic field is collapsing, I don't want to decrease, I want to keep it 100%, but I can't, oh crap, all the way down to 0. But because that field is collapsing, it's going to try to prevent that change. That's why we use these. That's why we use these.
Can inductors affect voltage?
Absolutely. If we're affecting current, definitely will have an effect on voltage. In summary, inductance is the ability to store energy in a magnetic field. Just remember the key word for inductance is magnetic. That's how they do their magic. The unit for measuring inductance is the Henry, measured by the capital letter H. The letter L represents inductance. Inductors have specific inductances. That's why they're designed. The symbol for a fixed inductor is down here at the bottom. Symbol for a variable inductor has an arrow going through it. The arrow means it's adjustable. Types of inductors include iron core, ferrite or powdered iron core, torrid core, shielded core, laminated core. Formula for adding them up in series is like the same formula for adding up resistors in series. The only thing you need to be aware of, you're adding up inductance measured in Henrys. If it's not in Henrys, can't use this formula. The formula for total conductance in inductors in parallel is the reciprocal formula. Use it same as you would for resistors in parallel. Time constant formula, T is equal to L over R. You run this calculation, it shows you what one time constant is worth. I need to multiply that by how many to figure out how long it's going to take to get to 100%. 5, because it takes 5 time constants to reach 100%. So understand that when you do this math, you only end up with 1 time constant. It takes 5 to get the job done. Or as it says here, 5 time constants required to fully build up or collapse the magnetic field of an inductor. Any questions on anything that we discussed with the inductors? Yes?
I'm still a little vague on why we have inductors. I mean, other than the fact that they create inductance.
Yep, and that's it. We have inductors because they create inductance. And inductance is that property which tries to oppose a change in current. So we're going to have a lot of different components that are going to want to bring about a change in current in a circuit. And if we put an inductor in there, an inductor could help stabilize that current flow because of that electromagnetic property. So it's going to help stabilize current levels in a circuit. The majority of applications that we're going to use inductors for is really going to be filtration. Because once, we're not there yet, some of you may have read far enough ahead, that when we apply an inductor to an AC circuit, it starts doing some wacky stuff. And by harnessing that wacky property called inductive reactance, we can use that to filter. We could use it in audio applications where we want only certain frequencies to go to certain speakers. Heck, I knew a guy that was getting some interference on one of his cable channels back in the day. And because this friend of mine had extensive electronics background. He didn't want to call the cable company and have them waste their time and come out and...
They check it out.
Exactly. So this friend of mine built a filter circuit to filter out the garbage signal that somebody was putting on this pay-per-view channel. And by filtering out the garbage that got put on the channel, the reception was enhanced and made the station viewable. And the key component in that whole, so I'm told, project is an inductor. And ironically, it was an inductor that was like 3 turns of wire. 1, 2, 3 turns of wire was adequate enough for the reception to be enhanced. Mind-boggling, so I'm told. Question?
Some of us old fossils that were welding 40 years ago, and welding on sheet metal is always a problem, keep them blowing through.
Yeah.
So we just take one of the cables, and kind of like you would do a garden hose, or on the deck of a ship, just coil up a line. That would gentle things out enough that you could strike an arc and not blow.
Oh, really? Interesting.
So obviously we were making an inductor.
Yeah.
Air core.
Yeah. And little did you realize what you were doing at the time.
It just worked.
Yeah. Nobody knew why, but it worked. Now you know. All right, let's go ahead and take a break. And at about 6:20, we'll start up with Chapter 17. Y'all ready for this? Chapter 11, Capacitance. Capacitance. If you believed what I sold you last chapter, this should not be a stretch for you. Because it's kind of like the same thing is happening, but with a different property. It's really what it's all about. But capacitance is actually kind of cool. We'll talk about it. A lot of uses for capacitance. After completing this chapter, the student, you, the student, will be able to explain the principles of capacitance, identify the basic units of capacitance, identify different types of capacitors, determine total capacitance in series and parallel circuits, explain RC time constants and how they relate to capacitance. Capacitance is the ability of a device to store electrical energy. Let me stop. The ability of a device to store electrical energy. What does that sound like the definition of? Mr. Carter. That sounds like the definition of a battery, doesn't it? The ability to store electrical energy. So there's really not that big of a difference between a capacitor and a storage cell. Typically, a storage cell is a small amount of current over a long period of time, unless you're a car battery. But a capacitor generally is a large amount of current over a short period of time that it's designed to expend, if you will. But the definitions are very, very, very similar, very close. The key word on how a capacitor works is that electrostatic field. Electrostatic field. Remember inductors, they were electromagnetic. This is electrostatic. Electrostatic. Talk about that property a little bit more in a bit. The letter C stands for capacitance. So inside a schematic diagram, if you see a letter C equals, it's capacitor. If you see C22, it's capacitor number 22 in the circuit. C47, capacitor number 47. A capacitor is a device that possesses a specific amount of capacitance. How these things are made are two conductors separated by an insulator. Two conductors separated by an insulator. What does that sound like the definition for? Close your eyes and think about it. Two conductors separated by an insulator. What does that sound like? Battery. You made that up, man. Now, what would the definition of an extension cord be? Two conductors separated by an insulator. What would speaker wire be? Yeah, so you know what? There are going to be a lot of things that have capacitive properties because they're two electrical conductors separated by an insulator. And a lot of these things that have capacitance is stray capacitance and capacitance that we don't necessarily want. Engineers don't want, but we have to deal with it because it's two conductors separated by an insulator. Anytime you do that, you're going to end up with the property of capacitance. Anytime you coil up your welding wire, your welding leads, electro leads, you're going to create some inductive properties.
The old flat TV antenna wire from the 1950s.
Yep.
The conductors were way far apart.
Yep. And that actually, believe it or not, that style of twin lead antenna cable, it was some of the most efficient. When properly installed, it had higher efficiency than coaxial cable. The only thing is people would get that nice ribbon cable, and then back in the day, right, growing up in Connecticut, you know, we had aluminum windows, and you'd route it through the window and then slam the window down on it, and there goes any advantage that you had. But when you use the proper standoffs and you use the proper bend radius and everything else directly to the back of the set, that had higher efficiency, it would get more RF energy into the back of that television set than using coaxial cable. But it was two conductors separated by a thick dielectric, thick insulator material. So that's one of the things I really want you to come out of these lectures with, is understanding that, you know, this is not a lecture about capacitors. This is a discussion about capacitance and capacitors. But the biggest thing is, when you get into some of the advanced classes, like Peter Welty and his PCB design class, it's one of the biggest challenges is determining stray capacitance inside a circuit. When we're physically trying to create capacitance, we're going to call the conductors plates. And we're going to call the insulator dielectric. So two plates separated by a dielectric. Now that, Mr. Carter, is the definition of a capacitor. Schematic diagram up at the top is a fixed capacitor, meaning what you see is what you get. Within tolerances, of course. Down below is a variable capacitor. There's actually different ways that they're going to be able to vary the capacitance. One is going to be varying the distance between the plates. We'll talk about this more in a bit. And the other is meshing the plates, where they don't physically touch, but they're just closer proximity. More in closer proximity to each other, less in less proximity to each other. Make sense? Treat all capacitors as though they were charged. Never touch both leads of a capacitor with your hands. I've got a capacitor. Where the heck it went? I got to get my stash better organized. Stuff disappears in here. Actually, I had a student that worked for one of the biomedical companies, Medtronic, and they had the starter jumper kits for when you die. It's great. I see them. They got like Costco, you know. You just got $680 worth of stuff in your cart at Costco. You drive your car and they revive you on the spot. Make sure you pay your bill. Airlines got them now. We're going to charge you $25 for that bag to check it. You know, you have a heart attack, they revive you. You know, just let me die here. Anyway, had a student at work there, evening student of mine, and he brought me a capacitor that was a key component in that. And right on the capacitor was a label. The energy stored in this device could be lethal. The energy stored in this device could be lethal. So if that capacitor is charged up and I toss it to you and you touch it, it'll kill you dead. Because you're building up all of that charge and then rapidly discharging it through your body, which it's not designed to do. Capacitor can hold that charge potential indefinitely if it doesn't have a discharge path. A theoretically perfect capacitor will hold the charge forever. Because of manufacturing flaws and defects and stuff, eventually that current will dissipate. I remember when they were, I've been here for a while, not when they were building this building, not when they were building that building, the new one, not when they were building this building, but when they were building that building, like 20 years ago. And there's actually a time capsule buried out there somewhere. And they were looking for ideas from, I'm like, let's charge up a capacitor and put it in the time capsule. I mean, as an electronics guy, I think that'd be cool. Like, great, let's take it out of its protective covering and see if any voltage is still present. I mean, I would have gotten a kick out of it. They're all looking at me like I'm a goofball. I mean, don't you think that would have been an outstanding freaking idea?
Will a battery hold indefinite charge as well too, or will that dissipate faster than a
Because of the chemicals, a chemical cell will eventually dissipate. So it has a shelf life. Lithium batteries have the longest shelf life. I mean, those, what are they? The Energizer, whatever that you could buy, lithium, best batteries that you could buy. Very great product, innovative product. If you absolutely positively have to have a portable electronic device operate under extreme temperature conditions, whatever, great shelf life, use those batteries. So I just bought some, and I think that it's good to the year 2025 or something on it. It's like, wow, that's a shelf life. The basic unit of capacitance is the farad. A farad is the amount of capacitance that can store 1 coulomb. Remember the coulomb? 6.24 times 10 to the 18th electrons of charge when a capacitor is charged to 1 volt. So we got a couple different things going on there. You got these 2 plates, and what you're doing is you're charging it, and what it's doing is you're physically loading those plates up with a large number of electrons. And then you're building up an electrostatic field across those 2 plates. So when you build up 1 coulomb across the plates, we're able to store 1 coulomb of charge and bring the capacitor up to 1 volt. We call that a farad. Now, typically the values that we're going to work with in electronics are going to be centered around the microfarad. The typical value of measurement of capacitance is the microfarad, which is times 10 to the negative 6th. And also the picofarad, which is times 10 to the negative 12th. So we go from the 6th to the 12th. What's between 6 and 12? Nano. For the longest time, I used to put out in lecture, you will never see a nanofarad capacitor, because they didn't used to make nanofarad. Actually, you know what they used to call nanofarad capacitors? Millimicro. Millimicro, 3 places past milli. No, micro. Millimicro. 3 places past micro, which would be nano, so they'd call it millimicrofarad, MMF, millimicrofarad. Or they would call it tens of thousands of picofarad.
Why'd they refuse to use nano?
I don't know if it was a small letter N that just like freaked them out. Seriously. I mean, sometimes it boils down to that. It was, they'd have this Congress that would meet and analyze this stuff, and they just wouldn't. So I used to put it out in lecture. You will never see a nanofarad capacitor. Whenever I put out absolutes, somebody feels compelled to prove Joe Gryniuk wrong. So the next day, Stuart, hey, I found this, my company's using these. What's this? Showed it to me. It was like a 20 nanofarad capacitor. Great. You're doing it. It should be a 20,000 picofarad capacitor or a 20 millimicrofarad capacitor. But, and that's, I'm intentionally talking to you about this because traditionally capacitor values have been all over the place as far as how they label them and how they identify them, and sometimes determining what size capacitor is very, very difficult. And what a manufacturer labels it as. I mean, resistors were easy with color code. Sometimes you got to trust the packaging on these things. What's up?
Do you remember what the Farad rating of the capacitor that the guy brought in from the defibrillator was?
No.
High?
Yeah. Yeah, I mean, enough to kill you. But yeah, you could really, and don't do the stuff here. I mean, that's one of the things, again, we take safety seriously, but some of those big capacitors, charge that up, leave that there, or, you know. In the Navy, which was different, we were government property, you know. We always used to do that crap, you know, charge it up. It's like, hey, check this out, you know, here, catch. Pshaw, you know. Stuff freaking hurt, man. It wasn't funny. Go up to somebody with a charged capacitor, man, stick it on their neck. Cha! Yep, these people were entrusted with our nuclear arsenal. Basically, that's a high discharge device. You're using capacitors and inductors in there to create a high voltage to make someone compliant. A capacitor is either fixed or variable. A fixed capacitor has a definite value that cannot be changed. It's made a certain way, if you will. A variable capacitor is one whose capacitance can be changed by varying the space between the plates or by varying the amount of meshing between two sets of plates. Although they say mesh, the plates never touch. They have to be kept electrically isolated with an insulator in between, and that insulator could be air. Factors affecting capacitance. Now this is kind of important to understand these. If you understand these, the math makes a lot of sense. The area of the plates, right? The bigger the area, well, actually, let me put that formula up on the board, right? C is equal to Q over V. Remember that? Capacitance measured in farads is equal to Coulomb brought to a volt. 1 Coulomb brought to 1 volt equals 1 farad. Make sense? So area of the plate, what effect is that going to have? Is that going to affect Q or is that going to affect V? Q. The bigger the plate, the more electrons I could park on the plate physically, right? Because even though electrons are electrons, they still take up space. They still are comprised of matter. So very good. So the bigger the plates, what effect is that going to have on capacitance? Bigger plate, more capacitance. Smaller plate, smaller capacitance, right? Because Q and C are directly proportional, right? Because Q is sitting up on top of this here. Distance between the plates. Distance between the plates, what's that going to affect?
Static field.
So what's that going to affect? Q or V? Think of the distance between the plates as like regapping a spark plug. That's the distance between the electrodes. This is the distance between the plates. The further that you move those plates away from each other, the higher the voltage you could store on those plates. And that's where engineers have to determine, what am I trying to do here? Am I trying to store a lot of electrons? Am I trying to have a high voltage that I'm trying to build up across it? What am I trying to do? So engineers have to take that into account. So if I separate the two plates, that means my voltage that I could store will go up. If my voltage goes up, what's my capacitance going to do? It's going to drop. So engineers are faced with this compromise. Higher voltage I could store, but I'm going to get less capacitance out of it. Why is capacitance going to go down too? Well, when I separate those plates, that electrostatic field is going to diminish because the plates are physically further away from each other. So you separate the plates, get a higher voltage on it, higher voltage, lower the capacitance. The type of dielectric material, what effect is that going to have? What's that going to affect? The type of dielectric material. Is that going to affect the Q or the V? Or the C? Well, I think it's going to affect the C, yeah. Why? Because of Q or V? Think about this one. What's it going to affect? Q, bzz.
Wouldn't it affect both?
Bzz. It's going to affect the voltage. Because if I've got two plates separated by air, and then now instead of the air I slip in a piece of mica, mica has a higher dielectric constant than air, does it not? Remember you guys are deceiving me, man. Remember those lectures early in the quarter? We talked about different types of insulators. Mica was at the top of the chart. So if I slip a piece of mica between those two plates now, I could actually have those plates real close to each other and slip some mica in there and really get a high voltage across those plates. Get a higher voltage for the distance because I'm using a dielectric material that has better dielectric properties. So that's how that's going to affect V. Affect V, it's going to affect C. And then temperature. Temperature. How is temperature going to affect this? What changes with temperature?
Resistance.
Yeah, but we're not talking about resistance here, so. It's actually simpler than that. It's something probably that you all knew even before you walked in here. Things expand and contract with temperature. Right? That's why there's expansion joints on bridges. Right? Because bridges expand and contract, and if not, they'd break. You know, oh no, it got over 70 degrees today, the bridge broke. You know, no, expansion joints because things expand and contract. Capacitors are going to expand and contract. So as the plates expand, it can hold or affect Q. As the distance between the two changes, it's going to affect V. So the bottom line is the amount of capacitance will vary with temperature. For some circuits, like at room temperature, it's not that big of a deal. For some stuff, I don't think in your wildest hallucinations you've ever really thought it through where a lot of electronic systems are used. I mean, it's a pretty harsh environment. My favorite aircraft of all time, military aircraft of all time, I just get so jazzed when I see one, is the F-15 Fighting Falcon. Okay? These things were designed as high-altitude interceptors. The closest to us right here are in Portland, Oregon, the Oregon Air National Guard. So if you've ever flown commercially in and out of Portland or been down there, you might be on an Alaska Airlines jet that has to give way to two F-15s that are taking off in front of you. The F-15 still holds the unclassified time to climb record. 45,000 feet in 1 minute. That basically means you're sitting at the end of the runway at Portland International Airport. They give you the thumbs up, clear for takeoff. You advance the throttles, you kick in the afterburner, and next thing, 1 minute later, 60 seconds later, you're passing through 45,000 feet. These things are so good, they used them last summer when President Obama was in town. And there was a small plane that penetrated the airspace up here. Guy was flying into Kenmore in a float plane. And they're watching them on radar, and they got concerned. So they called up the Oregon Air National Guard, and they said, we know you got a couple fighters there and ready standby. I think it's time to scramble them. And these guys are like, woohoo! Because what they did is they not only got to take off, but they got to go supersonic. They got to go on an intercept call. So what they did is they went supersonic. I'm sure you all heard about it with the windows getting knocked out and the sonic booms. Okay? Where I'm going with this, though, is imagine that airplane sitting on the runway down there in the middle of summer, sitting on the tarmac, 115, 120 degrees, and then 60 seconds later, he's at 45,000 feet where it's negative 45. If electronics are not all in heated areas of that aircraft, so if you've got a capacitor that is in an area that is prone to temperature change, you're going to get different results. Hopefully that's not part of a targeting system on that aircraft where all of a sudden, you know, and the military's smarter than that. The reason temperature that it always strikes a chord with me, I was not always the best student, especially when I was in a lot of military schools. I went through over 4,500 hours of military schools, different systems. I was in a great position because as soon as the Russians came up with something, we had to come up with something to detect it and counter it, and I was constantly in school. Traveled through 46 of the 50 states on official business going to school, a lot of factory schools, a lot of stuff. Long schools, and it was not a school day like yours. These are 8-hour days. 8-hour days, 5 days a week. And it was back in the day, old school. So we used to go out for liquid lunches. And I mean, I used to sit in back. And I was sitting there one day and I'm like, you know, falling asleep and hopefully not snoring too loud. And I wake up and the instructor is showing me this, you know, they have the presentation and they had not PowerPoint, they had the view foils. And they're showing this oven ready light coming on. And I'm like, oven ready light. Oven ready light. I'm in electronic intercept and analysis. Why is he talking about an oven ready light coming on? I mean, if this is like, I picked the wrong time to wake up because I don't have a freaking clue what he's talking about. An oven ready light, and I'm just trying to wrap my mind around it. And actually what happened is this equipment was so sensitive, it was very secret special equipment for measuring these very specific emissions from Soviet equipment, that they put key sensitive temperature components in what was called an oven. And what it was is a small metal box inside the piece of equipment, and it had a heating coil and it had a thermostat, and it would keep that temperature stable so that the readings would be stable. And if that oven ready light was not on, that told the technician that the oven wasn't on, and the numbers, the results, could not be trusted. So that was a big thing before you use that equipment, is verifying that oven ready light was on. It was it's funny, because even though I slept through the lecture, I still remember it like it happened yesterday. This is not an endorsement to fall asleep in class. But it was a blue light. It was this blue light. And I always remember, because I'll tell you what, we had our labs were written tests, and then we had practical labs that you had to go in and troubleshoot that equipment. And I remember that the day I went into, you know, I was basically being evaluated. I had 2 instructors standing in there with clipboards and, you know, let's see how Petty Officer Gryniuk evaluates this problem here. So I walked in, and the first thing I noticed is the blue oven ready light was not on. So I knew immediately where the problem was. And I told him, oven ready light's not on. There's a problem with that circuitry. Got in there, and basically there was like a fuse that was blown, replaced the fuse, boom, fixed the problem. If you're not a vigilant technician paying attention to that, oh yeah, you could run through all the tests. Oh, everything's working okay. So some key components like capacitors that are in real critical roles in circuits may be put in a circuit or in a box called an oven where they keep that temperature really stable. For most stuff like this, you know, inside buildings and, you know, whatever, industrial controls, it's normally not an issue. Normally even an automotive application, I've never heard about anybody, you know. And actually cars are pretty freaking robust when you think about it. I mean, from, you know, I've been down in Arizona in the summer, you know, it's like stuff is melting, plastic is melting, you know, your tires are melting on the cars, it's just nuts, you know. And I went up to Alaska here in February, and you know, that was like the week before I was up there, it was negative 47. So you go to Fairbanks Airport, you land, you're going to rent a car, and it's buried in snow, but you just follow the extension cord from the post, and it's all on a block heater. You can dust it all off of them. It's all powder snow up there because it's so cold and so dry. Turn the key, fire it up. Every place you go, the hotels all have a place to plug into, though. I mean, it's just, you know, but still, that extreme cold is like, wow, the electronics work reasonably well from Arizona to Alaska. Keep these 4 factors in mind. They're critical. Dielectric constant, this is the measure of the effectiveness of a material as an insulator. Some materials of dielectric constants, paper has a dielectric constant between 2 and 3. Typically what they're talking about here is wax paper. Wax paper. Wax paper used to be used as the dielectric, as the insulator in a lot of capacitors prior to World War II. I've actually restored many an antique radio by simply going in, removing the paper caps that have deteriorated, and putting in mica caps of the same value. Just that easy, remove it. Everybody always gets an old radio, and oh yeah, it must be them there tubes. Them tubes there need to be replaced. I've restored a handful of radios, haven't replaced one tube. Got in there, replaced the capacitors. Why? Paper capacitors. What happens to paper over time? Deteriorates. It deteriorates, loses its dielectric constant, capacitor shorts out, doesn't work. Mica, dielectric constant between 5 and 6. This should be tantalum, not titanium. Titanium, they're using that in golf clubs, in Soviet submarines. This is tantalum. Tantalum is a material that has a high dielectric property. So by putting it in a tantalum capacitor, it gives you a big bang for the buck. Some of the best capacitors that money will buy, tantalum. Electrolytic capacitors. These are large capacitance for size and weight. Consist of 2 metal foils separated by fine gauze saturated with a chemical paste called an electrolyte. They're polarized, having a positive and negative lead. If you put an electrolytic capacitor into a circuit backwards, it will explode. Literally. If you put one of these in a circuit backwards, it will explode. Some of the smaller caps actually have where, like, there's an X etched on the top, so when it blows, it'll blow outward and not necessarily build. I don't know. I knew a guy that likes to play around with explosives and stuff in the past. You know, and it's all about keeping it compressed, those gases, you know, compressed, and it's going to give you a bigger bang. So some of those small caps that don't have a little release mechanism on that, you can throw some shrapnel. Some of the big caps actually have a release valve on it. So if you put it in backwards, pow. But I've seen smoke pouring out of them like a smoke bomb. If you ever want to blow up caps, let Peter or myself know. And we want to do it in a controlled, contained environment. You just do it for kicks in the lab. Somebody could lose an eye, seriously. You know, because they're little metal cans, and you put it in backwards, these things blow. Shrapnel is going to go flying.
You guys actually have a controlled area that you can do that?
I've done it before out in the back. You know, we rope off an area, and it was actually funny. We were doing that. It was one evening years ago, blowing up capacitors. You know, and pow, 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 pow. We're putting them in series and parallel and doing all kinds of wacky stuff. You know, and literally, we were doing it in the back here, and you know the second floor up above the restaurant, that patio area between the two buildings? I had debris raining down on that. So nobody really cared about it until I went to the custodians and I asked for like some you know, brooms and stuff to clean it up. And then it was kind of like, well, they all got puzzled and stuff because they're like all union here. And they're like, if it's a mess, you know, we need to clean it up. It's like, well, no, my students made this freaking huge mess out here for blowing up crap. Well, no, we'll clean it up, you know. And, oh, I'm sorry, you know, file a grievance because we're going to clean up the mess we made, you know. So it was just an odd time. I guess it's still an odd time, you know, here. But it's my personal collection of capacitors. These are all electrolytic capacitors. And on the electrolytic capacitors, you got to look for the markings here to find which lead is the negative lead and which one's the positive lead. And there will be some discerning mark on it. Some manufacturers identify the negative lead, some identify the positive lead. You just got to pay particular attention. This here, like with the band on it, that would signify the negative lead. See that solid band? You just got to look and be observant. Put it in backwards, it will explode. Paper and plastic caps, construction by a rolled foil technique. Plastic film is often used more often. Basically, if you went and got 2 rolls of aluminum foil and a roll of wax paper or a roll of saran wrap, right? Laid out one roll, put the insulator on top of it, laid the other roll out, we rolled it all up, dipped it in wax, attached leads to it, dip it in wax, you just made yourself a capacitor. So if you want to roll your own, you can roll your own. You make it out of paper, same thing. And that's exactly what paper caps were. 2 pieces of foil with wax paper between them, the leads attached, dipped in wax. That was it. And that wax didn't prevent that paper from deteriorating over time. These are plastic caps here. Basically, if you slice that open with an X-Acto knife, you'd find nothing but rolls of aluminum foil wrapped around plastic. Ceramic disc capacitors, popular because they're inexpensive to produce. They're used for values of 0.1 microfarad and smaller. Ceramic is the dielectric. They're reliable general purpose capacitors. This is my personal collection. I get all my ceramics from Mexico. I get a lot of them manufactured there.
How come that doesn't have any positive marking leads on it?
It's not electrolytic. Ceramic. These don't have a positive negative lead. It's only the electrolytic that does. Check out the value of this. This will 3 kV. It'll hand up to 3,000 volts. You exceed that, you destroy the capacitor. You operate all day long underneath that. Variable capacitors are also known as padders, trimmers, or tuners. This is a tuning capacitor. This is something you'd find in a 1960s, 50s, 60s, 70s radio. Elegant. Elegant in design. I mean, they don't make stuff like this no more. I mean, how many of these went to the landfill? A lot of these, the shaft right here, this would actually be ball bearing movement right there with a heavy grease in there, and you turn it ever so slightly. And actually what they would do with this is they'd put a big pulley on here, and then there'd be a string that was attached to your tuning dial. So when you move that knob just a little bit, it would ever so slightly move that tuning cap, and that's how you would adjust. By adjusting the capacitance, you would tune your radio. Now it's done all electronically. So this is something kind of from a bygone era. Which is good and bad in some ways. I don't know. Well, I don't think these new tuners have the sensitivity that those old tuners had. And I saw the transition in the military. When I first got into electronic intelligence gathering, there were manually operated tuners. I mean, I used to have to sit there and manually tune through, find a target of interest, intercept it, analyze it. I saw the transition to computer-operated systems, and it boggled my mind. I rode my submarine out here, and my sub was going to get a new system, so I rode it here. The work was being done in Bremerton, then they flew me back to Connecticut for the summer. Actually, I drove. It was kind of funny. I used to tell the Navy I had a fear of flying. That's why I'm in the Navy. So because I would go to so many schools, they'd pay me to travel. So it was like, I don't know, 300 miles a day per diem and hotels and whatever. So I used to get 14 days off to drive to Connecticut, so I'd go to San Diego and goof off for a week and a half, and crap, and I marathon across the country or whatever, you know. But anyway, I was getting sent to this school where it was going to be computer-controlled receivers. And I'm like, computer-controlled receivers? I mean, it was like It's like some robotic arm is going to come out and like tune the dial. I mean, how do you do that? I mean, I'm serious. I had no freaking clue what they were talking about. And that's not what they were talking about. But I just don't think we ever had the sensitivity that those old manual tuners had. The newer systems, of course, were much more efficient, and they, once you integrate computers, you can process the data. The data is only getting processed as well as it was programmed. But yeah, those old tuners, boy, I could listen to some stuff way out there. We'd be way the heck out in the middle of nowhere, and I could tune stuff in with a good antenna and good receiver. Series capacitors. Yeah, you're not looking at a typo. When you have capacitors in series, you treat them like resistors in parallel. Does anybody know why that is? Why do you suppose? It's a good try. Okay, these three capacitors are in series, are they not? What am I really limited to here? I'm limited to this plate area here, am I not? And this plate area here. What am I actually doing? I'm increasing the distance between the plates, which means my voltage goes up. That means my capacitance has to go down. Make sense? That's why that formula works. Plus, I'm getting 1, 2, 3 times the insulated material, as opposed to 1 time the insulated material. Make sense? So everything always goes back to this formula. Everything in electronics always is explained away with a formula. In parallel, what am I doing here? I've got this plate, and this plate. Now here I triple the size of my plates. I tripled the size of my electrostatic field that I could build up across the two. So what am I doing? I'm increasing my Q, which increases my C. That's why that formula works. So I don't know if that helps you, but it helps me remember formulas if I understand how the formula works. If I just give you a formula, C is equal to Q over V. Okay, I'll remember that. That's not going to do you any good. If you remember, C is equal to Q over V, increase the area of the plates. I could store more Q. Q goes up, C goes up. Distance between the plates increases, V goes up, C goes down, inverse proportional relationship. Make sense? RC time constants reflects the time required for a capacitor to charge 63.2% of the applied voltage or to discharge down 63.2%. It's not a typo, it's the way I worded it intentionally on this slide. You're decreasing down 63.2% to 36.8%. This is what the circuit's going to look like. This is the formula. T is equal to R times C. It's going to take 5 time constants. And physically what's happening with this, what kind of a circuit is this? Series. Series RC circuit. It's a series RC circuit. And when I close this switch, this capacitor here is going to be at 0 volts and it's going to start charging up to 100%. How long is it going to take to get to 100%? 5 time constants. How do I figure out what 1 time constant is equal to? T is equal to R times C. When this capacitor is at 100%, what voltage is going to be across R1? Bzz. When capacitor C1 is at 100% after the passage of 5 time constants, what voltage is going to be present across R1? 0. When 63.2% of the voltage is across C1, where's the remaining voltage going to be? Across R1. So basically, as the capacitor is increasing in voltage, the resistor is decreasing in voltage. Because this is not only a series circuit, it's also a voltage divider. It's a voltage divider. After 5 time constants, this voltage will be equal to this voltage. Voltage rise, voltage drop. After 5 time constants, this is equal to this, which means there's 0 left over. Kirchhoff's voltage law. Everything always goes back to what we talked about. I'm really not talking about a whole lot of new stuff here. Getting paid to talk about the same old stuff. Just every week I introduce a new word. This week it was inductance, capacitance.
What is it 5 times?
Why?
Why not be 2?
Because in 5 times you basically get close to 100%. That's why we call it 5 times. It's really between 5 and 6 times. Some books say 6 time constants. Some say 5. But you're so close to 100%.
Because the 6 would be 63% of 99.3% then, for the 6th consonant? Because on the 5th consonant it would be 99.3%, right? Right?
After 5 time constants, we call it even. We just say,
But the books that you say do sometimes have a 6th time consonant.
well, yeah, I mean, if you're dealing with real high power stuff, that could be a difference. If it was high power and a high voltage, it could be the difference of a couple volts, that small percentage. But generally, it's accepted 5 time constants. Every exam you take here, it'll be 5 time constants. In summary, capacitance is that property that stores energy in the form of an electrostatic field. A capacitor is a specific device designed to possess the property of capacitance. Fixed capacitor symbol on the top, variable capacitor symbol on the bottom. Capacitance is measured in farads, developed by a guy by the name of Joe Farad. Microfarads, picofarads are typically the most often used values. Instead of nano, you may see milli, micro, or you may see tens of thousands of pico. The letter C represents capacitance. 4 factors affect capacitance: area of the plates, distance between the plates, types of materials, and temperature. Capacitor types include electrolytic, paper, plastic, ceramic, or variable. To add up capacitance in series, you use the parallel formula. To add them up in parallel, you use the series formula. And to determine capacitive time constants, we use the formula T is equal to R times C. Any questions? All right. Let's go ahead and take about a 10-minute break. And when we come back, section 2 of the book, AC circuits.